Hello everyone and welcome to this advanced deep learning full course by Simplilearn. In this comprehensive program, we will dive into the concept of deep learning. Deep learning, a subfield of artificial intelligence, has made significant progress in recent years and profoundly impacted various aspects of modern world. One area where deep learning has been particularly transformative is in the advancement of chatbots and other conversational AI systems. Chatbots are computer programs designed to stimulate human conversation, and with the help of deep learning techniques, they have become increasingly intelligent, versatile, and capable of engaging in more natural and human-like interactions. Professionals with deep learning skills can access various career opportunities, including roles like deep learning engineer, machine learning engineer, data scientist, computer vision engineer, and NLP engineer. And based on data from Glassdoor, the average annual salary for deep learning professionals in the United States is around $109,000. And the average annual salary for deep learning professionals in India is 8 lakhs. So if you want to seek expertise in deep learning skills and aspire to be a part of cutting-edge field of building chatbots and service bots using deep learning, our Caltech postgraduate program in AI and machine learning provides comprehensive coverage of the latest tools and technologies within the AI ecosystem. It offers masterclasses led by esteemed Caltech faculty and IBM experts, engaging hackathons, and interactive Ask Me Anything sessions. By enrolling in this program, delivered in partnership with IBM, you will gain the expertise needed to become a professional in AI and ML. This comprehensive artificial intelligence course will equip you with the knowledge about various AI-based technologies, empowering you to excel in this field. So do check out the course link in the description for more details. Let's get started now.
And the 2.0 addressed so many things out there that the 1.0 really needed. So when we start talking about TensorFlow 1.0 versus 2.0, I guess you would need to know this for a legacy programming job if you're pulling apart somebody else's code. The first thing is that TensorFlow 2.0 supports eager execution by default. It allows you to build your models and run them instantly. And you can see here from TensorFlow 1 to TensorFlow 2, we have almost double the code to do the same thing. So if I want to do with tf.session or TensorFlow session as a session, the session run, you have your variables, your session run, you have your tables initializer, and then you do your model fit. X train, Y train, and then your validation data, your X value, Y value, and your epochs and your batch size. All that goes into the fit. And you can see here where that was all just compressed to make it run easier. You can just create a model and do a fit on it, and you only have like that last set of code on there. So it's automatic. That's what they mean by the eager. So if you see the first part and you're like, what the heck is all this session thing going on? That's TensorFlow 1.0. And then when you get into 2.0, it's just nice and clean. If you remember from the beginning, I said Keras on our list up there. And Keras is the high-level API in TensorFlow 2.0. Keras is the official high-level API of TensorFlow 2.0. It has incorporated Keras as tf.keras. Keras provides a number of model building APIs such as sequential, functional, and subclassing, so you can choose the right level of abstraction for your project. And we'll hopefully touch base a little bit more on this, sequential being the most common form. That is, your layers are going from one side to the other. So everything's going in a sequential order. Functional is where you can split the layers. So you might have your input coming on one side, it splits into two completely different models, and then they come back together. And one of them might be doing classification, the other one might be doing just linear regression kind of stuff, or a basic reverse propagation neural network, and then those all come together into another layer, which is your neural network reverse propagation setup. Subclassing is the most complicated as you're building your own models, and you can subclass your own models into Keras. So very powerful tools here. This is all the stuff that's been coming out currently in the TensorFlow Keras setup. A third big change we're going to look at is that in TensorFlow 1.0, in order to use TF layers as variables, you would have to write TF variable block. So you'd have to predefine that. In TensorFlow 2, you just add your layers in under the sequential, and it automatically defines them as long as they're flat layers. Of course, this changes a little bit as the more complicated tensor you have coming in, but all of it's very easy to do, and that's what 2.0 does a really good job of. And here we have a little bit more on the scope of this, and you can see how TensorFlow 1 asks you to do these different layers and values. If you look at the scope and the default name, you start looking at all the different code in there to create the variable scope. That's not even necessary in Tensor 2.0. So you'd have to do 1 before you do what you see the code in 2.0. In 2.0, you just create your model. It's a sequential model, and then you can add all your layers in. You don't have to pre-create the variable scope. So if you ever see the variable scope, you know that came from an older version. And then we have the last two, which is our API cleanup and the autograph. In the API cleanup, TensorFlow 1, you could build models using TF GANs, TF app, TF contrib, TF flags, etc. In TensorFlow 2, a lot of APIs have been removed. And this is they just cleaned them up because people weren't using them, and they've simplified them. And that's your TF app, your TF flags, and your TF logging are all gone. So those are 3 legacy features that are not in 2.0. And then we have our TF function and autograph feature. In the old version, TensorFlow 1.0, the Python functions were limited and could not be compiled or exported, re-imported. So you were continually having to redo your code, and you couldn't very easily just put a pointer to it and say, hey, let's reuse this. In TensorFlow 2, you can write a Python function using the TF function to mark it for the JIT compilation, for the Python JIT, so that TensorFlow runs it as a single graph. Autograph feature of TF function helps to write graph code using natural Python syntax. Now we just threw in a new word in you, graph. Graph is not a picture of a person. You'll hear graph X and some other things. Graph is what are all those lines that are connecting different objects. So if you remember from before, where we had the different layers going through sequentially, each one of those white lined arrows would be a graph X. That's where that computation is taken care of, and that's what they're talking about. And so if you had your own special code or Python way that you're sending that information forward, you can now put your own function in there instead of using whatever function they're using. In neural networks, this would be your activation function, although it could be almost anything out there depending on what you're doing. Next, let's go for hierarchy and architecture, and then we'll cover 3 basic tools in TensorFlow before we roll up our sleeves and dive into the example. So let's just take a quick look at TensorFlow toolkits and their hierarchy. At the high level, we have our object-oriented API. So this is what you're working with. You have your TF Keras, you have your estimators. This sits on top of your TF layers, TF losses, TF metrics. So you have your reusable libraries for model building. This is really where TensorFlow shines, is between the Keras, running your estimators, and then being able to swap in different layers. Your losses, your metrics, all of that is so built into TensorFlow. It makes it really easy to use. And then you can get down to your low-level TF API. You have extensive control over this. You can put your own formulas in there, your own procedures or models in there. You could have it split. We talked about that earlier. So with the 2.0, you can now have it split one direction where you do a linear regression model, and then go to the other where it does a neural network. And maybe each neural network has a different activation set on it. And then it comes together into another layer, which is another neural network. So you can build these really complicated models, and at the low level, you can put in your own APIs. You can move that stuff around. And most recently, we have the TF code can run on multiple platforms. And so you have your CPU, which is basically like on the computer I'm running on. I have 8 cores and 16 dedicated threads. I hear they now have one out there that has over 100 cores. So you have your CPU running, and then you have your GPU, which is your graphics card. And most recently, they also include the TPU setup, which is specifically for TensorFlow models, neural network kind of setup. So now you can export the TF code, and it can run on all kinds of different platforms for the most diverse setup out there. And moving on from the hierarchy to the architecture, in the TensorFlow 2.0 architecture, we have, you can see on the left, this is usually where you start out with, and 80% of your time in data science is spent pre-processing data, making sure it's loaded correctly and everything looks right. So the first level in TensorFlow is going to be your read and pre-processed data, your TF data feature columns. This is going to feed into your TF Keras or your pre-made estimators, and kind of you have your TensorFlow hub that sits on top of there so you can see what's going on. Once you have all that set up, you have your distribution strategy. Where are you going to run it? Are you going to be running it on just your regular CPU? Are you going to be running it with the GPU added in? Like I have a pretty high-end graphics card, so it actually grabs that GPU processor and uses it. Or do you have a specialized TPU set up in there that you paid extra money for? It could be if you're later on, when you're distributing the package, you might need to run this on some really high processors because you're processing at a server level for, let's say, you might be processing this at you're distributing it, not the distribution strategy, but you're distributing it into a server where that server might be analyzing thousands and thousands of purchases done every minute. And so you need that higher speed to give them a recommendation or a suggestion so they can buy more stuff off your website. Or maybe you're looking for data fraud analysis working with the banks. You want to be able to run this at a high speed so that when you have hundreds of people sending their transactions in, it says, hey, this doesn't look right. Someone's scamming this person and probably has their credit card. So when we're talking about all those fun things, we're talking about saved model. We were talking about that earlier, where it used to be when you did one of these models, it wouldn't truncate the float numbers the same. And so a model going from one, you build the model on your machine in the office, and then you need to distribute it. And so we have our TensorFlow serving cloud on premium. That's what I was talking about if you're like a banking or something like that. Now they have TensorFlow Lite, so you can actually run a TensorFlow on an Android or an iOS or Raspberry Pi. Little breakout board there. In fact, they just came out with a new one that has a built-in, this is a little mini TPU with the camera on it so it can pre-process a video. So you can load your TensorFlow model onto that. Talking about an affordable way to beta test a new product. You have the TensorFlow JS, which is for browser and node server. So you can get that out on the browser for some simple computations that don't require a lot of heavy lifting, but you want to distribute to a lot of endpoints. And now they also have other language bindings. So you can now create your TensorFlow backend, save it, and have it accessed from C, Java, Go, C#, Rust, R, or from whatever package you're working on. So we kind of have an overview of the architecture and what's going on behind the scenes, and in this case, what's going on as far as distributing it. Let's go ahead and take a look at 3 specific pieces of TensorFlow. And those are going to be constants, variables, and sessions. So very basic things you need to know and understand when you're working with the TensorFlow setup. So constants in TensorFlow. In TensorFlow, constants are created using the function constant. In other words, they're going to stay static the whole time, whatever you're working with. The syntax for constant value, dtype 9, shape equals none, name constant, verify shape equals false. That's kind of the syntax you're looking at. And we'll explore this with our hands-on a little more in depth. And you can see here we do z equals tf.constant, 5.2, name equals x, dtype is a float. That means that we're never going to change that 5.2. It's going to be a constant value. And then we have our variables in TensorFlow. Variables in TensorFlow are in memory buffers that store tensors. And so we can declare a 2x3 tensor populated by ones. You could also do constants this way, by the way. So you can create an array of ones for your constants. I'm not sure why you do that, but you might need that for some reason. In here we have v equals tf.variables, and then in TensorFlow you have tf.ones, and you have the shape, which is 2, 3, which is then going to create a nice 2x3 array that's filled with ones. And then of course you can go in there and they're variables, so you can change them. It's a tensor, so you have full control over that. And then you of course have sessions in TensorFlow. A session in TensorFlow is used to run a computational graph to evaluate the nodes. And remember, when we're talking about graph or GraphX, we're talking about all that information then goes through all those arrows and whatever computations they have that take it to the next node. And you can see down here where we have import TensorFlow as TF. If we do x equals a tf.constant of 10, we do y equals a tf constant of 2.0 or 20.0, and then you can do z equals tf.variable, and it's a tf.add x comma y. And then once you have that set up in there, you go ahead and init your tf global variables initializer with tf session as session. You can do a session run init, and then you print the session run y. And so when you run this, you're going to end up with, of course, the 10 plus 20 is 30. And we'll be looking at this a lot more closely as we actually roll up our sleeves and put some code together. So let's go ahead and take a look at that. And for my coding today, I'm going to go ahead and go through Anaconda, and then I'll use specifically the Jupyter Notebook on there. And of course, this code is going to work whatever platform you choose, whether you're in a notebook, the Jupyter Lab, which is just the Jupyter Notebook but with tabs for larger projects. We're going to stick with Jupyter Notebook. PyCharm, whatever it is you're going to use in here. You have your Spider and your Qt console for different programming environments. The thing to note, it's kind of hard to see, but I have my main Pi 3.6. Right now, when I was writing this, TensorFlow works in Python version 3.6. If you have Python version 3.7 or 3.8, you're probably going to get some errors in there. Might be that they've already updated it and I don't know it, and I have an older version. But you want to make sure you're in a Python version 3.6 in your environment. And of course, in Anaconda, I can easily set that environment up. Make sure you go ahead and pip in your TensorFlow, or if you're in Anaconda, you can do Anaconda install TensorFlow to make sure it's in your package. So let's just go ahead and dive in and bring that up. This will open up a nice browser window. I just love the fact I can zoom in and zoom out depending on what I'm working on, making it really easy to adjust a demo for the right size. Go under New, and let's go ahead and create a new Python. And once we're in our new Python window, this is going to leave it untitled. Let's go ahead and import. Import TensorFlow as TF. At this point, we'll go ahead and just run it real quick. No errors. Yay! No errors. I do that whenever I do my imports because I invariably will have opened up a new environment and forgotten to install TensorFlow into that environment or something along those lines. So it's always good to double check. And if we're going to double check that, it's also good to know what version we're working with. And we can do that simply by using the version command in TensorFlow, which you should know is probably intuitively the TF dot underscore underscore version underscore underscore. And it always confuses me because sometimes you do TF dot version for one thing, you do TF dot underscore version underscore for another thing. This is a double underscore in TensorFlow for pulling your version out. And it's good to know what you're working with. We're going to be working in TensorFlow version 2.1.0. And I did tell you we were going to dig a little deeper into our constants, and you can do an array of constants. And we'll just create this nice array, a equals tf.constant, and we're just going to put the array right in there, 4361. We can run this, and now that is what a is equal to. And if we want to just double check that, remember we're in Jupyter Notebook where I can just put the letter A, and it knows that that's going to be print. Otherwise, you'd surround it in print. And you can see it's a TF tensor. It has the shape, the type, and the array on here. It's a 2x2 array. And just like we can create a constant, we can go ahead and create a variable. And this is also going to be a 2x2 array. And if we go ahead and print the v out, we'll run that. And sure enough, there's our TF variable in here. Then we can also, let's just go back up here and add this in here. I could create another tensor, and we'll make it a constant this time. And we'll go ahead and put that in over here. We'll have b TF constant. And if we go ahead and print out v and b, we go ahead and run that. And this is an interesting thing that happens in here. You'll see right here when I print them both out, what happens is it only prints the last one unless you use print commands. So important to remember that in Jupyter Notebooks. But we can easily fix that by go ahead and print and surround v with brackets. And now we can see with the two different variables we have the 3152, which is a variable, and this is just a flat constant, so it comes up as a TF tensor shape 2 kind of 2. And that's interesting to note that this label is a TF.tensor and this is a TF variable. So that's how it's looking in the back end when you're talking about the difference between a variable and a constant. The other thing I want you to notice is that in variable we capitalize the V, and with the constant we have a lowercase c. Little things like that can lose you when you're programming and you're trying to find out, hey, why doesn't this work? So those are a couple little things to note in here. And just like any other array in math, we can do like a concatenate the different values here. And you can see we can take AB concatenated. You just do a tf.concat values, and there's our AB axes on 1. Hopefully you're familiar with axes and how that works when you're dealing with matrices. And if we go ahead and print this out, you'll see right here we end up with a tensor. So let's put it in as a constant, not as a variable. And you have your array 4, 3, 7, 8, and 6, 1, 4, 5. It's concatenated the two together. And again, I want to highlight a couple things on this. Our axes equals 1. This means we're doing the columns. So if you had a longer array, like right now we have an array that is like, has a shape 1, or whatever it is, 2, 2. Axes 0 is going to be your first one, and axes 1 is going to be your second one, and it translates as columns and rows. If we had a shape, let me just put the word shape here, so you know what I'm talking about, and it's very clear. And this is, I'll tell you what, I spend a lot of time looking at these shapes and trying to figure out which direction I'm going in and whether to flip it or whatever. So you can get lost in which way your matrix is going and which is column, which is rows. Are you dealing with the third axis or the second axis? Axis 1, 0, 1, 2, that's going to be our columns. And if you can do columns, then we also can do rows, and that is simply just changing the concatenate. We'll just grab this one here and copy it. We'll do the whole thing over. Control copy, Control V, and changes from axis 1 to axis 0. And if we run that, you'll see that now we concatenate by row as opposed to column. And you have 4, 3, 6, 1, 7, 8, 4, 7. So it just brings it right down and turns it into rows versus columns. You can see the difference there, your output. This really, you want to look at the output sometimes just to make sure your eyes are looking at it correctly and it's in the format. I find visually looking at it is almost more important than understanding what's going on, because conceptually your mind just too many dimensions sometimes. The second thing I want you to notice is this says a NumPy array. So TensorFlow is utilizing NumPy as part of their format as far as Python's concerned. And so you can treat this output like a NumPy array because it is just that. It's going to be a NumPy array. Another thing that comes up more than you would think is filling one of these with zeros or ones. And so you can see here we just create a tensor tf.zeros, and we give it a shape. We tell it what kind of data type it is. In this case, we're doing an integer. And then if we print out our tensor, again, we're in Jupyter, so I can just type out tensor. And I run this, you can see I have a nice array of with shape 3, 4 of zeros. One of the things I want to highlight here is integer 32. If I go to the TensorFlow data types, I want you to notice how we have float 16, float 32, float 64, complex. If we scroll down, you'll see the integer down here, 32. The reason for this is that we want to control how many bits are used in the precision. This is for exporting it to another platform. So what would happen is I might run it on this computer where Python does a float to indefinite, however long it wants to. And then we can take it, but we want to actually say, hey, we don't want that high precision. We want to be able to run this on any computer. And so we need to control whether it's a TF float 16. In this case, we did an integer 32. We could also do this as a float. So if I run this as a float 32, that means this has a 32-bit precision. You'll see 0 point whatever. And then to go with zeros, we have ones, if we're going from the opposite side, and so we can easily just create a TensorFlow with ones. And you might ask yourself, why would I want zeros and ones? And your first thought might be to initiate a new tensor. Usually we initiate a lot of this stuff with random numbers because it does a better job solving it. If you start with a uniform set of ones or zeros, you're dealing with a lot of bias. So be very careful about starting a neural network for one of your rows or something like that with ones and zeros. On the other hand, I use this for masking. You can do a lot of work with masking. You can also have, it might be that one tensor row is masked, 0 is false, 1 is true, or whatever you want to do it. And so in that case, you do want to use the zeros and ones. And there are cases where you do want to initialize it with all zeros or all ones and then swap in different numbers as the tensor learns. So it's another form of control. But in general, you see zeros and ones, you usually are talking about a mask over another array. And just like in NumPy, you can also do reshapes. So if we take our, remember this is shaped 3, 4, maybe we want to swap that to 4, 3. And if we print this out, you will see, let me just go and do that, Control V, let me run that. And you'll see that the order of these is now switched. Instead of 4 across, now we have 3 across and 4 down. And just for fun, let's go back up here where we did the ones. And I'm going to change the ones to tf.randomUniform. And we'll go ahead and just take off, well, we'll go ahead and leave that. We'll go ahead and run this. And you'll see now we have 0.0441. And this way you can actually see how the reshape looks a lot different. 0.041, 0.15, 0.71. And then instead of having this one, it rolls down here to the 0.14. And this is what I was talking about. Sometimes a lot of times you fill these with random numbers. And so this is the random.uniform is one of the ways to do that. Now, I just talked a little bit about this float32 and all these data types. One of the things that comes up, of course, is recasting your data. So if we have a D-type float32, we might want to convert these to integers because of the project we're working on. I know one of the projects I've worked on ended up wanting to do a lot of round off so that it would take a dollar amount or a float value and then have to round it off to a dollar amount. So we only wanted 2 decimal points. And in which case you have a lot of different options. You can multiply by 100 and then round it off or whatever you want to do. There's a lot of, or then convert it to an integer was one way to round it off. Kind of a cheap and dirty trick. So we can take this and we can take the same tensor and we'll go ahead and create a, as an integer. And so we're going to take this tensor, we're going to tf.cast it. And if we print tensor, and then we're going to go ahead and print our tensor. Let me just do a quick copy and paste. And when I'm actually programming, I usually type out a lot of my stuff just to double check it. In doing a demo, copy and paste works fine, but sometimes be aware that copy and paste can copy the wrong code over. Personal choice, depends on what I'm working on. And you can see here we took a float 32, 4.6, 4.2, and so on, and it just converts it right down to a integer value. Sorry, integer 32 setup. And remember we talked about a little bit about reshape as far as flipping it, and I just did 4, 3 on the reshape up here, and we talked about axis 0, axis 1. One of the things that is important to be able to do is to take one of these variables. We'll just take this last one, tensor as integer, and I want to go ahead and transpose it. And so I can do, we'll do a equals tf.transpose. And we'll do our tensor integer in there. And then if I print the a out and we run this, you'll see that's the same array, but we've flipped it so that our columns and rows are flipped. This is the same as reshaping. So when you transpose, you're just doing a reshape. What's nice about this is that if you look at the numbers, the columns, when we went up here and we did the reshape, they kind of roll down to the next row. So you're not maintaining the structure of your matrix. So when we do a reshape up here, they're similar, but they're not quite the same. And you can actually go in here and there's settings in the reshape that would allow you to turn it into a transform. So when we come down here, it's all done for you. And so there are so many times you have to transpose your digits that this is important to know that you can just do that. You can flip your rows and columns rather quickly here. And just like NumPy, you can also do your different math functions. We'll look at multiplication. And so we're going to take matrix multiplication of tensors. We'll go ahead and create A as a constant, 5839. And we'll put in a vector V, 4, 2. And we could have done this where they matched, where this was a 2 by 2 array. But instead, we're going to do just a 2 by 1 array. And the code for that is your tf.matmul, so matrix multiplier. And we have A times V. And if we go ahead and run this, let's make sure we print out our AV on there. And if we go ahead and run this, you'll see that we end up with 36 by 30. And if it's been a while since you've seen the matrix math, this is 5 times 4 plus 8 times 2, 3 times 4 plus 9 times 2. And that's where we get the 36 and 30. Now, I know we're covering a lot really quickly as far as the basic functionality. So the matrix, or your matrix multiplier, is a very commonly used back-end tool as far as computing different models or linear regression, stuff like that. One of the things is to note is that just like in NumPy, you have all of your different math. So we have our TF math. And if we go in here, we have functions, we have our cosines, absolute, angle, all of that's in here. So all of these are available for you to use in the TensorFlow model. And if we go back to our example, and let's go ahead and pull, let's do some multiplication. That's always good. We'll stick with our AV, our constant A and our vector V. And we'll go ahead and do some bitwise multiplication, and we'll create an AV, which is A times V. Let's go and print that out. And you can see coming across here, we have the 4, 2 and the 5, 8, 3, 9, and it produces 20, 32, 618. And that's pretty straightforward. If you look at it, you have 4 times 5 is 20, 4 times 8 is 32. That's where those numbers come from. We can also quickly create an identity matrix, which is basically your main values on the diagonal being 1s and 0s across the other side. Let's go ahead and take a look and see what that looks like. And we can do, let's do this. So we're going to get the shape. This is a simple way, very similar to your NumPy. You can do a.shape. And it's going to return a tuple, in this case our rows and columns. And so we can do a quick print. We'll do rows. Oops. And we'll do columns. And if we run this, you can see we have 3 rows, 2 columns. And then if we go ahead and create an identity matrix, the script for that, got a wrong button there. The script for that looks like this, where we have the number of rows equals rows, the number of columns equals columns, and D type is a 32. And then if we go ahead and just print out our identity, you can see we have a nice identity column with our ones going across here. Now, clearly we're not going to go through every math module available, but we do want to start looking at this as a prediction model and seeing how it functions. So we're going to move on to a more of a direct setup where you can actually see the full TensorFlow in use. For that, let's go back and create a new setup. And we'll go in here, new Python 3 module. There we go. Bring this out so it takes up the whole window, because I like to do that. Hopefully you made it through that first part and you have a basic understanding of TensorFlow as far as being a series of NumPy arrays. You got your math equations and different things that go into them. We're going to start building a full setup as far as the NumPy, so you can see how Keras sits on top of it and the different aspects of how it works. The first thing we want to do is we're going to go ahead and do a lot of imports. Date times, warnings, SciPy. SciPy is your math, so the back-end scientific math. Warnings, because whenever we do a lot of this, you have older versions, newer versions, and so sometimes when you get warnings, you want to go ahead and just suppress them. We'll talk about that if it comes up on this particular setup. And of course, date time. Pandas, again, is your data frame. Think rows and columns. We import it as PD. NumPy is your numbers array, which of course TensorFlow is integrated heavily with. Seaborn for our graphics, and the Seaborn as SNS is going to be set on top of our matplot library, which we import as MPL. And then of course we're going to import our matplot library Pyplot as PLT. And right off the bat we're going to set some graphic colors, patch force edge color equals true. The style, we're going to use the 538 style. You can look this all up. When you get into matplot library, into Seaborn, there are so many options in here. It's just kind of nice to make it look pretty when we start up. That way we don't have to think about it later on. And then we're going to take, we have our MPLRC. We're going to put a patch edge color, dim gray line width. Again, this is all part of our graphics here in our setup. We'll go ahead and do an interactive shell. Node interactivity equals last expression. Here we are, PD for pandas. Options display max columns, so we don't want to display more than 50. And then our matplot library is going to be inline. This is a Jupyter Notebook thing, the matplot library inline. Then warnings, we're going to filter our warnings, and we're just going to ignore warnings. That way when they come up, we don't have to worry about them. Not really what you want to do when you're working on a major project. You want to make sure you know those warnings and then filter them out and ignore them later on. And if we run this, it's just going to be loading all that into the background. So that's a little back-end kind of stuff. Then what we want to go ahead and do is we want to go ahead and import our specific packages that we're going to be working with, which is under Keras. Now remember, Keras kind of sits on TensorFlow. So when we're importing Keras and the sequential model, we are in effect importing TensorFlow underneath of it. We just brought in the math, probably should have put that up above. And then we have our Keras models. We're going to import sequential. Now if you remember from our slide, there was 3 different options. Let me just flip back over there so we can have a quick recall on that. And so in Keras, we have sequential, functional, and subclassing. So remember those 3 different setups in here we talked about earlier. And if you remember from here, we have sequential, where it's going one TensorFlow layer at a time. You go kind of think of it as going from left to right or top to bottom or whatever direction it's going in. But it goes in one direction all the time. Where functional can have a very complicated graph of directions. You can have the data split into 2 separate tensors, and then it comes back together into another tensor. All those kinds of things. And then subclassing is really the really complicated one, where now you're adding your own subclasses into the tensor to do external computations right in the middle of like a huge flow of data. But we're going to stick with sequential. It's not a big jump to go from sequential to functional. But we're running a sequential TensorFlow. And that's what this first import is here. We want to bring in our sequential. And then we have our layers. And let's talk a little bit about these layers. This is where Keras and TensorFlow really are happening. This is what makes them so nice to work with, is all these layers are pre-built. So from Keras, we have layers import dense. From Keras, layers import LSTM. When we talk about these layers, Keras has so many built-in layers. You can do your own layers. The dense layer is your standard neural network. By default, it uses ReLU for its activation. And then the LSTM is a long short-term memory layer. Since we're going to be looking probably at sequential data, we want to go ahead and do the LSTM. And if we go into Keras and we look at their layers, this is a Keras website, you can see as we scroll down for the Keras layers that are built in, we can get down here and we can look at, let's see, here we have our layer activation, our base layers. Activation, layer weights, there's a lot of stuff in here. We had the ReLU, which is the basic activation that was listed up here for layer activations. You can change those. And here we have our core layers and our dense layers. You have an input layer, a dense layer, and then we've added a more customized one with the long-term, short-term memory layer. And of course, you can even do your own custom layers in Keras. There's a whole functionality in there if you're doing your own thing. What's really nice about this is it's all built in. Even the convolutional layers, this is for processing graphics. There's a lot of cool things in here you can do. This is why Keras is so popular. It's open source, and you have all these tools right at your fingertips. So from Keras, we're just going to import a couple layers, the dense layer and the long short-term memory layer. And then, of course, from sklearn, our scikit, we want to go ahead and do our min-max scaler, standard scaler for pre-editing our data, and then metrics just so we can take a look at the errors and compute those. Let me go ahead and run this, and that just loads it up. We're not expecting anything from the output. And our file coming in is going to be airquality.csv. Let's go ahead and take a quick look at that. This is in OpenOffice. It's just a standard, you can do Excel, whatever you're using for your spreadsheet. And you can see here we have a number of columns, a number of rows. It actually goes down to like 8,000. The first thing we want to notice is that the first row is kind of just a random number put in going down. Probably not something we're going to work with. The second row is Bandung. I'm guessing that's a reference for the profile. If we scroll to the bottom, which I'm not going to do because it takes forever to get back up, they're all the same. The same thing with the status. The status is the same. We have a date, so we have a sequential order here. Here is the jam, which I'm going to guess is the timestamp on there. So we have a date and time. We have our O3, CO, NO2 reading, SO2, NO, CO2, VOC, and then some other numbers here, PM1, PM2.5, PM4, PM10. Without actually looking through the data, some of this I can guess is like temperature, humidity. I'm not sure what the PMs are. But we have a whole slew of data here. So we're looking at air quality as far as an area and a region and what's going on with our date timestamps on there. And so code-wise, we're going to read this into a pandas data frame. So our data frame, DF is a nice abbreviation commonly used for data frames, equals pd.read_csv, and then the path to it just happens to be on my D drive, separated by spaces. And so if we go ahead and run this, we'll print out the head of our data. And again, this looks very similar to what we were just looking at. Being in Jupyter, I can take this and go the other way. Make it real small so you can see all the columns going across and we can get a full view of it. Or we can bring it back up in size. That's pretty small on there. Overshot. But you can see it's the same data we were just looking at. We're looking at the number, we're looking at the profile, which is the Bandung, the date, we have a timestamp, our O3 count, CO, and so forth on here. And this is just your basic pandas printing out the top 5 rows. We could easily have done 3 rows, 5 rows, 10, whatever you want to put in there. By default, that's 5 for pandas. Now, I talk about this all the time, so I know I've already said it at least once or twice during this video. Most of our work is in pre-formatting data. What are we looking at? How do we bring it together? So we want to go ahead and start with our date time. It's come in 2 columns. We have our date here, and we have our time. And we want to go ahead and combine that. And then we have, this is just a simple script in there that says combine date time. That's our formula we're building. We're going to submit our pandas data frame and the tab name. When we go ahead and do this, that's all of our information that we want to go ahead and create. And then goes for I in range df shape 0. So we're going to go through the whole setup, and we're going to list tab append df location I. And here is our date going in there, and then return the numpy array list tab d types date time 64. That's all we're doing. We're just switching this to a date timestamp. And if we go ahead and do df date time equals combine date time, and then I always like to print. We'll do df head just so we can see what that looks like. And so when we come out of this, we now have our setup on here, and of course it's edited on to the far right. Here's our date time. You can see the format's changed. So we've added in the date time column, and we've brought the date over, and we've taken this format here, and it's an actual variable with a 000 on here. Well, that doesn't look good. So we need to also include the time part of this, and we want to convert it into hourly data. So let's go ahead and do that. To do that, to finish combining our date time, let's go ahead and create a little script here to combine the time in there. Same thing we just did. We're just creating a numpy array, returning a numpy array, and forcing this into a date-time format. And we can actually spend hours just going through these conversions. How do you pull it from the pandas data frame? How do you set it up? So I'm kind of skipping through it a little fast because I want to stay focused on TensorFlow and Keras. Keep in mind, this is like 80% of your coding when you're doing a lot of this stuff is going to be reformatting these things, resetting them back up so that it looks right on here. And, it just takes time to get through all that. But that is usually what the companies are paying you for. That's what the big bucks are for. And we want to go ahead and a couple things going on here is we're going to go ahead and do our date time. We're going to reorganize some of our setup in here, convert it into hourly data. Let me just put a pause in there. Now remember, we can select from DF our different columns we're going to be working with. And you're going to see that we actually dropped a couple of the columns. Those ones I showed you earlier, they're just repetitive data. So there's nothing in there that exciting. And then we want to go ahead and we'll create a second data frame here. Let me just get rid of the DF head. And DF2 is we're going to group by date time, and we're looking at the mean value. And then we'll print that out so you can see what we're talking about. We have now reorganized this, so we put in date time 03 CO. So now this is in the same order as it was before. And you'll see the date time now has our 00, same date, 1, 2, 3, and so on. So it's grouped the data together so that it's a lot more manageable and in the format we want. And in the right sequential order. And if we go back to, there we go, our air quality, you can see right here we're looking at these columns going across. We really don't need, since we're going to create our own date time column, we can get rid of those. These are the different columns of information we want, and that should reflect right here in the columns we picked coming across. So this is all the same columns on there. That's all we've done is reformatted our data, grouped it together by date, and then you can see the different data coming out set up on there. And then as a data scientist, first thing I want to do is get a description. What am I looking at? And so we can go ahead and do the df2 describe, and this gives us our describe gives us our basic data analytics information we might be looking for, like what is the mean, standard deviation, minimum amount, maximum amount. We have our first quarter, second quarter, and third quarter numbers also in there. So you can get a quick look at a glance describing the data, or descriptive analysis. And even though we have our quantile information in here, we're going to dig a little deeper into that. We're going to calculate the quantile for each variable. We're going to look at a number of things for each variable. We'll see right here, Q1, we can simply do the quantile 0.25%, which should match our 25% up here. And we're going to be looking at the min, the max, and we're just going to do this. It's basically we're breaking this down for each different variable in there. One of the things that's kind of fun to do, we're going to look at that in just a second. Let me put the next piece of code in here. We got to clean out some of our, we're going to drop a couple things, our last rows and first row, because those usually they have a lot of null values, and the first row is just our titles. So that's important. It's important to drop those rows in here. And so this right here, as we look at our different quantiles, again, it's the same, we're still looking at the 25 quantile here. We're going to do a little bit more with this. So now that we've cleared off our first and last rows, we're going to go ahead and go through all of our columns, and this way we can look at each column individually. And so we'll just create a Q1, Q3, min, max, min IQR, max IQR, and calculate the quantile of I of DF2. We're basically doing the math that they did up here, but we're splitting it apart. That's all this is. And this happens a lot because you might want to look at individual. If this was my own project, I would probably spend days and days going through what these different values mean. One of the biggest data science things we can look at that's important is use your common sense. If you're looking at this data and it doesn't make sense, and you go back in there and you're like, wait a minute, what the heck did I just do? At that point, you probably should go back and double check what you have going on. Now, we're looking at this, and you can see right here, here's our attribute for our O3. So we've broken it down. We have our Q1, 5.88, Q3, 10.37. If we go back up here, here's our 5.8. We've rounded it off. 10.37's in there. So we've basically done the same math, just split it up. We have our minimum and our max IQR. And that's computed, let's see, where is it? Here we go. Q1 minus 1.5 times IQR. And the IQR is your Q3 minus Q1. So that's the difference between our two different quarters. And this is all data science. As far as the hard math, we're really not, we're actually trying to focus on Keras and TensorFlow. You still got to go through all this stuff. I told you 80% of your programming is going through and understanding what the heck happened here. What's going on? What does this data mean? And so when we're looking in that, we're going to go ahead and say, hey, we've computed these numbers. And the reason we've computed these numbers is if you take the minimum value and it's less than your minimum IQR, that means something's going wrong there. And that usually, in this case, is going to show us an outlier. So we want to go ahead and find the minimum value. If it's less than the minimum IQR, it's an outlier. And if the max value is greater than the max IQR, we have an outlier. And that's all this is doing. Low outlier is found. Minimum value, high outlier is found. Really important, actually. Outliers are almost everything in data sometimes. Sometimes you do this project just to find the outliers because you want to know crime detection. What are we looking for? We're looking for the outliers. What doesn't fit a normal business deal? And then we'll go ahead and throw in, just threw in a lot of code. Oh my goodness. So we have, if your max is greater than IQR, print outlier is found. What we want to do is we want to start cleaning up these outliers. And so we want to convert, create a convert nan, x max IQR equals max underscore IQR, min IQR equals min IQR. So this is just saying this is the data we're going to send. That's all that is in Python. And if x is greater than the max IQR and x is less than the min IQR, x equals null. We're going to set it to null. Why? Because we want to clear these outliers out of the data. Now, again, if you're doing fraud detection, you would do the opposite. You would be cleaning everything else that's not in that series so that you can look at just the outlier. And then we're going to convert the nan hum. Again, we have x, max IQR is 100%, min IQR is min IQR. If x is greater than max IQR and x is less than min IQR, again, we're going to return a null value. Otherwise, it's going to remain the same value x equals x. And you can see as we go through the code, if I equals our HUM, then we go ahead and do, that's a column specific to humidity. That's your HUM column. Then we're going to go ahead and run a map on there and convert the non-HUM. You can see here this is just cleanup. We found out that humidity probably has some weird values in it. We have our outliers. That's all this is. And so when we go ahead and finish this and we take a look at our outliers and we run this code here, we have a low outlier, 2.04. We have a high outlier, 99.06. Outliers have been interpolated. That means we've given them a new value. Chances are these days when you're looking at something like these sensors coming in, they probably have a failed sensor in there. Something went wrong. That's the kind of thing that you really don't want to do your data analysis on. So that's what we're doing is we're pulling that out and then converting it over and setting it up method linear. So we interpolate method linear is it's going to fill that data in based on a linear regression model of similar data. Same thing with this up here with the df2i interpolate. That's what we're doing. Again, this is all data prep. We're not actually talking about TensorFlow. We're just trying to get all our data set up correctly so that when we run it, it's not going to cause problems or have a huge bias. So we've dealt with outliers specifically in humidity. And again, this is one of these things where when we start running we ran through this, you can see down here that we have our outliers found, high-low outliers, migrated them in. We also know there's other issues going on with this data. How do we know that? Some of it's just looking at the data, playing with it until you start understanding what's going on. Let's take the temp value, and we're going to go ahead and use a logarithmic function on the temp value. And it's interesting because it's like, how do you heck do you even know to use logarithmic on the temp value? That's domain specific. We're talking about being an expert in air care. I'm not an expert in air care. It's not what I go look at. I don't look at air care data. In fact, this is probably the first air care data setup I've looked at. But the experts come in there and they come to you and say, hey, in data science, this is a exponentially variable on here, so we need to go ahead and do transform it and use a logarithmic scale on that. So at that point, that would be coming from your data. Here we go. Data science programmer overview, does a lot of stuff connecting the database and connecting in with the experts. Data analytics, a lot of times you're talking about somebody who is a data analysis, might be all the way usually a PhD level. Data science, programming level interfaces, database manager, that's going to be the person who's your admin working on it. So when we're looking at this, we're looking at something they've sent to me and they said, hey, domain, air care, this is a skew because the data just goes up exponentially and affects everything else. And we'll go ahead and take that data. Let me just go ahead and run this. Just for another quick look at it, we have our, we'll do a distribution df. We'll create another data frame from the temp values and then from a data set from the log temp. So we can put them side by side. And we'll just go ahead and do a quick histogram. And this is kind of nice. Plot a figure size. Here's our PLT from Matplot library. And then we'll just do a distribution underscore df. There's our data frames. This is nice because it just integrates the histogram right into pandas. Love pandas. And this is a chart you would send back to your data analyst and say, hey, is this what you wanted? This is how the data is converting on here. As a data scientist, the first thing I note is we've gone from a 10, 20, 30 scale to 2.5, 3.0, 3.5 scale. And the data itself has kind of been adjusted a little bit based on some kind of a skew on there. So let's jump into, we're getting a little closer to actually doing our Keras on here. We'll go ahead and split our data up. And this, of course, is any good data scientists. You want to have a training set and a test set. And we'll go ahead and do the train size. We're going to use 0.75% of the data. Make sure it's an integer. You don't want to take a slice as a float value. Give you a nice error. And we'll have our train size is 75%, and the test size is going to be, of course, the train size minus the length of the data set. And then we can simply do train comma test. Here's our data set, which is going to be the train size, the test size. And then if we go ahead and print this, let me just go ahead and run this. We can see how these values split. It's a nice split of 1298 and then 433 points of value that are going to be for our setup on here. And if you remember, we're specifically looking at the data set. Where did we create that data set from? That was from up here. That was what we called the logarithmic value of the temp. That's where the data set came from. So we're looking at just that column with this train size and the test, with the train and test data set here. And let's go ahead and do convert an array of values into a data set matrix. We're going to create a little setup in here. We create our data set. Our data set's going to come in. We're going to do a look back of 1. So we're going to look back one piece of data going backward. And we have our data X and our data Y for I in range, length of data set, look back minus 1. This is creating, let me just go ahead and run this. Actually, the best way to do this is to go ahead and create this data and take a look at the shape of it. Let me go ahead and just put that code in here. So we're going to do a look back 1. Here's our train X, our train Y, and it's going to be adding the data on there. And then when we come up here and we take a look at the shape, there we go. And we run this piece of code here. We look at the shape on this, and we have a new, slightly different change on here, but we have a shape of X, 1296, 1. shape of y, train y, test x, test y. And so what we're looking at is that the x comes in, and we're only having a single value out. We want to predict what the next one is. That's what this little piece of code is here for. What are we looking for? Well, we want to look back one. That's the what we're going to train the data with is yesterday's data. Yesterday says, hey, the humidity was at 97%. What should today's humidity be at? If it's 97% yesterday, is it going to go up or is it going to go down today? If 97, does it go up to 100? What's going on there? And so we're looking forward to the next piece of data, which says, hey, tomorrow's is going to, today's humidity is this. This is what tomorrow's humidity is going to be. That's all that is. All that is stacking our data so that our y is basically x plus 1, or x could be y minus 1. And then a couple things to note is our x data. We're only dealing with the one column, but you need to have it in a shape that has it by the columns. So you have the two different numbers. And since we're doing just a single point of data, we have, and you'll see with the train y, we don't need to have the extra shape on here. Now, this is going to run into a problem. And the reason is that we have what they call a time step. And the time step is that long-term, short-term memory layer. So we're going to add another reshape on here. Let me just go down here and put it into the next cell. And so we want to reshape the input array in the form of sample time step features. We're only looking at one feature. And I mean, this is one of those things when you're playing with this, you're like, why am I getting an error in the numpy array? Why is this giving me something weird going on? So what we're going to do is we're going to add one more level on here. Instead of being 1299.1, we want to go one more. And when they put the code together in the back, you can see we kept the same shape, the 1299. We added the one dimension, and then we have our train x shape 1. And this depends again on how far back in the long short-term memory you want to go. That is what that piece of code is for, and that reshape is. And you can see the new shape is now 1299.11 versus the 1299.1. And then the other part of the shape, 432.11. Again, this is our x in, and of course our test x. And then our y is just a single column because we're just doing one output that we're looking for. So now we've done our 80%. That's all the writing all the code, reformatting our data, bringing it in. Now we want to go ahead and do the fun part, which is we're going to go ahead and create and fit the LSTM neural network. And if we're going to do that, the first thing we need is we're going to need to go ahead and create a model. And we'll do this sequential model. And if you remember, sequential means it just goes in order. That means if you have two layers, the layers go from layer 1 to layer 2, or layer 0 to layer 1. This is different than functional. Functional allows you to split the data and run two completely separate models and then bring them back together. We're doing just sequential on here. And then we decided to do the long short-term memory. And we have our input shape, which it comes in. Again, this is what all this switching was. We could have easily made this 1, 2, 3, or 4 going back as far as the end number on there. We just stuck to going back 1. And it's always a good idea when you get to this point, where the heck is this model coming from? What kind of models do we have available? And let me go ahead and put the next model in there, because we're going to do two models. And the next model is going to go ahead and we're going to do dense. So we have model equals sequential, and then we're going to add the LSTM model, and then we're going to add a dense model. And if you remember from the very top of our code, where we did the imports, oops, there we go, our Keras, this is it right here. Here's our importing a dense model, and here's our importing an LSTM. Now, just about every TensorFlow model uses dense. Your dense model is your basic forward propagation, reverse propagation error, where it does reverse propagation to program the model. So any of your neural networks that you've already looked at that looks and says, here's the error, and sends the error backwards, that's what this is. The long short-term memory is a little different. The real question that we want to look at right now is, where do you find these models? What kind of models do you have available? And so for that, let's go to the Keras website, which is the keras.io. If you go under API/layers, and I always have to do a search, just search for Keras API layers. It'll open up and you can see we have your base layers right here, class, trainable, weights, all kinds of stuff like there. Your activation, so a lot of your layers you can switch how it activates. ReLU, which is like your smaller arrays, or if you're doing convolutional neural networks, the convolution usually uses a ReLU. Your sigmoid, all the way up to softmax, softplus, all these different choices as far as how those are set up. And what we want to do is we want to go ahead, and if you scroll down here, you'll see your core layers, and here is your dense layer. So you have an input object, your dense layer, your activation layer, embedding layer. This is your kind of your one setup on there that's most common. Convolutional neural networks, or your convolutional layers, these are like for doing image categorizing, so trying to find objects in a picture, that kind of thing. We have pooling layers, so as you have the layers come together, usually you bring them down into a single layer, although you can still do like global max pooling 3D. And there is just, I mean, this list just goes on and on. There's all kinds of different things hidden in here as far as what you can do. And it changes. You know, you go in here and you just have to do a search for what you're looking for, and figure out what's going to work best for you as far as which project you're working on. Long short-term memory is a big one, because this is when we start talking about text. What if someone says what comes after the cat in the hat, little kid's book there, starts programming it, and so you really want to know not only what's going on, but it's going to be something that has a history. The history behind it tells you what the next one coming up is. Now, once we've built all our different, we built our model, we've added our different layers we want in there, play with it. Remember, if you're in functional, you can actually link these layers together and they branch out and come back together. If you do the sub setup, then you can create your own different model. You can embed a model in there that might be linear regression. You can embed a linear regression model as part of your functional split, and then have that come back together with other things. So we're going to go ahead and compile your model. This brings everything together. We're going to put in what the loss is, which we'll use the mean squared error. And we'll go ahead and use the atom optimizer. Clearly, there's a lot of choices on here depending on what you're doing. And just like any of these different prediction models, if you've been doing any scikit from Python, you'll recognize that we have to then fit the model. So what are we doing in here? We're going to send in our train X, our train Y. We're going to decide how many epochs we're going to run it through. 500 is probably a lot for this. I'm guessing it'd probably be about 200 or 300, probably do just fine. Our batch size. So how many different, when you process it, this is the math behind it. If you're in data analytics, you might try to know what this number is as a data scientist, where I haven't had the PhD level math that says this is why you want to use this particular batch size. You kind of play with this number a little bit. You can dig deeper into the math, see how it affects the results depending on what you're doing. And there's a number of other settings on here. We did verbose 2. I'd have to actually look that up to tell you what verbose means. I think that's actually the default on there if I remember correctly. There's a lot of different settings when you go to fit it. The big ones are your epoch and your batch size. Those are what we're looking for. And so we're going to go ahead and run this. And this is going to take a few minutes to run because it's going through 500 times through all the data. So if you have a huge data set, this is the point where you're kind of wondering, oh my gosh, is this going to finish tomorrow? If I'm running this on a single machine and I have a terabyte of data going into it, if this is my personal computer and I'm running a terabyte of data into this, this is running rather quickly through all 500 iterations. But at a terabyte of data, we're talking something closer to days, week, even with a 3.5 gigahertz machine in 8 cores, it's still going to take a long time to go through a full terabyte of data. And then we want to start looking at putting it into some other framework like Spark or something that will be able to process on there more across multiple processors and multiple computers. And if we scroll all the way down to the bottom, you're going to see here's our square mean error of 0.0088. if we scroll way up, you'll see it kind of oscillates between 0.0888 and 0.0089. It's right around 250 where you start seeing that oscillation where it's really not going anywhere. So we really didn't need to go through a full 500 epochs. If you're retraining this stuff over and over again, it's kind of good to note where that error zone is so you don't have to do all the extra processing. Of course, if you're going to build a model, we want to go ahead and run a prediction on it. So let's go ahead and make our prediction. And remember, we have our training test set and our test set, we have the train X and the train Y for training it, or train predict. And then we have our test X and our test Y going in there. So we can test to see how good it did. And when we come in here, we have, you'll see right here, we go ahead and do our train predict equals model predict train X and test predict model predict test X. Why would we want to run the prediction on train X? Well, it's not 100% on its prediction. We know it has a certain amount of error, and we want to compare the error we have on what we programmed it with the error we get when we run it on new data that's the model's never seen before. And one of the things we can do, we go ahead and invert the predictions. This helps us level it off a little bit more. Get rid of some of our bias. We have train predict equals an NP exponential M1, the train predict, and then train Y equals the exponential M1 for train Y, and then we do again that with test predict and test Y. Again, reformatting the data so that it all matches, and then we want to go ahead and calculate the root mean square error. So we have our train score, which is your math square root times the mean square root error, train Y and train predict. And again, we're just, this is just feeding the data through so we can compare it. And the same thing with the test. And let's take a look at that, because really the code makes sense. If you're going through it line by line, you can see what we're doing. But the answer really helps to zoom in. So we have a train score, which is 2.40 of our root mean square error. And we have a test score of 3.16 of the root mean square error. If these were reversed, if our test score is better than our training score, then we've overtrained. Something's really wrong. At that point, you got to go back and figure out what you did wrong. Because you should never have a better result on your test data than you do on your training data. And that's why we put them both through. That's why we look at the error for both the training and the testing. When you're going out and quoting your publishing this and you're saying, hey, how good is my model? It's the test score that you're showing people. This is what it did on my test data that the model had never seen before. This is how good my model is. And a lot of times you actually want to put together like a little formal code where we actually want to print that out. And if we print that out, you can see down here, test prediction and standard deviation of data set, 3.16 is less than 4.40. I have to go back, and we're up here. If you remember, we did the square means error. This is standard deviation. That's why these numbers are different. It's saying the same thing that we just talked about. 3.16 is less than 4.40. Model is good enough. We're saying, hey, this model is valid. We have a valid model here. So we can go ahead and go with that. And along with putting a formal print out of there, we want to go ahead and plot what's going on. And this, we just want a pretty graph here so that people can see what's going on. When I walk into a meeting and I'm dealing with a number of people, they really don't want these numbers. They don't want to say, hey, standard deviation, unless you know what statistics are. You might be dealing with a number of different departments. Head of sales might not work with standard deviation or have any idea what that really means number-wise. And so at this point, we really want to put it in a graph so we have something to display. And with displaying, you got to remember that we're looking at the data today going into it and what's going to happen tomorrow. So let's take a quick look at this. We're going to go ahead and shift the train predictions for plotting. We have our train predict plot, NP empty like data set, train predict plot, set it up with null values. It's just kind of a weird thing where we're creating the data groups as we like them, and then putting the data in there is what's going on here. So we have our train predict plot, which is going to be our look back, our length, plus look back, we're just is going to equal train predict. So we're creating this. Basically, we're taking this and we're dumping the train predict into it. So now we have our nice train predict plot. And then we have the shift test predictions for the plotting. We're going to continue more of that. Oops, looks like I put it in here double. No, it's just, yeah, they put it in here double. Didn't mean to do that. We really only need to do it once. Oh, here we go. This is where the problem was, is because this is the test predict. So we have our training prediction. We're doing the shift on here. And then the test predict, we're going to look at that. Same thing, we're just creating those two data sets. Test predict plot, length prediction, set up on there. And then we're going to go through the plotting, the original data set, and the predictions. So we have a time axis. Always nice to have your time set on there. Set that to the time array, time axis lap. All this is setting up the time variable for the bottom. And then we have a lot of stuff going on here as far as setting up our figure. Let's go ahead and run that, and then we'll break it down. We have on here our main plot. We have two different plots going on here. The ISPU going up and the data, and the ISPU here with all these different settings on it. And so when we look at this, we have our AX1, that's the main plot. I mean our AX, that's the main plot, and we have our AX1, which is the secondary plot over here. So we're doing a figure PLT, or PLT.figure, and we're going to dump those two graphs on there. And so we take, and if you go through the code piece by piece, which we're not going to do, we're going to do the data set here, exponential, reverse exponential, so that it looks correctly. We're going to label it the original data set. We're going to plot the train predict plot. That's what we just created. We're going to make that orange, and we'll label it train prediction. Test predict plot, we're going to make that red and label it test prediction, and so forth. Set our ticks up. This actually just put ticks, time axis gets its ticks. The little marks there going along the axes, that kind of thing. And let's take a look and see what these graphs look like. And these are just kind of fun. You know, when you show up into a meeting and this is the final output and you say, hey, this is what we're looking at. Here's our original data in blue. Here's our training prediction. You can see that it trains pretty close to what the data is up there. I would also probably put a like a little timestamp and do just right before and right after, where we go from train to test prediction. And you can see with the test prediction, the data comes in red, and then you can also see what the original data set looked like behind it and how it differs. And then we can just isolate that here on the right. That's all this is just the test prediction on the right. And it's, you know, you'll see with the original data set, there's a lot of peaks we're missing and a lot of lows we're missing. But as far as the actual test prediction, it does pretty good. It's pretty right on. You can get a good idea of what to expect for your ISPU. And so from this, we would probably publish it and say, hey, this is what you expect, and this is our this is a range of error. That's the kind of thing I'd put out on a daily basis. Maybe we predict the cells are going to be this, or maybe weekly. So you kind of get you kind of flatten the data coming out, and you say, hey, this is what we're looking at. The big takeaway from this is that we're working with, let me go back up here. Oops, oh, too far. There we go. Is this model here. This is what this is all about. We worked through all of those pieces, all the TensorFlows, and that is to build this sequential model. And we're only putting in the 2 layers. This can get pretty complicated. If you get too complicated, it never verges into a usable model. So if you have like 30 different layers in here, there's a good chance you might crash it, kind of thing. So don't go too haywire on that. And that you kind of learn as you go. Again, it's domain knowledge, and also starting to understand all these different layers and what they mean. The data analytics behind those layers is something that your data analysis professional would come in and say, this is what we want to try. But I tell you, as a data scientist, a lot of these basic setups are common, and I don't know how many times working with somebody and they're like, oh my gosh, if I only did a tangent H instead of a ReLU activation, I worked for 2 weeks to figure that out. Well, as a data science, I can run it through the model in 5 minutes instead of spending 2 weeks doing the math behind it. So that's one of the advantages of data scientists is we do it from programming side, and a data analytics is going to look for it. How does it work in math? And this is really the core right here of TensorFlow and Keras, is being able to build your data model quickly and efficiently. And of course, with any data science, putting out a pretty graph so that your shareholders, again, we want to take and reduce the information down to something people can look at and say, oh, that's what's going on. They can see what's going on as far as the dates and the change in the ISPU.
Now, let's talk a little bit about recurrent neural networks. So neural networks are of different types. We have CNN, we have RNN, ANN, so on. Now, RNN is one type of neural network. RNN stands for recurrent neural network. The networks like CNN and ANN are feed-forward network, which means that the information pretty much only goes from left to right or from front to back, whichever way you call it. Whereas in case of recurrent neural network, there will be some information traveling backwards as well. So that is why it is known as a recurrent neural network. And each of these types have a specific application. So for example, convolutional neural networks or CNN are very good for doing image processing and object detection using for video and images. Whereas recurrent neural networks are pretty good for doing NLP or speech recognition and so on. Okay. So for the next few minutes, we will kind of focus on recurrent neural networks, and we will see an example of how we can use RNN to do a time series analysis. So in a typical neural network, this is how it looks, right? So where you have a neuron and then the inputs are coming to the neuron, and then you have an output which goes to other neurons in the other layers. In case of recurrent neural network, what happens is you have the inputs, let's say at a given point in time, but then a part of the previous output also gets fed in along with the inputs for the given time. Now, this can be a little confusing. So let's see if we can take a little expanded view of this. So this is another view of one single neuron, which is what is known as in an unfolded manner. Okay. So if we are getting inputs or data over a period of time, then this is how the neuron will look. Remember, these are not three neurons. This is one neuron, and it is what is known as, it is shown in a unfolded way. Okay. We have unfolded this single neuron over a period of time. So at a given time, let's say t minus 1, an input of xt minus 1 is fed to the neuron, and it gets an output of yt minus 1. Then the next instant, which is xt at a time t, right? There is an input of xt, and then there is an output of yt. So this is a single neuron, but is displayed in an unfolded way. So this is like expanding it over a period of time. So let's start with this part here. This particular neuron gets an input at an instant t minus 1. Let's say time is equal to t minus 1. It gets an input of xt minus 1, and it gives an output of yt minus 1. Then when we go to the instant t, here it gets an input of xt, and it also additionally gets an input from this previous time frame t minus 1. So this yt minus 1 gets fed here, and that results in yt. All right. Then when we go to the time t plus 1, there is an input of xt minus 1 at that given time, plus the input from the previous time frame, which is a time frame of t. That also gets fed in here, and then we get an output of yt plus 1. Okay. So let me explain once again. This is a single neuron. So these are not three different neurons. A single neuron seen over a period of time from t minus 1 to t plus 1. And unlike a regular feed-forward neuron, which only gets x, in this case, the input is x, and also another input which is coming from the previous time frame, and that is what this loop is. In this, on the left hand side diagram, this loop is indicating that. Okay. So on the right hand side, it is represented in an unfolded way. Okay. So the input, if we take a time frame t, for example, is not only xt, which is the input, which is the normal input at the time frame t, but it is also getting an input from the previous time frame, which is this yt minus 1 is also being fed as an input. That is the key differentiator here. Okay. Similarly, at the instant t plus 1, it is getting a normal input of xt plus 1 plus this yt is actually being fed here, and then the output comes as yt plus 1. Okay, so this is the construct of a recurrent neural network. Now, recurrent neural networks again can be of different subtypes. It can be one-to-one, one-to-many, many-to-one, and many-to-many, depending on what kind of application we want to use. One of the examples is like the stock price. So you're feeding, so there is only one input. Only thing is it is spread over a period of time. So you're feeding the stock price input. That is what comes here as an input. And you get an output, which is again the stock price, which is probably predicted over the next 2 days, 3 days, or 10 days, or whatever. So the number of outputs and inputs is the same. There is only one input. There is only one output. Only thing is it is spread over a time. So variables are not many. Then you have one-to-many. So there is one input, but you're expecting multiple outputs. What is an example of this? Let's say you want to caption an image. So how do you want to do that? What is the input that will go here? It's just an image, which is one input. But what is the output you're looking for? You're looking for a phrase maybe, right? Not just a word, but a phrase. So it's like cat is sitting on a mat, right? So the image is, there is only one image which consists of the cat sitting on a mat, but the output are like maybe 3 or 4 words, which is saying the cat is sitting on a mat. So this is one-to-many, right? Then you can have many-to-one. Examples of this are like you're feeding some text and you want to know the output, whether the text is, what kind of sentiment is expressed by the text. It could be positive, it could be negative. So that's the output you're looking for. So you feed a large number of words, maybe the text may consist of words or lines or whatever. So that is what is the multiple inputs. But the output, all it says is the sentiment is positive. So it is just one output, or the sentiment is negative, just one output, right? So this is many-to-one. Then we have many-to-many. So what is an example of this? Let's say you want to do some translation. So how do you do a translation? You feed in a sentence maybe in a particular language, English, and then you want a sentence actually in another language. So that is like there are multiple inputs. One sentence can consist of multiple words, and the output also is a sentence consisting of multiple words. All right. So how do we implement RNN? This is an example of implementing an RNN for a particular use case. So in our particular example, we have the data about milk production over a few months, and using RNN, we want to predict, because this is time series analysis. So RNN is good to do time series analysis. So using RNN, we want to predict what will be the milk production in the future. So let us see how we can do that. I will first take you quickly through the slides, and then I will actually run this in a Jupyter notebook. The code, I will run it in the Jupyter notebook. So this is how it looks, the code looks. So while this is TensorFlow, you still use the standard Python libraries like NumPy and Pandas and even Matplotlib to do some initial processing, getting the data, processing it, cleaning it, whatever. All that can be still done within the same program. So that's what we're doing here. We're importing some libraries like NumPy and Pandas, and then we read the data file. And if we plot the data, we see here it is the data for the years 1962 to 75, and we can see that there is a certain trend, right? So this is how a typical time series data would look. Again, some of you, if you're not familiar with time series and time series analysis and so on, I would recommend you to go through some videos around that, which will make it easy to understand this. So this is how a typical time series data would look. In this case, it is nothing but there is only one variable, which is milk production, and it is spread across several years. So it's going from 1962 to 75, and that value has been plotted. So if you see, there is a certain kind of a trend here, which is basically going upwards, and there will be some seasonality. So time series data has these 3 components, right? So it will have a trend, it will have a seasonality, and then it will have some randomness. So that's what this graph is showing. And now if we want to perform analysis on this, time series analysis on this, first thing we need to do is split the data into train and test. And in this case, we will just use a straightforward method, which is taking the data for the first 13 years. So the idea here is we need to train our model, right? This is time series data. So and we want to predict for the future. So the way we need to use this is we have to take the data for a certain period of time and train our model. And then we use a part of the known data so that we can then ask our model to predict for that duration and compare it with the known information. So what do we mean by that? So here, if you see this data, I will show you in the notebook as well, Jupyter notebook as well. This has 13 years of data. So what we are doing is we are taking the first 12 years and using that as our training set, right? So 12 years we are doing, and this has about, I think, 14 years of data. So we are taking 13 years of data for training purpose, and then we are using the last 1 year, remaining 1 year of data for testing purpose. Because here what we can do is this 1 year data, we know the values, right? Because if we want to compare the accuracy or anything like that, we need to know the values. So in this case, we know the values of this one particular year. So we will use that. But at the same time, we train the model for 13 years of data. And for the 14th year, we will ask our model to predict and then compare it with this known value so that we know how accurate our model is. I hope that makes sense. Okay. So that's what we are doing here. 156 is nothing but 12 into 13. On a monthly basis, we get the data. The next step is to scale the data. This is all regular data manipulation, data munching activity. And then you split it. You are basically assigning the train and test data to the scaled variables. And then you need to read the data in batches. So it is very important, as I mentioned earlier also, that instead of reading the entire data in one shot, you feed the data in batches. So in order to do that, we are writing a function for that. That's all we are doing here. So that is still here what we have done is regular Python programming. There is no TensorFlow as of now here. Okay, so far what we have done is preparation, data munching. Now what we are doing is actually training our model. So this is where TensorFlow now comes into picture. So we are importing, first step is to import the TensorFlow library. So this is how you do it, import TensorFlow STF. And then you can define some variables or constants, whichever way. Now here, of course, there are a couple of ways of doing it. You can create them as TensorFlow nodes, but that is a little bit of an overhead. We will just use the regular Python variables or constants. So here I am creating regular Python variables and I'm saying number of inputs is 1. So instead of hard coding, I'm just storing them as variables. So this is number of inputs is 1, number of time steps is 12, number of neurons is 100 and so on, right? And then learning rate is 0.03 and number of iterations we are saying is 4000. Then we create placeholders. Now we will be storing the independent variables in X and the dependent variables in Y, and this we will read from an external file. Remember, I told you placeholders are used for getting data from outside and then feeding it to our model. So that's the reason we have two placeholders, one for reading the X values and another for reading the Y values. In this step, we are only just creating the nodes, right? So this is just creating the graph. And similarly, we are mentioning what is the loss function and what is the optimizer and how to run the optimizer. And once that is done, you are initializing the variables and then you're creating a saver variable or a saver instance. So saver is basically nothing but in machine learning, you can train your model and you can save it for later use. So that's where the saving comes into play. We will see how to use that as well. And then the last step is to create your session and run this graph, right? So we are initializing the variables. Remember this, we run init. So which is nothing but this one. So we are initializing the variables, whatever are there. Instead of hard coding, remember in earlier case we were hard coding how many iterations. So here we are saying for the given number of iterations which are stored in this, maybe how many iterations we said is, what is the value of iterations? This is training iterations is 4000. So we specify that based on the number of training iterations. Next batch will basically fetch the data and then we run the session. We are basically saying train is the node which we will run in the session, and this will basically train our model, and this is more for printing. Every 100 times you print it. That's all. There's nothing more to it. So for example, the output would look somewhat like this. This is for 0, this for 100, next for 200 and so on. Okay. And then you save the model. You remember saver we created. So you save the model for later use. So this is our test data. Remember, we are doing this on training data, right? So once the training is done, we then try to create the inference on the test data so that we can compare how accurate this is. Right. So this is how the test set would look, and then we will basically restore this model, okay, because in the previous slide we created the model and we stored it. So now we have to restore the model and then run our test data against it and see what are the values that are predicted, what are the Y values, and then compare with X to see the accuracy. So train seed is what we are seeing here. So that is what will have the predicted values, and these predicted values, what we want to do do is we want to create an additional column, because remember, we need to compare, because we want to find out the accuracy of this model. So we need to compare the predicted values with the actual value. So what we are doing here is adding another column called generated and assign a value to that. All right, so this is the result of the prediction. And then if we need to reshape, because we have to show this in the form of monthly results. So that's what we are doing here. And once we generate the results and then display it, we can actually see it month wise here, and the actual and the generated values. Okay, so we create a data frame which is a combination of the actual values and the predicted values from the test set. And then we can plot to see how the trend is. As you can see, pretty much the actual value is in blue color and the generated or predicted value, the curve is in yellow color. The trend is maintained. So it will probably, it's not 100% accurate, but the trend is maintained. All right, so let's do one thing. Let's go into the Jupyter notebook and take a look at how this works in TensorFlow environment. Actually, the code, I will walk you through the code. This is my Jupyter notebook, and the data is taken from this particular link. In case you're interested, you can download it from there. And this is the data for the years 1962 to 75. The first thing we do is import these libraries, because before we start with the actual TensorFlow activity, we need to prepare the data and so on. So for that, you can use your regular Python libraries, which are like NumPy, Pandas, and so on. So that's what we are doing here. And then we read the data using Pandas into a data frame. So this is a data frame, milk is a data frame, and we will do some quick exploratory analysis just to see how our data is looking. Initial 5 records that we'll get, 1, 2, 3, 4, 5, that is the head. So it goes from 1962 January to 1962 May. Once we rechange, or basically we need to split this into month specifically separately. So that's what we are doing here, date to time. So we kind of do a little bit of a reindexing, and then if we plot this, this is how the data look. As you can see, there is a clear upward trend, and there is some seasonality and so on. But anyway, we will not break that up into those components. We will just use RNN to predict and test. Okay, so the next thing is to check some, if we can run like an info, it will tell us what is the information about this data set. So let us just run that. Okay, so it is just telling us how many total columns and what is the size of the file and so on and so forth. Again, in case you're interested in doing some exploratory analysis. So what we'll do next is we will take the 13 years of data for our training data set. So what are we going to do now? Let me step back. So what have we seen here? We have seen that there are 168 records, so which is nothing but 14 years of data. We now have to split this into our training and test data set. So how do we do that? I think in case of time series, we cannot do it like 80-20 like we do in normal splitting in normal machine learning process. Here it is time series data. So what we are going to do is we will take out of this 14 years, we will take the first 13 years of data and we will use that for training, and then we will test it with the last, which is the 14th year data. We will use it for testing. Okay, so that's what we are going to do here. So let's split that. So training set will consist of my 156 records, which is nothing but 13 into 12, right? My 13 years of data I'm taking for training, and then my test set will consist of the bottom 12 observations, which is last 1 year of data, which is the 14th year. Okay, so that's now done. Training and test splitting is done. The next step is to do some normalizing, which is basically we'll use our scaling, rather we will use min-max scaler, and we will just scale the data. And now we do it for both test as well as train. Now we are ready to create our RNN model. But before that, one quick thing, in order to fetch the data, we have to create a function. So that's what we are doing here. We create a function called next batch, and how you want to fetch the steps, they are all defined as our constants, if you remember, and that's what this function is all about. So we define that function. We will be calling that in our training method. All right, so from here onwards up to there, we are done with the preparation of the data and whatever functions or whatever are required. From here onwards is where the TensorFlow part starts. So the first thing we do is import the TensorFlow library. Typically, this is a very standard way of importing importing the library, we say import TensorFlow as TF. Now TF is nothing but a name, so you can change it to TF1 or ABC or XYZ, whatever. So this part you can change, but by and large everybody uses this, so I would rather recommend you also use the same syntax. So you say import TensorFlow as TF, so it's very easy for others to understand as well. And then you declare or define a bunch of constants. That's what we are doing here. Like for example, the number of time steps, in this case it is 12, number of neurons, there are 100, number of outputs, it is only 1, and so on, right? And then the learning rate and all that, we are declaring or defining those variables in this particular block. Next is to create placeholders. You remember the placeholders are used for feeding the data. So we have X and Y. X is for the input, which is the independent variable, and Y is the output, which is the dependent variable. And in our case, these are not different characteristics or features, but it is the same one feature or one variable, but it is over a period of time. So that's the only difference. So that's what we are doing here. And now we need to create our network, right? The neural network. So in our case, we said we will create a RNN layer. Now there are different ways or different formats of RNN, which is probably not in scope of this module. So for now, we will just assume we are creating one RNN layer, and one type of RNN is GRU cell. So we will use GRU cell, and we use this APIs for creating our layer. So each cell will be with an output projection wrapper. There is a need for doing that. And again, the details of this we will probably do in another video where we talk in detail about RNN. So for now, we are creating a GRU cell with the wrapper, and the syntax for creating the GRU cell is like this. The number of units, which we said there should be 100 neurons. What will be the activation function? In this case, it is ReLU, and then number of outputs. In our case, it is only 1. Okay, so we create the cell here. Okay, then we got the GRU cell, and then we say what is our output, which is nothing but we get the outputs and the states and their states, and which is the way we get that is tf.nnn.dynamic_rnn. So if we call this and we pass the cell and the data, which is basically in placeholder. So again, remember, all we are doing here is we are creating just the nodes for the graph. So nothing is actually getting executed from a TensorFlow perspective. Okay. All right. So once that is done, now we need to pass this, calculate the outputs and the states using the dynamic_rnn method, and we pass the cell as a parameter and then the x values as a parameter. And if we run that, we will have the outputs and the states. And this is where we actually run the training method. So, or create, not really run the training method, but we create the nodes for the training and the optimizer. Then we have the initialization of the variables, and we save this model. We create a saver object just to save the model, because we will then restore it and run it to do our predictions. So this is what we will do here. So that is another node, and this is where we actually create a session and run the training. Okay, so let's go ahead and do that. That will take a little while because we said 4,000 iterations. So we will allow it to finish. We will probably come back once the training is completed. All right, so the training is done. Now let's go and run this on the test data. So let's just quickly take a look at the test data set. So this is our 1 year data for the year of 1975. So if we see this is from January, February, and so on. And we will pass this to our model. So what are we doing here? We are restoring the model here, for example, right? This is the path that we have given when we were saving the model. Let's go back once and show you. Let me show you where we did the saving of the model. Yes, so we saved the model here. So that again, we will restore that, and we will use that to run it on our test data and see how well it predicts. So let's go ahead and run this. And this is just 12 records, so this will not take time. Remember, I told you training is what takes a lot of time. The regular inference, this is called inference, doesn't take much time, right? So it just depends on how much data there were only 12 records here, so it was very quick. But in training, what we do, we pass this multiple times. There are iterations, 4,000 iterations we did, for example. So that takes longer. And in general, in machine learning, deep learning, training is what takes the maximum amount of time. All right, so let's go ahead and see the results. We will, in order to plot it, we will have to kind of adjust the format of the results. Otherwise, we will not be able to see it in a proper way. And then we will, so this is our, so what we have done is we created a data frame which consists of the predicted value and the actual value. So this is the data frame. So this is the actual value, this 834, 782 and so on. This is what our model has predicted. So it may not be so easy to see in a tabular format. So let's go ahead and plot it so that we can compare these two. So when we plot it, you will see that the trend is more or less maintained, right? So we go from the blue color is the actual values, and the yellow color or the orange color, whatever is it, is the one which is generated by our model. So it pretty much is following the actual trend. So not bad for such a quick iteration and training.
This tutorial is about object detection. We will walk you through a TensorFlow code using which we will do object detection in images. We will tell you what are the libraries that are required, a little bit about the Coco dataset, and then we will show you the implementation code itself, a demo of the code. Alright, so let's get started. So what is the TensorFlow Object Detection API? This is an open source framework which is actually provided by the TensorFlow team, and there are trained models available, and the sample code is also available which we can use in order to easily detect objects in images and videos. This is pretty robust and can detect objects fairly quickly, and this is very easy for people to use as well. People with very less or no knowledge of machine learning or deep learning can also, with a little bit of Python programming knowledge, can actually use this API, this library, to build object detection applications. This is a list of libraries that are required, and they have been shown in the code as well. The exact purpose of each of this library, why it is required, is out of the scope of this tutorial, but we will see in the code as we walk through some of these libraries how and why they are used. The Coco data set, Coco stands for Common Objects in Context. So this data set consists of 300,000 images of 90 most commonly found objects like chairs and tables and so on and so forth. So this model has been trained, or in fact a set of models have been trained on this data set, and this is pretty good to detect the most common objects in the images and videos. So with that, let's get into the code. Alright, so the first part is to import all these libraries, and this we have shown you in the slides as well. Again, a large part of this will be for doing some helper functions and maybe for visualizing the images and so on and so forth. So that's the reason they are required. As I said, the exact details of each and every library probably is out of scope, but these are needed. So as a first step, maybe you just go ahead and include these libraries and run the code, and maybe at a later point we can discuss what each of these libraries does. Now this will work with TensorFlow version higher than 1.4. So if you are having TensorFlow version below 1.4, you may have to upgrade to a higher version. So let me go ahead and execute the cell, and we also need this line of code to make sure that once we run this object detection, the labeled images are displayed within this notebook, and many of you by now must be familiar with this. And we will import a few utility libraries, and you will see that we will be using some of these for visualization purpose. So once the objects are detected, we need to display the information, what that object is, and then what percentage of confidence the model has. So all these details, that's the utility functions that are stored here. And then the next part is to prepare the model. As I mentioned, we will be using an existing trained model, The TensorFlow team has actually provided these models. The one that we will be using is SSD with the mobile net, but you can actually use any one of the ones that are listed in this URL. Let me just quickly take you through this URL. These are a bunch of models, trained models that are readily available for anybody to use. It is open source. And let me scroll down. The only thing is that if there are some of them where the accuracy is much higher but they take longer, and there are some where the accuracy is not so high and they are much faster. So they are faster but the accuracy may not be that very high. So you can play around with some of these, and we in this particular exercise or in this particular tutorial we are using this SSD model, which is SSD MobileNet version 1. So that's the model that we'll be using. So in this cell we are primarily creating a bunch of variables with the various, for example, the name of the model, the path, and so on and so forth, so that we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, and then you kind of extract or you freeze the model. So that's the reason they are called frozen models, so that others can just use this without any further training. So this is where we download and extract our model locally. So this will take a little while. Let me see if I can wait or maybe pause the video and come back once it is done. Might take a little while. Let's see if it completes. I have a pretty high speed network, but even then it takes some time, so that's good. But this part is over. Now let us see this part, and yes, both are done. So once that is done, we need to load some label mapping. Basically what this will do is your model, as you may be aware by now, if you do some classification, the model will actually not give any output as a text. It will give some numbers. So if there are 5 classes, it will say, okay, this belongs to model class 1 or 2 or 3 or 5 and so on, the numbers. Now each of these will obviously, the numbers will not make any sense to the outside world, so we need to do some small mapping. So in this case, let's say 1 may be a chair, 2 may be a table, 3 may be a balloon, and so on. So that kind of number to text mapping we need to do, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, so that the NumPy array is what gets processed and used by the model to do the detection part of it. So that is what this method is all about. So we will be later on we will be calling that function. And next is preparation for detection. So here we are basically telling where the images are stored and how many images, or what is the naming convention or format of the images. Now if you want, you can modify this code. For example, currently I have test_images as my folder. So let me go and show this to you. So this is under my object detection folder. I have another subfolder where I'm storing my images, which is text_images. Now you can rename this folder and give some other name, and then in your code you can probably give that particular name for the subfolder. Similarly, the format of these files, what is the name and format of these files? Here it is in a very simple format, which is the names of the files are like beach 1, beach 2, beach 3, and so on. So I have taken beach as the theme. So I have images which are related to beaches. So this is beach 1, beach 2, and then beach 3. I have a few others, but we will use these 3 for our demo. And so that's what I'm saying here. The name of the images will be beach something.jpg, which is JPEG format, and in this curly braces basically we will be filled with either 1, 2, or 3 based on in this particular for loop. Okay, so that is what this is doing. Alright, so the next step is to run inference on these images in a loop, and what we are basically doing here is getting these images one by one and then running through the model to find out what are the objects that can be detected, and then against each of the object a box will be drawn and it will be labeled with the name and the percentage of accuracy or confidence that the model detects these objects. Okay, so that is the function here, and so let me just run that piece of code. And here is basically where we are calling this function. So we are loading this images, and then we are calling this function for each image, and then we are displaying this using the matplotlib library. So let's run this. It will take one image at a time and then detect the images. Now the beauty is that the same format of the code can be used for doing object detection in a video. So we have another video for doing object detection in a video. So most of the code out there will be reused from here, and the only thing is that instead of reading the images from the local storage, we read the frames from the video, and there is a neat little video reader that is available, and it will be shown in the other video. And frame by frame we read the video and then pass on to this function, and it will act as if each of these frames is an image, and then it will do the same object detection on the entire video. So that's in a separate video, just look out for that. And actually the information about that is provided in the cards, the I symbol. So that's the video object detection in video. That's the separate tutorial. All right, so now that we have all the pieces together, the last cell is where the whole action takes place. So let's run this and see how it looks. So it will take probably a little while, and there are about 3 images. Let's see what it detects. There we go. So good. So the first one, it has detected a person, and that too with 97% accuracy, which is I think pretty good. Okay, and then the next image, it detects umbrella and chair. There are a few other objects, but it's not able to detect. It has detected umbrella with 63% accuracy, or confidence rather, and the chair with 58%. Again, not bad. Then let's see the next image. So here, these are actually balloons, hot air balloons, but the model thinks it is a kite, which is probably not that bad. It sees there is something in the sky, and therefore probably it thinks it is a kite, and it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images. And in this video, I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries. For example, NumPy, we need image.io, datetime, and pill, and so on and so forth, and of course matplotlib. So we import all these libraries, and then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. All right. And then these are some warnings. We can just ignore them. So if I run this code once again, it will go away. All right. And then here onwards, we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one, because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on, so you can probably play around with these other models. Okay, so we will be using that model. So this piece of code, this line is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build a model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. So things like that. So this mapping is done in this next cell. Alright, so let's keep moving. And then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images. So we are actually going to reuse, because video is nothing but it consists of frames, which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is here once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code what we are doing basically is there are a few lines of code. What they do is basically once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image.io. So we can read and write videos using that, and the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like cars. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that, but let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and no, actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it and then annotating and then writing it back. So you will see that we will have a video file named something like this, traffic_annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video_writer.close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done. The hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. We'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic underscore annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay. So I think because of the board on top, it somehow thinks there is a truck. Let's play some more and see if it detects anything else. So this is again a car, looks like. So let us, yeah. So this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our application will, our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so yeah, so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat. The extension, it will automatically up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video reader, video underscore reader, has a neat little feature or interface whereby you can say for frame in video underscore reader. So it will basically provide frame by frame. So you are in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell again. It will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. Let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is a cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit that's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here it is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video. Okay, so close this. So that's pretty much it. Thank you very much for watching this video.
Hey there learner, Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
In this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little MNIST database is a nice little database that has images of handwritten digits nicely formatted, because very often in deep learning and neural networks we end up spending a lot of time in preparing the data for training, and with MNIST database we can avoid that. You already have the data in the right format which can be directly used for training, and MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation. And all of them are labeled. So you have the images and their label. And these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database. And the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information. And the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but, these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28. So there are 784 pixels. So pixel number 1 starts here. It goes all the way up to 28. Then 29 starts here and goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TensorFlow is available as an object in the name of TF, and then you can run its methods and accesses its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use a pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay, so in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0, this is at position 1, position 2, and so on and so forth. Let's say this is position 7, then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay, so one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates. So based on which digit is 1, we know what is the label. So in this case, the 8th position is 1, therefore we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay, so that is the significance of this one hot true. All right, and then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values, so you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set there are 10,000, and then validation there are 5,000. So altogether there are 70,000 images. All right, so let's move on, and we can view the actual image by using the matplotlib library. And this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values, so of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between is, it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code. And the first step is to create some placeholders, and then you create a model. In this case, we will use the softmax model, one of the simplest ones. And placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then, of course, you will have variables, which are remember, these are your weights and biases. So in our case, there are 10 neurons, and each neuron actually has 784 because each neuron takes all the inputs. If we go back to our slide here, actually every neuron takes all the 784 inputs. Right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 708. So each of these inputs needs to be multiplied with a weight, and that's what we are talking about here. So this is a matrix of 784 values for each of the neurons, and so it is like a 10 by 784 matrix because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned bias is only 1 per neuron. So it is not 1 per input, unlike the weights. So therefore, there are only 10 biases because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of three different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables or at the most variables and constants. But in TensorFlow, you have three different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication or matmul function. So that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is in very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use, and reduce mean is what is like the mechanism whereby which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low, because it will, in that case, it will take very long. So you define the optimizer, and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment. Or you can go for any cloud service, like for example Google Cloud, Amazon, or Cloud Labs. Any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. We have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data. And we need to adjust the data in such a way that the one hot is encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, the 784 is nothing but the 28 by 28, 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values are, so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5,000, right? So 5,000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50? Again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again, we can check what is the maximum value and what is the minimum value of these pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here, as we have seen in the slides. So we create one placeholder and we create 2 variables, which is for the weights and biases. These 2 variables are actually matrices. So each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron. There are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron, so there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of X into W, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is our The y value is basically the label value. So this is another placeholder. We had x as one placeholder and y underscore true as a second placeholder, and this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right. Then we have cross entropy, which is nothing but the loss function. And we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this. But even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use a softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything, but you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session. Right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have w is a variable and B is a variable. So any variables that we created, you have to run this code. You have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500 depending on the size of your system and so on and so forth. So in this case, we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this. But in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose. And then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnest function here. So we are saying mnest train.next batch. Right? So this is the advantage of using MNIST database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using MNIST database, and that's why we use this for the initial learning phase. Okay. So when we say fetch, what it will do is it will fetch the images into X and the labels into Y. And then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously, it will not be 100% accurate. Okay. So once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on. But it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data and you're trying to find out what is the actual value and what is the predicted value and seeing whether they are equal or not, tf.equal, right? And how many of them are correct and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy, and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell. So we will have to just run it in one shot. It may take a little while. Let us see. and not bad. So it has finished the 1000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay, now which is pretty good for such a short exercise. Within such a short time we got 90% accuracy. However, in real life this is probably not sufficient, so there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%.
Hey there learner, Simplilearn brings you Master's Program in Artificial Intelligence created in collaboration with IBM. To learn more about this course, you can find the course link in the description box below.
We're going to dive right into what is Keras. We'll also go all the way through this into a couple of tutorials, because that's where you really learn a lot, is when you roll up your sleeves. So when we talk about what is Keras, Keras is a high-level deep learning API written in Python for easy implementation of neural networks. It uses deep learning frameworks such as TensorFlow, Pytorch, etc. as backend to make computation faster. And this is really nice because as a programmer, there is so much stuff out there and it's evolving so fast, it can get confusing. And having some kind of high-level order in there where you can actually view it and easily program these different neural networks is really powerful. It's really powerful to have something out really quick and also be able to start testing your models and seeing where you're going. So Keras works by using complex deep learning frameworks such as TensorFlow, Pytorch, MLPlaid, etc. as a backend for fast computation, while providing a user-friendly and easy-to-learn front-end. And you can see here we have the Keras API specifications, and under that you'd have like TF Keras for TensorFlow, Thano Keras, and so on. And then you have your TensorFlow workflow that this is all sitting on top of. And this is, like I said, it organizes everything. The heavy lifting is still done by TensorFlow or whatever underlying package you put in there. And this is really nice because you don't have to dig as deeply into the heavy end stuff while still having a very robust package you can get up and running rather quickly. And it doesn't distract from the processing time because all the heavy lifting is done by packages like TensorFlow. This is the organization on top of it. So the working principle of Keras. The working principle of Keras is Keras uses computational graphs to express and evaluate mathematical expressions. And you can see here we put them in blue. They have the expression expressing complex problems as a combination of simple mathematical operators, where we have like the percentage, or in this case in Python that's usually your remainder, or multiplication. You might have the operator of x to the power of 0.3. And it uses useful for calculating derivatives by using backpropagation. So if we're doing with neural networks, when we send the error back up to figure out how to change it, this makes it really easy to do that without really not banging your head and having to hand write everything. It's easier to implement distributed computation, and for solving complex problems, specify input and outputs and make sure all nodes are connected. And so this is really nice as you come in through, is that as your layers are going in there, you can get some very complicated different setups nowadays, which we'll look at in just a second. And this just makes it really easy to start spinning this stuff up and trying out the different models. So when we look at Keras models, Keras model, we have a sequential model. Sequential model is a linear stack of layers where the previous layer leads into the next layer. And this, if you've done anything else, even like the sklearn with their neural networks and propagation and any of these setups, this should look familiar. You should have your input layer, it goes into your layer 1, layer 2, and then to the output layer. And it's useful for simple classifier or decoder models. And you can see down here we have the model equals a Keras sequential, and this is the actual code. You can see how easy it is. We have a layer that's dense, your layer 1. As an activation, they're using the ReLU in this particular example. And then you have your name layer 1, layer dense ReLU, name layer 2, and so forth. And they just feed right into each other, so it's really easy just to stack them, as you can see here, and it automatically takes care of everything else for you. And then there's a functional model. And this is really where things are at. This is new. Make sure you update your Keras, or you'll find yourself running this, doing the functional model. You'll run into an error code because this is a fairly new release. And it uses multi-input and multi-output model. The complex model, which forks into 2 or more branches. And you can see here we have our image inputs equals your Keras input shape equals 32 by 32 by 3. You have your dense layers, dense 64 activation ReLU. This should look similar to what you already saw before, but if you look at the graph on the right, it's going to be a lot easier to see what's going on. You have 2 different inputs. And one way you could think of this is maybe one of those is a small image and one of those is a full-sized image. And that feedback goes into, you might feed both of them into one node because it's looking for one thing, and then only into one node for the other one. And so you can start to get kind of an idea that there's a lot of use for this kind of split and this kind of setup. We have multiple information coming in, but the information's very different even though it overlaps. And you don't want it to send it through the same neural network. And they're finding that this trains faster and also has a better result depending on how you split the data up and how you fork the models coming down. And so in here we do have the 2 complex models coming in. We have our image inputs, which is a 32 by 32 by 3, or 3 channels, or 4 if you're having an alpha channel. You have your dense, your layers, dense is 64 activation using the ReLU, very common. X equals dense inputs, X layers dense X64 activation equals ReLU, X outputs equals layers dense 10X, model equals Keras, model inputs equals inputs, outputs equals outputs, name equals minced model. So we add a little name on there. And again, this is this kind of split here. This is setting us up to have the input go into different areas. So if you're already looking at Keras, you probably already have this answer. What are neural networks? But it's always good to get on the same page, and for those people who don't fully understand neural networks, to dive into them a little bit or do a quick overview. Neural networks are deep learning algorithms modeled after the human brain. They use multiple neurons, which are mathematical operations, to break down and solve complex mathematical problems. And so just like the neuron, one neuron fires in and it fires out to all these other neurons, or nodes as we call them, and eventually they all come down to your output layer. And you can see here we have the really standard graph input layer, a hidden layer, and an output layer. One of the biggest parts of any data processing is your data pre-processing. So we always have to touch base on that. With a neural network, like many of these models, they're kind of, when you first start using them, they're like a black box. You put your data in, you train it, and you test it and see how good it was. And you have to pre-process that data because bad data in is bad outputs. So in data pre-processing, we will create our own data examples set with Keras. The data consists of a clinical trial conducted on 2,100 patients, ranging from ages 13 to 100, with the patients under 65 and the other half over 65 years of age. We want to find the possibility of a patient experiencing side effects due to their age. And you can think of this in today's world with COVID, what's going to happen on there. And we're going to go ahead and do an example of that in our live hands-on. Like I said, most of this you really need to have hands-on to understand. So let's go ahead and bring up our Anaconda, and I'll open that up and open up a Jupyter notebook for doing the Python code in. Now, if you're not familiar with those, you can use pretty much any of your setups. I just like those for doing demos and showing people, especially shareholders. It really helps because it's a nice visual. So let me go ahead and flip over to our Anaconda. And the Anaconda has a lot of cool tools. They just added Datalore and IBM Watson Studio Cloud into the Anaconda framework. But we'll be in the Jupyter Lab or Jupyter Notebook. I'm going to do Jupyter Notebook for this because I use the lab for like large projects with multiple pieces because it has multiple tabs. Where the notebook will work fine for what we're doing. And this opens up in our browser window because that's how Jupyter Notebook is set to run. And we'll go under New, create a new Python 3, and it creates an untitled Python. We'll go ahead and give this a title, and we'll just call this Keras tutorial. And let's change that to a capital. There we go. We'll go ahead and just rename that. And the first thing we want to go ahead and do is get some pre-processing tools involved. And so we need to go ahead and import some stuff for that, like our NumPy, do some random number generation. I mentioned sklearn, or your scikit. If you're installing sklearn, the sklearn stuff, it's scikit you want to look up. That should be a tool of anybody who is doing data science. If you're not familiar with the sklearn toolkit, it's huge, but there's so many things in there that we always go back to. And we want to go ahead and create some train labels and train samples for training our data. And then just a note of what we're actually doing in here. Let me go ahead and change this. This is kind of a fun thing you can do. We can change the code to Markdown. And then Markdown code is nice for doing examples once you've already built this. Our example data, we're going to do experimental. There we go. Experimental drug was tested on 2,100 individuals between 13 to 100 years of age. Half the participants are under 65, and 95% of participants are under 65. Experienced no side effects, while 95% of participants over 65 experienced side effects. So that's kind of where we're starting at. And this is just a real quick example, because we're going to do another one with a little bit more complicated information. And so we want to go ahead and generate our setup. So we want to do for I in range, and we want to go ahead and create, if you look here, we have random integers, train the labels, append. So we're just creating some random data. And then we go ahead and just run that. And so once we've created our random data, and I mean, you can certainly ask for a copy of the code from Simplilearn. They'll send you a copy of this, or you can zoom in on the video and see how we went ahead and did our train samples append. And we're just using this. I do this kind of stuff all the time. I was running a thing on that had to do with errors following a bell-shaped curve on a standard distribution error. And so what do? I generate the data on a standard distribution error to see what it looks like and how my code processes it, since that was the baseline I was looking for. In this, we're just doing generating random data for our setup on here. And we could actually go in, print some of the data up. Let's just do this, print. We'll do train samples, and we'll just do the first 5 pieces of data in there to see what that looks like. And you can see the first 5 pieces of data in our train samples is 49, 85, 41, 68, 19. Just random numbers generated in there. That's all that is. And we generated significantly more than that. Let's see, 50 up here, 1,000. Yeah, so there's 1,000 here. 1,000 numbers we generated. And we could also, if we wanted to find that out, we could do a quick print the length of it. And so, or you could do a shape kind of thing, and if you're using NumPy, although the link for this is just fine. And there we go, it's actually 2,100, like we said in the demo setup in there. And then we want to go ahead and take our labels. Oh, that was our train labels. We also did samples, didn't we? So we could also print, do the same thing. Oh, labels. And let's change this to labels. And labels. And run that just to double check, and sure enough we have 2,100, and they're labeled 10, 10, 10. I guess that's if they have symptoms or not. 1 symptoms, 0 none. And so we want to go ahead and take our train labels and we'll convert it into a NumPy array, and the same thing with our samples. And let's go ahead and run that. And we also shuffle. This is just a neat feature you can do in NumPy right here. Put my drawing thing on, which I didn't have on earlier. I can take the data and I can shuffle it. So we have it just randomizes it. That's all that's doing. We've already randomized it, so it's kind of an overkill. It's not really necessary. But if you're doing a larger package where the data is coming in, and a lot of times it's organized somehow, and you want to randomize it just to make sure that the input doesn't follow a certain pattern that might create a bias in your model. And we go ahead and create a scalar. The scalar range, minimum max scalar, feature range 0 to 1. Then we go ahead and scale the scaled trained samples. So we're going to go ahead and fit and transform the data so it's nice and scaled. And that is the age. So you can see up here we have 49, 85, 41. We're just moving that so it's going to be between 0 and 1. And so this is true with any of your neural networks. You really want to convert the data to 0 and 1, otherwise you create a bias. So if you have like 100 creates a bias versus the math behind it gets really complicated. If you actually start multiplying stuff, because there's a lot of multiplication and addition going on in there, that higher end value will eventually multiply down, and it will have a huge bias as to how the model fits it, and then it will not fit as well. And then one of the fun things we can do in Jupyter Notebook is that if you have a variable and you're not doing anything with it, and it's the last one on the line, it will automatically print. And we're just going to look at the first 5 samples on here. And so it's going to print the first 5 samples. And you can see, here we go, 0.9195, 0.791. So everything's between 0 and 1. And that just shows us that we scaled it properly and it looks good. It really helps a lot to do these kind of print-ups halfway through. You never know what's going to go on there. I don't know how many times I've gotten down and found out that the data sent to me that I thought was scaled was not. And then I have to go back and track it down and figure it out on there. So let's go ahead and create our artificial neural network. And for doing that, this is where we start diving into TensorFlow and Keras. TensorFlow, if you don't know the history of TensorFlow, it helps to jump into, we'll just use Wikipedia. Be careful, don't quote Wikipedia on these things because you get in trouble. But it's a good place to start. Back in 2011, Google Brain built Disbelief as a proprietary machine learning setup. TensorFlow became the open source for it. So TensorFlow was a Google product, and then it became open sourced, and now it's just become probably one of the de factos when it comes for neural networks as far as where we're at. So when you see the TensorFlow setup, it's got like a huge following. There are some other setups like the Scikit under the sklearn has their own little neural network. But the TensorFlow is the most robust one out there right now. And Keras sitting on top of it makes it a very powerful tool, so we can leverage both the Keras easiness in which we can build a sequential setup on top of TensorFlow. And so in here we're going to go ahead and do our input of TensorFlow, and then we have the rest of this is all Keras here from number 2 down. We're going to import from TensorFlow the Keras connection, and then you have your TensorFlow Keras models, import sequential. It's a specific kind of model. We'll look at that in just a second. If you remember from the files, that means it goes from one layer to the next layer to the next layer. There's no funky splits or anything like that. And then we have from TensorFlow Keras layers, we're going to import our activation and our dense layer. And we have our optimizer Atom. This is a big thing to be aware of, how you optimize your data. When you first do it, Atom's as good as any. Atom is usually, there's a number of optimizer out there. There's a couple of main ones, but Atom is usually assigned to bigger data. It works fine. Usually the lower data does it just fine, but Atom is probably the mostly used. But there are some more out there, and depending on what you're doing with your layers, your different layers might have different activations on them. And then finally down here you'll see our setup where we want to go ahead and use the metrics. And we're going to use the TensorFlow Keras metrics for categorical cross entropy. so we can see how everything performs when we're done. That's all that is. A lot of times you'll see us go back and forth between TensorFlow, and then Scikit has a lot of really good metrics also for measuring these things. Again, it's the end of the at the end of the story. How good does your model do? And we'll go ahead and load all that, and then comes the fun part. I actually like to spend hours messing with these things. And 4 lines of code. You're like, you're going to spend hours on 4 lines of code? No, we don't spend hours on 4 lines of code. That's not what we're talking about when I say spend hours on 4 lines of code. What we have here, and I'm going to explain that in just a second, we have a model. And it's a sequential model. If you remember correctly, we mentioned the sequential up here where it goes from one layer to the next. And our first layer is going to be your input. It's going to be what they call dense, which is usually it's just dense, and then you have your input and your activation. How many units are coming in? We have 16. What's the shape? What's the activation? And this is where it gets interesting, because we have in here ReLU on 2 of these and softmax activation on 1 of these. There are so many different options for what these mean and how they function. How does the ReLU, how does the softmax function? And they do a lot of different things. We're not going to go into the activations in here. That is what really you spend hours doing, is looking at these different activations. And just some of it is just almost like you're playing with it like an artist. You start getting a feel for like a inverse tangent activation, or the tanh activation. Takes up a huge processing amount, so you don't see it a lot. Yet it comes up with a better solution, especially when you're doing when you're analyzing Word documents and you're tokenizing the words. And so you'll see this shift from one to the other because you're both trying to build a better model. And if you're working on a huge data set, it'll crash the system. It'll just take too long to process. And then you see things like softmax. Softmax generates an interesting setup where a lot of these, when you talk about ReLU, oops, let me do this. ReLU, there we go. ReLU has a setup where if it's less than 0, it's 0, and then it goes up. And then you might have what they call lazy setup, where it has a slight negative to it so that the errors can translate better. Same thing with softmax. It has a slight laziness to it so that errors translate better. All these little details make a huge difference on your model. So one of the really cool things about data science that I like is you build your what they call you build to fail. And it's an interesting design setup. Oops, I forgot the end of my code here. The concept of build to fail is you want the model as a whole to work, so you can test your model out. So that you can do, you can get to the end and you can do your, let's see, where was it? Overshot down here. You can test out the quality of your setup on there. And see, where did I do my TensorFlow? Oh, here we go. It was right above me. There we go. We start doing your cross entropy and stuff like that. Is you need a full functional set of code so that when you run it, you can then test your model out and say, hey, it's either this model works better than this model, and this is why. And then you can start swapping in these models. And so when I say I spend a huge amount of time on pre-processing data, it's probably 80% of your programming time. Well, between those two, it's like 80-20. You'll spend a lot of time on the models. Once you get the model down, once you get the whole code and the flow down set, depending on your data, your models get more and more robust as you start experimenting with different inputs, different data streams, and all kinds of things. And we can do a simple model summary here. Here's our sequential, here's our layer, our output, our parameter. This is one of the nice things about Keras is you can see right here, here's our sequential 1 model. Boom, 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 boom. Everything's set and clear and easy to read. So once we have our model built, the next thing we're going to want to do is we're going to go ahead and train that model. And so the next step is, of course, model training. And when we come in here, this a lot of times is just paired with the model because it's so straightforward. It's nice to print out the model setup so you can have a tracking. But here's our model. The keyword in Keras is compile, optimizer atom, learning rate, another term right there that we're just skipping right over that really becomes the meat of the setup is your learning rate. So whoops, I forgot that I had an arrow, but I'll just underline it. A lot of times the learning rate set to 0.01. Depending on what you're doing, this learning rate can overfit and underfit. So you'd want to look up. I know we have a number of tutorials out on overfitting and underfitting that are really worth reading once you get to that point and understanding. And we have our loss, sparse categorical cross entropy. So this is going to tell Keras how far to go until it stops. And then we're looking for metrics of accuracy. So we'll go ahead and run that. And now that we've compiled our model, we want to go ahead and run it, fit it. So here's our model fit. We have our scaled train samples, our train labels, our validation split. In this case, we're going to use 10% of the data for validation. Batch size, another number you kind of play with. Not a huge difference as far as how it works, but it does affect how long it takes to run, and it can also affect the bias a little bit. Most of the time, though, a batch size is between 10 to 100, depending on just how much data you're processing in there. We want to go ahead and shuffle it. We're going to go through 30 epochs and put a verbose of 2. Let me just go ahead and run this. And you can see right here, here's our epoch, here's our training, here's our loss. Now, if you remember correctly up here, we set the loss. Let's see, where was it? Compiled our data. There we go, loss. So it's looking at the sparse categorical cross entropy. This tells us that as it goes, how much does the error go down? Is the best way to look at that. And you can see here, the lower the number, the better. It just keeps going down. And vice versa, accuracy we want. Let's see, where's my accuracy? Value accuracy at the end. And you can see 0.619, 0.69, 0.74, it's going up. We want the accuracy, would be ideal if it made it all the way to 1. But we also, the loss is more important because it's a balance. You can have 100% accuracy and your model doesn't work because it's overfitted. Again, you want to look up overfitting and underfitting models. And we went ahead and went through 30 epochs. It's always fun to kind of watch your code going. To be honest, I usually, the first time I run it, I'm like, oh, that's cool, I get to see what it does. And after the second time of running it, I'm like, I like to just not see that. And you can repress those, of course, in your code. Repress the warnings in the printing. And so the next step is going to be building a test set and predicting it now. So here we go. We want to go ahead and build our test set. And we have, just like we did our training set, a lot of times you just split your initial set up. But we'll go ahead and do a separate set on here. And this is just what we did above. There's no difference as far as the randomness that we're using to build this set on here. The only difference is that we already did our scalar up here. Well, that doesn't matter because the data is going to be across the same thing. But this should just be transform down here instead of fit transform. Because you don't want to refit your data on your testing data. There we go. And now we're just transforming it because you never want to transform the test data. Easy mistake to make, especially on an example like this where we're not doing, we're randomizing the data anyway, so it doesn't matter too much because we're not expecting something weird. And then we want to go ahead and do our predictions. The whole reason we built the model is we take our model, we predict, and we're going to do, here's our X-scale data, batch size 10, verbose, and now we have our predictions in here, and we could go ahead and do a we'll print predictions, and then I guess I could just put down predictions in 5 so we can look at the first 5 of the predictions. And what we have here is we have our age and the prediction on this age versus what we think it's going to be, what we think is going to they're going to have symptoms or not. And the first thing we notice is that's hard to read because we really want a yes/no answer. So we'll go ahead and just round off the predictions using the argmax, the NumPy argmax for predictions. So it just goes to a 0, 1, and if you remember, this is a Jupyter Notebook, so I don't have to put the print. I can just put in rounded predictions, and we'll just do the first 5. And you can see here 0, 1, 0, 0, 0. So that's what the predictions are that we have coming out of this. Is no symptoms, symptoms, no symptoms, symptoms, no symptoms. And just as we were talking about at the beginning, we want to go ahead and take a look at this. There we go. Confusion matrices for accuracy check. Most important part when you get down to the end of the story, how accurate is your model before you go and play with the model and see if you can get a better accuracy out of it. And for this, we'll go ahead and use the scikit, the sklearn metrics, scikit being where that comes from. Import confusion matrix, some iteration tools, and of course a nice matplot library. That makes a big difference, so it's always nice to have a nice graph to look at. Picture's worth 1,000 words. And then we'll go ahead and call it CM for confusion matrix, y true equals test labels, y predict rounded predictions. And we'll go ahead and load in our CM. And I'm not going to spend too much time on the plotting, going over the different plotting code. You can spend we have whole tutorials on how to do your different plotting on there. But we do have here is we're going to do a plot confusion matrix. There's our CM, our classes, normalized false, title, confusion matrix. CMAP is going to be in blues. And you can see here we have to the nearest CMAP, titles, all the different pieces, whether you put tick marks or not, the marks, the classes, the color bar. So a lot of different information on here as far as how we're doing the printing of the confusion matrix. You can also just dump the confusion matrix into a Seaborn and real quick get an output. It's worth knowing how to do all this when you're doing a presentation to the shareholders. You don't want to do this on the fly. You want to take the time to make it look really nice, like our guys in the back did. And let's go ahead and do this. Forgot to put together our CM plot labels. We'll go ahead and run that. And then we'll go ahead and call the definition for our mapping. And you can see here plot confusion matrix. That's the little script we just wrote. And we're going to dump our data into it. So our confusion matrix, our classes, title confusion matrix, and let's just go ahead and run that. And you can see here we have our basic setup. No side effects 195, had side effects 200, no side effects that had side effects. So we predicted the 10 of them who actually had side effects, and that's pretty good. I mean, I don't know about you, but you know, that's 5% error on this, and this is because there's 200 here. That's where I get 5% is divide these both by 2 and you get 5 out of 100. You can do the same kind of math up here. Not as quick on the fly because it's 15 and 195, not an easily rounded number. But you can see here where they have 15 people who predicted to have with the no side effects but had side effects kind of setup on there. And these confusion matrix are so important at the end of the day. This is really where you show whatever you're working on comes up, and you can actually show them, hey, this is how good we are or not, how messed up it is. So this was I spent a lot of time on some of the parts, but you can see here is really simple. We did the random generation of data, but when we actually built the model coming up here, here's our model summary, and we just have the layers on here that we built with our model on this, and then we went ahead and trained it and ran the prediction. Now we can get a lot more complicated. Let me flip back on over here because we're going to do another demo. So that was our basic introduction to it. We talked about the oops, here we go. Okay, so implementing a neural network with Keras. After creating our samples and labels, we need to create our Keras neural network model. We will be working with a sequential model which has 3 layers. And this is what we did. We had our input layer, our hidden layers, and our output layers. And you can see the input layer coming in was the age factor. We had our hidden layer, and then we had the output. Are you going to have symptoms or not? So we're going to go ahead and go with something a little bit more complicated. Training our model is a 2-step process. We first compile our model and then we train it in our training data set. So we have compiling. Compiling converts the code into a form of understandable by machine. We use the atom in the last example, a gradient descent algorithm, to optimize the model, and then we trained our model, which means it let it learn on training data. And I actually had a little backwards there, but this is what we just did. Is we, if you remember from our code we just had, oops, let me go back here. Here's our model that we created, summarized. We come down here and we compile it. So it tells it, hey, we're ready to build this model and use it. And then we train it. And this is the part where we go ahead and fit our model and put that information in here, and it goes through the training on there. And of course we scaled the data, which was really important to do. And then you saw we did the creating a confusion matrix with Keras. As we are performing classifications on our data, we need a confusion matrix to check the results. A confusion matrix breaks down the various misclassifications as well as correct classifications to get the accuracy. And so you can see here, this is what we did with a true positive, true negative, false negative. And that is what we went over. Let me just scroll down here. On the end, we printed it out, and you can see we have a nice printout of our confusion matrix with the true positive, false negative, true negative. And so the blue ones, we want those to be the biggest numbers because those are the better side. And then we have our false predictions on here as far as this one. So it had no side effects, but we predicted, let's see, no side effects predicting side effects and vice versa.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, saving and loading models with Keras. We're going to dive into a more complicated demo. And you're going to say, oh, well, that was a lot of complication before. Well, if you broke it down, we randomized some data, we created the Keras setup, we compiled it, we trained it, we predicted, and we ran our matrix. So we're going to dive into something a little bit more fun. Is we're going to do a face mask detection with Keras. So we're going to build a Keras model to check if a person is wearing a mask or not in real time. And this might be important if you're at the front of a store. This is something today which is might be very useful as far as some of our, making sure people are safe. And so we're going to look at mask and no mask. And let's start with a little bit on the data. And so in my data I have with a mask. You can see they just have a number of images showing the people in masks. And again, if you want some of this information, contact Simplilearn, and they can send you some of the information as far as people with and without masks, so you can try it on your own. And this is just such a wonderful example of this setup on here. So before I dive into the mask detection, talking about being in the current with COVID and seeing if people are wearing masks, this particular example I had to go ahead and update to a Python 3.8 version. It might run in a 3.7, I'm not sure. I kind of skipped 3.7 and installed 3.8. So I'll be running in a Python 3.8, and then you also want to make sure your TensorFlow is up to date, because the they call functional layers, that's where they split, if you remember correctly from back. Let's take a look at this. Remember from here, the functional model and a functional layer allows us to feed in the different layers into different nodes into different layers and split them. Very powerful tool, very popular right now in the edge of where things are with neural networks and creating a better model. So I've upgraded to Python 3.8, and let's go ahead and open that up and go through our next example, which includes multiple layers, programming it to recognize whether someone wears a mask or not, and then saving that model so we can use it in real time. So we're actually almost a full end-to-end development of a product here. Of course, this is a very simplified version, and there'd be a lot more to it. You'd also have to do like recognizing whether it's someone's face or not. All kinds of other things go into this. So let's go ahead and jump into that code, and we'll open up a new Python 3. Oops, Python 3. It's working on it. There we go. And then we want to go ahead and train our mask. We'll just call this train mask. And we want to go ahead and train mask and save it. So it's save mask, train mask detection, not to be confused with masking data. A little bit different. We're actually talking about a physical mask on your face. And then from the Keras standpoint, we got a lot of imports to do here. And I'm not going to dig too deep on the imports. We're just going to go ahead and notice a few of them. So we have in here, oops, let me go Alt-D, there we go. Have something to draw with a little bit here. We have our image processing, and the image processing right here, let me underline that, deals with how do we bring images in, because most images are like a square grid, and then each value in there has 3 values for the 3 different colors. Keras and TensorFlow do a really good job of working with that, so you don't have to do all the heavy listening and figuring out what's going to go on. We have the mobile net average pooling 2D. This again is how do we deal with the images and pooling them. Dropout's a cool thing worth looking up. If you haven't, as you get more and more into Keras and TensorFlow, it'll auto drop out certain nodes. That way you'll get a better, the nodes just kind of die. They find that they actually create more of a bias than a help, and they also add processing time, so they remove them. And then we have our flatten. That's where you take that huge array with the 3 different colors and you find a way to flatten it so it's just a one-dimensional array instead of a 2 by 2 by 3. Dense input, we did that in the other one, so that should look a little familiar. Oops, there we go. Our input, our model. Again, these are things we had on the last one. Here's our optimizer with our atom. We have some pre-processing on the input that goes along with bringing in the data in. More pre-processing with image to array, loading the image. This stuff is so nice. It looks like a lot of work. So you have to import all these different modules in here. But the truth is it does everything for you. You're not doing a lot of pre-processing. You're letting the software do the pre-processing. And we're going to be working with the setting something to categorical. Again, that's just a conversion from a number to a category. 0, 1 doesn't really mean anything. It's like true, false. Label binarizer, the same thing. We're changing our labels around. And then there's our train test split classification report. Our IM utilities, let me just go ahead and scroll down here a notch for these. This is something a little different going on down here. This is not part of the TensorFlow or the sklearn. This is the scikit setup and TensorFlow above. The path, this is part of OpenCV, and we'll actually have another tutorial going out with the OpenCV. So if you want to know more about OpenCV, you'll get a glance on it in this software, especially the second piece when we reload up the data and hook it up to a video camera. We're going to do that on this round. But this is part of the OpenCV thing, and you'll see CV2 is usually how that's referenced. But the IM utilities has to do with how do you rotate pictures around and stuff like that, and resize them. And then the matplot library for plotting, because it's nice to have a graph, tells us how good we're doing, and then of course our numpy numbers array and just a straight OS access. Wow, so that was a lot of imports. Like I said, I'm not going to I spent a little time going through them, but we didn't want to go too much into them. And then I'm going to create some variables that we need to go ahead and initialize. We have the learning rate, number of epochs to train for, and the batch size. And if you remember correctly, we talked about the learning rate to the -4.00001 A lot of times it's 0.001 or 0.001. Usually it's in that variation depending on what you're doing and how many epochs, and they kind of play with the epochs. The epochs is how many times we're going to go through all the data. Now I have it as 2. The actual setup is for 20, and 20 works great. The reason I have it for 2 is it takes a long time to process. One of the downsides of Jupyter is that Jupyter isolates it to a single kernel. So even though I'm on an 8-core processor with 16 dedicated threads, only one thread is running on this, no matter what. So it doesn't matter. So it takes a lot longer to run, even though TensorFlow really scales up nicely. And the batch size is how many pictures do we load at once and process. Again, those are numbers you have to learn to play with depending on your data and what's coming in. And the last thing we want to go ahead and do is there's a directory with a data set we're going to run. And this just has images of masks and not masks. And if we go in here, you'll see data set. And then you have pictures with masks. They're just images of people with masks on their face. And then we have the opposite. Let me go back up here. Without masks. So it's pretty straightforward. They look kind of askew because they tried to format them into very similar setup on there. So they're mostly squares. You'll see some that are slightly different on here. And that's kind of an important thing to do on a lot of these data sets. Get them as close as you can to each other. And we actually will run in this processing of images up here, and the Keras layers and importing and dealing with images. It does such a wonderful job of converting these that a lot of it we don't have to do a whole lot with. So you have a couple things going on there. And so we're now going to be, this is now loading the images, and let me see. And we'll go ahead and create data and labels. Here's our here's the features going in, which is going to be our pictures, and our labels going out. And then for categories in our list directory, and if you remember I just flashed that at you, it had face mask or no face mask. Those are the two options. And we're just going to load into that. We're going to append the image itself and the labels. So we're just going to create a huge array. And you can see right now this could be an issue if you had more data. At some point, thankfully I have a 32 gig hard drive or RAM. Even that, you could do with a lot less of that. Probably under 16 or even 8 gigs would easily load all this stuff. And there's a conversion going on in here. I told you about how we are going to convert the size of the image so it resizes all the images. And that way our data is all identical the way it comes in. And you can see here with our labels, we have without mask, without mask, without mask. The other one would be with mask. Those are the two that we have going in there. And then we need to change it to the one-hot encoding. And this is going to take our, up here we had, what was it, labels and data. We want the labels to be categorical. So we're going to take labels and change it to categorical, and our labels then equal a categorical list. We'll run that. And again, if we do labels and we just do the last or the first 10, let's do the last 10 just because minus 10 to the end. There we go. Just so we can see what the other side looks like. We now have 1. That means they have a mask. 1, 0, 1, 0, so on. 1 being they have a mask, and 0 no mask. And if we did this in reverse, I just realized that this might not make sense if you've never done this before. Let me run this. 0, 1. So 0 is, do they have a mask on? 0. Do they not have a mask on? 1. So this is the same as what we saw up here without mask. 1 equals, the second value is without mask. So with mask, without mask. And that's just with any of your data processing, we can't really, if you have a 0, 1 output, it causes issues as far as training and setting it up. So we always want to use a one-hot encoder if the values are not actual linear value or regression values, are not actual numbers, if they represent a thing. And so now we need to go ahead and do our train X, test X, train Y, test Y, train split test data. And we'll go ahead and make sure it's going to be random, and we'll take 20% of it for testing and the rest for setting it up as far as training their model. This is something that's become so cool. When they're training these set, they realize we can augment the data. What does augment mean? Well, if I rotate the data around and I zoom in, I zoom out, I rotate it, share it a little bit, flip it horizontally, fill mode, as I do all these different things to the data, it is able to, it's kind of like increasing the number of samples I have. So if I have all these perfect samples, what happens when we only have part of the face, or the face is tilted sideways, or all those little shifts cause a problem if you're doing just a standard set of data. So we're going to create an augment in our image data generator, which is going to rotate, zoom, and do all kinds of cool things. And this is worth looking up, this image data generator and all the different features it has. A lot of times, the first time through my models, I'll leave that out because I want to make sure there's a thing what we call build to fail, which is just cool to know. You build the whole process, and then you start adding these different things in so that you can better train your model. And so we go and run this, and then we're going to load. And then we need to go ahead, and you probably would have gotten an error if you hadn't put this piece in right here. I haven't run it myself because the guys in the back did this. But we take our base model, and one of the things we want to do is we want to do a MobileNet v2. And this is a big thing right here. Include the top equals false. A lot of data comes in with a label on the top row. So we want to make sure that that is not the case. And then the construction of the head of the model that will be placed on the top of the base model. We want to go ahead and set that up. And you'll see a warning here. I'm kind of ignoring the warning because it has to do with the size of the pictures and the weights for input shape. So it'll switch things to defaults, just saying, hey, we're going to auto shape some of this stuff for you. You should be aware that with this kind of imagery, we're already augmenting it by moving it around and flipping it and doing all kinds of things to it. So that's not a bad thing in this. But in other data, it might be if you're working in a different domain. And so we're going to go back here, and we're going to we have our base model. We're going to do our head model equals our base model output. And what we got here is we have an average pooling 2D, pool size 7.7 head model. Head model flatten. So we're flattening the data. So this is all processing and flattening the images. And the pooling has to do with some of the ways it can process some of the data. We'll look at that a little bit when we get down to the lower level and is processing it. And then we have our dents. We've already talked a little bit about a dents, just what you think about. And then the head model has a dropout of 0.5. What we can do with a dropout? The dropout says that we're going to drop out a certain amount of nodes while training. So when you actually use the model, it will use all the nodes. But this drops certain ones out, and it helps stop biases from forming. So it's really a cool feature in here. They discovered this a while back. We have another dense mode, and this time we're using softmax activation. Lots of different activation options here. Softmax is a real popular one for a lot of things, and so is the ReLU. And we could do a whole talk on activation formulas and what their different uses are and how they work. When you first start out, you'll use mostly the ReLU and the softmax for a lot of them, just because they're some of the basic setups. It's a good place to start. And then we have our model equals model, inputs equals base model dot input, outputs equals head model. So again, we're still building our model here. We'll go ahead and run that. And then we're going to loop over all the layers in the base model and freeze them so they will not be updated during the first training process. So for layer and base model layers, layers.trainable equals false. A lot of times when you go through your data, you want to kind of jump in partway through. I'm not sure why in the back they did this for this particular example, but I do this a lot when I'm working with series and specifically in stock data. I want it to iterate through the first set of 30 data before it does anything. I would have to look deeper to see why they froze it on this particular one. And then we're going to compile our model. So compiling the model, atom, init, layer, decay, initial learning rate over epochs, and we go ahead and compile. Our loss is going to be the binary cross entropy, which will have that print out. Optimizer for opt, metrics is accuracy. Same thing we had before, not a huge jump as far as the previous code. And then we go ahead and we've gone through all this, and now we need to go ahead and fit our model. So train the head of the network, print info training head, run. Now I skipped a little time because you'll see the run time here is at 80 seconds per epoch. It takes a couple minutes for it to get through on a single kernel. One of the things I want you to notice on here while it's finishing the processing is that we have up here our augment going on. So anytime the train X and train Y go in, there's some randomness going on there, and is jiggling it around what's going into our setup. Of course, we're batch sizing it, so it's going through whatever we set for the batch values, how many we process at a time. And then we have the steps per epoch, the train X, the batch size, validation data. Here's our test X and test Y, where we're sending that in. And this, again, it's validation. One of the important things to know about validation is when both our training data and our test data have about the same accuracy, that's when you want to stop. That means that our model isn't biased. If you have a higher accuracy on your testing, you've trained it, and your accuracy is higher on your actual test data, then something in there is probably has a bias and it's overfitted. So that's what this is really about right here with the validation data and validation steps. So it looks like let me go ahead and see if it's done processing. It looks like we've gone ahead and gone through 2 epochs. Again, you could run this through about 20 with this amount of data, and it would give you a nice refined model at the end. We're going to stop at 2 because I really don't want to sit around all afternoon, and I'm running this on a single thread. So now that we've done this, we're going to need to evaluate our model and see how good it is, and to do that we need to go ahead and make our predictions. These are our predictions on our test X to see what it thinks are going to be. So now it's going to be evaluating the network, and then we'll go ahead and go down here, and we will need to turn the indexing, because remember it's either 0 or 1. It's 0, 1, 0, 1. So you have 2 outputs: wearing a mask, not wearing a mask. And so we need to go ahead and take that argument at the end and change those predictions to a 0 or 1 coming out. And then to finish that off, we want to go ahead and let me just put this right in here and do it all in one shot. We want to show a nicely formatted classification report so we can see what that looks like on here. And there we have it. We have our precision. It's 97% with a mask. There's our F1 score, support without a mask, 97%. So that's pretty high setup on there. 3 people are going to sneak into this door who are without a mask and that thinks they have a mask, and there's going to be 3 people with a mask that's going to flag the person at the front to go, oh hey, look at this person, he might not have a mask. That's I guess if it's a setup in front of a store. So there you have it. And of course, one of the other cool things about this is if someone's walking into the store and you take multiple pictures of them, this is just it would be a way of flagging, and then you can take that average of those pictures and make sure they match or don't match if you're on the back end. And this is an important step because this is just cool. I love doing this stuff. So we're going to go ahead and take our model and we're going to save it. So model save maskdetector.model. We're going to give it a name. We're going to save the format. In this case, we're going to use the H5 format. And so this model we just programmed has just been saved. So now I can load it up into, say, another program. What's cool about this is, let's say I want to have somebody work on the other part of the program. Well, I just saved the model. They upload the model. Now they can use it for whatever. And then if I get more information and we start working with that, at some point I might want to update this model. make a better model. And this is true of so many things, where I take this model and maybe I'm running a prediction on making money for a company, and as my model gets better, I want to keep updating it, and then it's real easy just to push that out to the actual end user. And here we have a nice graph. You can see the training loss and accuracy as we go through the epochs. We only did the, only shows just the one epoch coming in here, but you can see right here as the value loss, train accuracy, and value accuracy start switching and they start converging. And you'll hear converging. This is the convergence they're talking about when they say I know when I work in the scikit with sklearn neural networks, this is what they're talking about, a convergence, is our loss and our accuracy come together, and also up here, and this is why I'd run it more than just 2 epochs. As you can see, they still haven't converged all the way. So that would be a cue for me to keep going. But what we want to do is we want to go ahead and create a new Python 3 program. And we just did our train mask. So now we're going to go ahead and import that and use it and show you in a live action. Get a view of both myself in the afternoon along with my background of an office, which is in the middle still of reconstruction for another month. And we'll call this mask detector. And then we're going to grab a bunch of a few items coming in. We have our MobileNet v2 import preprocessing input, so we're still going to need that. We still have our TensorFlow image to array. We have our load model. That's where most of the stuff's going on. This is our CV2 or OpenCV. Again, I'm not going to dig too deep into that. We're going to flash a little OpenCV code at you, and we actually have a tutorial on that coming out. Our NumPy array, our IM utilities, which is part of the OpenCV or CV2 setup. And then we have, of course, time and just our operating system. So those are the things we're going to go ahead and set up on here. And then we're going to create, this takes just a moment, our module here, which is going to do all the heavy lifting. So we're going to detect and predict a mask. We have frame, FaceNet, MaskNet. These are going to be generated by our OpenCV. We have our frame coming in, and then we want to go ahead and create a mask around the face. So it's going to try to detect the face and then set that up so we know what we're going to be processing through our model. And then there's a frame shape here. This is just our height versus width. That's all HW stands for. They've called it blob, which is a CV2 DNN blob form image frame. So this is reformatting this frame that's going to be coming in literally from my camera. And we'll show you that in a minute, that little piece of code that shoots that in here. And we're going to pass the blob through the network and obtain the face detections. So FaceNet.setImport blob, detections FaceNet forward, print detections shape. So this is what's going on here. This is that model we just created. We're going to send that in there, and I'll show you in a second where that is, but it's going to be under FaceNet. And then we go ahead and initialize our list of faces, their corresponding locations, and the list of predictions from our face mask network. We're going to loop over the detections, and this is a little bit more work than you think as far as looking for different faces. What happens if you have a crowd of faces? So we're looping through the detections and the shapes going through here. And probability associated with the detection. Here's our confidence of detections. We're going to filter out weak detection by ensuring the confidence is greater than the minimum confidence. So we've set it, remember, 0 to 1. So 0.5 would be our minimal confidence, probably is pretty good. And then we're going to put in compute bounding boxes for the object. If I'm zipping through this, it's because we're going to do an OpenCV, and I really want to stick to just the Keras part. And so I'm just kind of jumping through all this code. You can get a copy of this code from Simplilearn and take it apart, or look for the OpenCV coming out. And we'll create a box. The box sets it around the image. Ensure the bounding boxes fall within the dimensions of the frame. So we create a box around what we hope is going to be the face. Extract the face, ROI, convert it from BGR to RGB channel. Again, this is an OpenCV issue. Not really an issue, but it has to do with the order. I don't know how many times I've forgotten to check the order colors when working with OpenCV. Causes all kinds of fun things when red becomes blue and blue becomes red. And we're going to go ahead and resize it, process it, frame it, face frame, setup. Again, the face, the CVT color, we're going to convert it. We're going to resize it, image to array, pre-process the input, pin the face, locate face, start X, start Y, and X. Boy, that was just a huge amount, and I skipped over a ton of it, but the bottom line is we're building a box around the face, and that box, because the OpenCV does a decent job of finding the face, and that box is going to go in there and see, hey, does this person have a mask on it? And so that's what all this is doing on here. And then finally we get down to this where it says predictions equals masknet.predict faces batch size 32. So these different images where we're guessing where the face is are then going to go through and generate an array of faces, if you will. And we're going to look through and say, does this face have a mask on it? And that's what's going right here is our prediction. That's the big thing that we're working for. And then we return the locations and the predictions. The location just tells where on the picture it is, and then the prediction tells us what it is. Is it a mask or is it not a mask? Alright, so we've loaded that all up. So we're going to load our serialized face detector model from disk. And we have the path that it was saved in. Obviously, you're going to put it in a different path depending on where you have it or however you want to do it and how you saved it on the last one where we trained it. And then we have our weights path. And so finally our facenet, here it is, equals cv2.dnn.readnet prototext path weights path. And we're going to load that up on here. So let me go ahead and run that. And then we also need to, I'll just put it right down here. I always hate separating these things in there. And then we're going to load the actual mask detector model from disk. This is the model that we saved. So let's go ahead and run that on there also. So this is pulling in all the different pieces we need for our model. And then the next part is we're going to open up our video. And this is just kind of fun because it's all part of the OpenCV video setup. And let me just put this all in as one. There we go. So we're going to go ahead and open up our video. We're going to start it and we're going to run it until we're done. And this is where we get some real kind of live action stuff, which is fun. This is what I like working about with images and videos, is that when you start working with images and videos, it's all right there in front of you. It's visual and you can see what's going on. So we're going to start our video streaming. This is grabbing our video stream source 0 start. That means it's grabbing my main camera I have hooked up. And then, starting video, you're going to print it out. Here's our video source equals 0 start. Loop over the frames from the video stream. Oops, a little redundancy there. Let me close. I'll just leave it. That's how they had it in the code. So while true, we're going to grab the frame from the threaded video stream and resize it to have the maximum width of 400 pixels. So here's our frame. We're going to read it from our visual stream. We're going to resize it. And then we're returning. Remember, we returned from our procedure the location and the prediction. So detect and predict mask. We're sending it the frame. We're sending it the face net and the mask net. So we're sending all the different pieces that say this is what's going through on here. And then it returns our location and predictions, and then for our box and predictions in the location and predictions. And the box is again, this is an OpenCV set that says, hey, this is a box coming in from the location. Because you have the two different points on there. And then we're going to unpack the box and predictions, and we're going to go ahead and do mask without a mask equals prediction. We're going to create our label. no mask, we can create color if the label equals mask L00225. And this is going to make a lot more sense when I hit the run button here. But we have the probability of the label. We're going to display the label and bounding box rectangle in the output frame. And then we're going to go ahead and show the output from the frame, CV2 IM show frame. And then the key equals CV2 wait key 1. We're just going to wait till the next one comes through from our feed. And we're going to do this until we hit the stop button pretty much. So are you ready for this? Let's see if it works. We've distributed our model. We've loaded it up into our distributed code here. We've got it hooked into our camera. And we're going to go ahead and run it. And there it goes. It's going to be running. And we can see the data coming down here. And we're waiting for the pop-up. And there I am in my office with my funky headset on. And you can see in the background my unfinished wall, and it says up here, no mask. Oh no, I don't have a mask on. I wonder if I cover my mouth, what would happen? You can see my no mask goes down a little bit. I wish I'd brought a mask into my office. It's up at the house. But you can see here that this says, there's a 95-98% chance that I don't have a mask on. And it's true, I don't have a mask on right now. And this could be distributed. This is actually an excellent little piece of script that you could start, you install somewhere on a video feed on a security camera or something, and then you'd have this really neat setup saying, hey, do you have a mask on when you enter a store or public transportation or whatever it is where they're required to wear a mask? Let me go ahead and stop that. Now, if you want a copy of this code, definitely give us a holler. We will be going into OpenCV in another one, so I skipped a lot of the OpenCV code in here as far as going into detail. Really focusing on the Keras, saving the model, uploading the model, and then processing a streaming video through it so you can see that the model works. We actually have this working model that hooks into the video camera, which is just pretty cool and a lot of fun. So I told you we're going to dive in and really roll up our sleeve and do a lot of coding today. We did the basic demo up above for just pulling in a Keras, and then we went into a Keras model where we pulled in data to see whether someone was wearing a mask or not. So very useful in today's world as far as a fully running application.
So if you want to seek expertise in deep learning skills and aspire to be a part of cutting-edge field of building chatbots and service bots using deep learning, our Caltech postgraduate program in AI and machine learning provides comprehensive coverage of the latest tools and technologies within the AI ecosystem. It offers masterclasses led by esteemed Caltech faculty and IBM experts, engaging hackathons, and interactive Ask Me Anything sessions. By enrolling in this program, delivered in partnership with IBM, you will gain the expertise needed to become a professional in AI and ML. This comprehensive artificial intelligence course will equip you with the knowledge about various AI-based technologies, empowering you to excel in this field. So do check out the course link in the description for more details. Let's get started now.
Now let's move on to the differences between TensorFlow, Keras, and Pytorch. The first difference that we'll be looking at is called level of API. There are two main types of APIs, a low-level API and a high-level API. API stands for Application Programming Interface. A low-level application programming interface is generally more detailed and allows you to have more detailed control to manipulate functions within them on how to use and implement them, while a high-level API is more generic and simple and provides more functionality with one command statements than a lower-level API. High-level interfaces are comparatively easier to learn and to implement the models using them. They allow you to write code in a shorter amount of time and to be less involved with the details. In this case, TensorFlow is a high and low-level API. Pure TensorFlow is a low-level API, while TensorFlow wrapped in Keras is a high-level API. Keras in itself is a high-level API which uses multiple low-level APIs as a backend and simplifies the operation of these low-level APIs. Pytorch is a low-level API. The next criteria that we'll be looking at is speed. TensorFlow is very fast and is used for high performances. Keras is slower as it works on top of TensorFlow. Not only does it have to wait for TensorFlow to finish implementation, it then starts its own implementation. Meanwhile, Pytorch works at the same speed as TensorFlow, as both of them are both low-level APIs. Now, Keras is a wrapper class for TensorFlow and has added abstraction functionalities on top of TensorFlow, which make it slower than TensorFlow and Pytorch. In computation speed, both TensorFlow and Pytorch are almost equal, and in development speed, Keras is faster as it has built-in functionalities which can significantly reduce your development time. The next difference is on the architecture. TensorFlow is not very easy to use, and even though it provides Keras as a framework that makes it work easier, TensorFlow still has a very complex architecture which is hard to use. Meanwhile, Keras has a simpler architecture and is easier to use. It provides a high level of abstraction which makes implementation of programs in Keras significantly easier. Pytorch, on the other hand, also has a complex architecture and the readability is less when compared to Keras. TensorFlow uses computational graphs, which makes it very complex and hard to interpret, but it has amazing computational ability across platforms. Pytorch is a little hard for beginners, but is really good for computer vision and deep learning purposes. Datasets and debugging. TensorFlow works with large datasets due to its high execution speed, and debugging is really hard in TensorFlow due to its complex nature. Meanwhile, Keras only works with very small datasets as its speed of execution is low. Programs do not require frequent debugging in Keras as they are relatively simpler, and Pytorch can manage high-level tasks in higher dimension datasets and is easier to debug than both Keras and TensorFlow. Next, we'll be looking at ease of development. As we said before, TensorFlow works with many hard concepts such as computational graphs and tensors, which means that writing code in TensorFlow is very hard. It is generally used by people when they are doing research work and really need very specific functionalities. Keras, on the other hand, provides a high level of abstraction which makes it very easy to use. It is best for people who are just starting out with Python and machine learning. Pytorch is easier than TensorFlow but is still comparatively hard than Keras. It is not very easy to learn for beginners but is significantly more powerful than just plain Keras. Ease of deployment. TensorFlow is very easy to deploy as it uses TensorFlow serving. TensorFlow Serving is a flexible, high-performance serving system for machine learning models designed for production environments. TensorFlow Serving makes it easy to deploy new algorithms and experiments while keeping the same server architecture and APIs. TensorFlow Serving provides out-of-the-box integration with TensorFlow models but can be easily extended to serve other types of models and data. In Keras, model deployment can be done with either TensorFlow Serving or Flask, which makes it relatively easy but not as easy as it would be with TensorFlow and Pytorch. Pytorch uses Pytorch Mobile, which makes deployment easy, but again, for TensorFlow deployment is way easier as TensorFlow Serving can update your machine learning backend on the fly without the user even realizing. There's a growing need to execute ML models on edge devices to reduce latency, preserve privacy, and enable new interactive use cases. In the past, engineers used to train models separately. They would then go through a multi-step, error-prone, and often complex process to train the models for execution on a mobile device. The mobile runtime was often significantly different from the operations available during training, leading to inconsistent developer and eventually user experience. All of these frictions have been removed by Pytorch Mobile by allowing a seamless process to go from training to deployment by staying entirely within the Pytorch ecosystem. It provides an end-to-end workflow that simplifies the research to production environment for mobile devices. In addition, it paves the way for privacy-preserving features via federated learning techniques. At the end of the day, the question that really matters is which framework should you use, Keras, TensorFlow, or Pytorch? Now, TensorFlow has implemented various levels of abstraction to make implementation of deep learning and neural networks easy. This has also made debugging easier. Keras is simple and easy but not as fast as TensorFlow. It is more user-friendly than any other deep learning API, however, and is easier to learn. for beginners. Pytorch, on the other hand, is the preferred deep learning API for teachers, but it is not as widely used in production as TensorFlow is. It is faster, but it has lower GPU utilization. At the end of the day, the framework that we would suggest that you use is TensorFlow. Why? While Pytorch may have been the preferred deep learning library for researchers, TensorFlow is much more widely used in day-to-day production. Pytorch's ease of use combined with the default eager execution mode for easier debugging predestines it to be used for fast, hacky solutions and smaller scale models. But TensorFlow's extensions for deployment on both servers and mobile devices combined with the lack of Python overhead makes it the preferred option for companies that work with deep learning models. In addition, the TensorFlow board visualization features offers a nice way of showing the inner workings of your model to, say, your customers. Meanwhile, between TensorFlow and Keras, the main difference isn't in performance. TensorFlow is a bit faster due to less overhead, but also the level of control you would like. Keras is much easier to start with than plain TensorFlow, but if you want to do something with Keras that doesn't come out of the box, it will be harder to implement that. TensorFlow, on the other hand, allows you to create any arbitrary computational graph, providing much more flexibility. So if you're doing more research type of work, TensorFlow is the sure route to go due to the flexibility that it provides.
So if you want to seek expertise in deep learning skills and aspire to be a part of cutting-edge field of building chatbots and service bots using deep learning, our Caltech postgraduate program in AI and machine learning provides comprehensive coverage of the latest tools and technologies within the AI ecosystem. It offers masterclasses led by esteemed Caltech faculty and IBM experts, engaging hackathons, and interactive Ask Me Anything sessions. By enrolling in this program, delivered in partnership with IBM, you will gain the expertise needed to become a professional in AI and ML. This comprehensive artificial intelligence course will equip you with the knowledge about various AI-based technologies, empowering you to excel in this field. So do check out the course link in the description for more details. Let's get started now.
So what are generative adversarial networks? Generative adversarial networks, or GANs, introduced in 2014 by Ian J. Goodfellow and co-authors, became very popular in the field of machine learning. GAN is an unsupervised learning task in machine learning. It consists of two models that automatically discover and learn the patterns in input data. The two models, called generator and discriminator, compete with each other to analyze, capture and copy the variations within a dataset. GANs can be used to generate new examples that possibly could have been drawn from the original dataset. In the image below, you can see that there is a database that has real 100 rupee notes. The generator, which is basically a neural network, generates fake 100 rupees notes. The discriminator network will identify if the notes are real or fake. Let us now understand in brief about what is a generator. A generator in GANs is a neural network that creates fake data to be trained on the discriminator. It learns to generate plausible data. The generated instances become negative training examples for the discriminator. It takes a fixed length random vector carrying noise as input and generates a sample. Now the main aim of the generator is to make the discriminator classify its output as real. The portion of the GAN that trains the generator includes a noisy input vector, the generator network, which transforms the random input into a data instance, a discriminator network which classifies the generated data, and a generator loss, which penalizes the generator for failing to dolt the discriminator. The backpropagation method is used to adjust each weight in the right direction by calculating the weight's impact on the output. The backpropagation method is used to obtain gradients, and these gradients can help change the generator weights. Now, let us understand in brief what a discriminator is. A discriminator is a neural network model that identifies real data from the fake data generated by the generator. The discriminator's training data comes from two sources. The real data instances, such as real pictures of birds, humans, currency notes, etc., are used by the discriminator as positive samples during the training. The fake data instances created by the generator are used as negative examples during the training process. While training the discriminator, it connects with two loss functions. During discriminator training, the discriminator ignores the generator loss and just uses the discriminator loss. In the process of training the discriminator classifies both real data and fake data from the generator. The discriminator loss penalizes the discriminator for misclassifying a real data instance as fake or a fake data instance as real. Now moving ahead, let's understand how GANs work. Now GANs consists of two networks, a generator which is represented as G of X and a discriminator which is represented as D of X. They both play an adversarial game where the generator tries to fool the discriminator by generating data similar to those in the training set. The discriminator tries not to be fooled by identifying fake data from the real data. They both work simultaneously to learn and train complex data like audio, video or image files. Now you are aware that GANs consists of two networks, a generator G of X and discriminator D of X. Now the generator network takes a sample and generates a fake sample of data. The generator is trained to increase the probability of the discriminator network to make mistakes. On the other hand, the discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the range 0 and 1. Here is an example of a generative adversarial network trying to identify if the 100 rupee notes are real or fake. So first, a noise vector or the input vector is fed to the generator network. The generator creates fake 100 rupee notes. The real images of 100 rupee notes stored in a database are passed to the discriminator along with the fake notes. The discriminator then identifies the notes and classifies them as real or fake. We train the model, calculate the loss function at the end of the discriminator network, and backpropagate the loss into both discriminator and generator. Now the mathematical equation of training a GAN can be represented as, you can see here. Now this is the equation and these are the parameters. Here G represents generator, D represents the discriminator. Now P data of X is the probability distribution of real data, P of Z is the distribution of generator, X is the sample of probability data of X, Z is the sample size from P of Z, D of X is the discriminator network, and G of Z is the generator network. Now the discriminator focuses to maximize the objective function such that D of X is close to 1 and Z of Z is close to 0. It simply means that the discriminator should identify all the images from the training set as real, that is 1, and all the generated images as fake, that is 0. The generator wants to minimize the objective function such that D of Z of Z is 1. This means that the generator tries to generate images that are classified as real, that is 1, by the discriminator network. Next, let's see the steps for training a neural network. So we have to first define the problem and collect the data. Then we'll choose the architecture of GAN. Now depending on your problem, choose how your GAN should look like. Then we need to train the discriminator on real data. Now that will help us predict them as real for n number of times. Next, you need to generate fake inputs for the generator. After that, you need to train the discriminator on fake data to predict the generated data as fake. Finally, train the generator on the output of discriminator. With the discriminator predictions available, train the generator to fool the discriminator. Let us now look at the different types of GANs. So first we have vanilla GANs. Now vanilla GANs have min-max optimization formula that we saw earlier, where the discriminator is a binary classifier and is using sigmoid cross entropy loss during optimization. In vanilla GANs, the generator and the discriminator are simple multi-layer perceptrons. The algorithm tries to optimize the mathematical equation using stochastic gradient descent. Up next, we have deep convolutional GANs or DC GANs. Now DC GANs support convolutional neural networks instead of vanilla neural networks at both discriminator and generator. They are more stable and generate higher quality images. The generator is a set of convolutional layers with fractional strided convolutions or transpose convolutions, so it unsamples the input image at every convolutional layer. The discriminator is a set of convolutional layers with strided convolutions, so it downsamples the input image at every convolutional layer. Moving ahead, the third type you have is conditional GANs or CGANs. Vanilla GANs can be extended into conditional models by using an extra label information to generate better results. In CGAN, an additional parameter called y is added to the generator for generating the corresponding data. Labels are fed as input to the discriminator to help distinguish the real data from fake data generated. Finally, we have super resolution GANs. Now SR GANs use deep neural networks along with adversarial neural network to produce higher resolution images. Super resolution GANs generate a photorealistic high resolution image when given a low resolution image. Let's look at some of the important applications of GANs. So with the help of DC GANs, you can train images of cartoon characters for generating faces of anime characters and Pokemon characters as well. Next, GANs can be used on the images of humans to generate realistic faces. The faces that you see on your screens have been generated using GANs and do not exist in reality. Third application we have is GANs can be used to build realistic images from textual descriptions of objects like birds, humans, and other animals. We input a sentence and generate multiple images fitting the description. Here is an example of a text-to-image translation using GANs for a bird with a black head, yellow body, and a short beak. The final application we have is creating 3D objects. So GANs can generate 3D models using 2D pictures of objects from multiple perspectives. GANs are very popular in the gaming industry. GANs can help automate the task of creating 3D characters and backgrounds to give them a realistic feel.
So if you want to seek expertise in deep learning skills and aspire to be a part of cutting-edge field of building chatbots and service bots using deep learning, our Caltech postgraduate program in AI and machine learning provides comprehensive coverage of the latest tools and technologies within the AI ecosystem. It offers masterclasses led by esteemed Caltech faculty and IBM experts, engaging hackathons, and interactive Ask Me Anything sessions. By enrolling in this program, delivered in partnership with IBM, you will gain the expertise needed to become a professional in AI and ML. This comprehensive artificial intelligence course will equip you with the knowledge about various AI-based technologies, empowering you to excel in this field. So do check out the course link in the description for more details. Let's get started now.
So computational graphs are really the heart and soul of neural networks. We talk about a computational graph. They are a visual representation of expressing and evaluating mathematical equations. The nodes and data flow in a graph correspond to mathematical operations and variables. You'll hear a lot, some of the terms you might hear are node and edge, the edge being the data flow in this case. It could also represent an actual value. They have, I think in Spark they have a graph X, which works just on computing edges. There's all kinds of stuff that has evolved from computational graphs. We're focusing just on Keras and on neural networks. So we're not going to go into great detail on everything a computational graph does. It is a core component of a neural network is what's important to know on this. So Keras offers a Python user-friendly front end while maintaining a strong computation power by using a low-level API like TensorFlow, Pytorch, etc., which use computational graphs as a backend. So one, this allows for abstraction of complex problems while specifying control flow. If you've ever looked at some of the backend or the original versions of TensorFlow, it's really a nightmare. You have all these different settings you have to put in there and create. It's a lot of back-end programming. This is like the old computers when you had to tell it how to dispose of a variable and how to properly reallocate the memory for use. All that is covered nowadays in our higher level programming. Well, this is the same thing with Keras, is it covers a lot of this stuff and does things for you that you could spend hours on just trying to figure out. It's useful for calculating derivatives by using back propagation. We're definitely not going to teach a class on derivatives in this little video, but understanding a derivative is the rate of change. So if you have a particular function you're using in your neural network, a lot of them is just simple y equals mx plus b, your Euclidean geometry where you just have a simple slope times the intercept. And they get very complicated. They have the inverse tangent function for activation as opposed to just a linear Euclidean model. And you can think about this as you have your data coming in and you have to alter it somehow. Well, you alter it going down to get an answer, you end up with an error, and that error goes back up, and you have to have that back propagation with the derivative. You want to know how it changed so that you can figure out how to adjust it for the error. A lot of that's hidden, so you don't even have to worry about it with Keras. And in today's Keras, it'll even, if you create your own formula for computing an answer, it will automatically compute the derivative for you in a lot of cases. It's easier to implement distributed computation. So Keras is a really nice way to package it and get it off on different computers and share it. And it allows parallelism, which means that two operations can run simultaneously. So as we start developing these backends, it can do all kinds of cool things and utilize multiple cores, GPUs on a computer to get that parallel processing up. What are neural networks? Well, like I said, there are already, we talked about in computational edges, you have a node and you have a connection, or your edge. So neural networks are algorithms fashioned after the human brain, which contain multiple layers. Each layer contains a node called a neuron, which performs a mathematical operation. They break down complex problems into simple operations. So one, an input layer takes in our data and pre-processes it. When we talk about pre-processing, when you're dealing with neural networks, you usually have to pre-process your data so that it's between -1 and 1 or 0 and 1 into some kind of value that's usable. That occurs before it gets to the neural network. In fact, 80% of data science is usually in prepping that data and getting it ready for your different models. Two, you have hidden layer performs a nonlinear transformation of input. Now it can do a linear transformation. It can use just a basic Euclidean geometry, and you could think of a node adding all the different connections coming in. So each connection would have a weight, and then it would add to that weight plus an intercept in the node itself. So you can actually use Euclidean geometry. But a lot of these get really complicated. They have all these different formulas, and they're really cool to look at. But when you start looking at them, look at how they work. You really don't need to know the high math behind it to figure them out and figure out what they're doing, which is really cool. That means a lot of people can use this without having to go get a PhD in mathematics. Number three, the output layer takes the results from hidden layer, transforms them, and gives a final output. So sequential models. So what makes this a sequential model? Sequential models are linear stacks of layers where one layer leads to the next. It is simple and easy to implement, and you just have to make sure that the previous layer is the input to the next layer. So you have used for plain stack of layers where each layer has one input and one output tensor. And this is what TensorFlow is named after, is each one of these layers is like a tensor. Each node is a tensor, and then the layer is also considered a tensor of values. And it's used for simple classifier, declassifier models. It's also used for regression models too. So it's not just about this is something, this is a teapot, this is a cat, this is a dog. It's also used for generating the actual values. You know, this is worth $10, that's worth $30. The weather's going to be 90 degrees out or whatever it is. So you can use it for both classifier and declassifier models. And one more note when we talk about sequential models. The term sequential is used a lot, and it's used in different areas and different notations when you're in data science. So when we talk about time series, we'll talk about sequential. That is something very different. Sequential, in this case, means it goes from the input to layer 1 to layer 2 to the output. So it's very directional. It's important to note this because if you have a sequential model, can you have a non-sequential model? And the answer is yes. If you master the basics of a sequential model, you can just as easily have another model that shares layers. You can have another model where you have an input coming in and it splits. And then you have one set that's doing one set of nodes. Maybe they're doing a yes-no kind of node, where it's either putting out a 0 or a 1, a classifier. And the other one might be regression. It's just processing numbers, and then you recombine them for the output. That's what they call the Keras API. So there's a lot of different availabilities in here, and all kinds of cool things you can do as far as encoding and decoding and all kinds of things. And you can share layers and things like that. We're just focusing on the basic Keras model with the sequential model. So let's dive into the meat of the matter. Let's do a demo on here. Today's demo, in this demo, we'll be performing flower classification using sequential model in Keras. And we'll use our model to classify between 5 different types of flowers. Now, for this demo, and you can do this demo on whatever platform you want, or whatever user interface for developing Python, I'm actually using Anaconda, and then I'm using Jupyter notebooks to develop in. And if you're not familiar with this, you can go under Environment. Once you've created environment, you can come in here to open a terminal window. And if you don't have the different modules in here, you can do your conda install, or whatever module it is. Just happened that this particular setup didn't have a Seaborn in it, which I already installed. So here's our Anaconda, and then I'm going to go back and start up my Jupyter notebook, where I already created a new Python project, Python 3. I'm in Python 3.8 on this particular one. Sequential model for flowers. So lots of fun there. So we're going to jump right into this. The first thing is to make sure you have all your modules installed. So if you don't have NumPy, Pandas, Matplotlib, and Seaborn, and the Keras, and sklearn, or scikit, it's not actually sklearn, you'll need to go ahead and install all of those. Now, having done this for years and having switched environments and doing different things, I get all my imports done, and then we just run it, and if we get an error, we know we have to go back and install something. Right off the bat, though, we have NumPy, Pandas, Matplotlib, Seaborn. These are built on top of each other. Pandas, the data frame, and built on top of NumPy, the data array. And then we bring in our sklearn, or scikit. This is the scikit setup, scikit. Even though you use sklearn to bring it in, it's a scikit. And then our Keras. We have our pre-processing the images, image data generator, our model. This is our basic model, our sequential model. And then we bring in from Keras layers, import dents, optimizers. These optimizers, a lot of them already come in. These are your different optimizers, and it's almost, a lot of this is so automatic now. Atom is a lot of times the default because you're dealing with a large data. And then we get our SGD, which is smaller data, does better on smaller pieces of data. And I'm not going to go into all of these different optimizers. We didn't even use these in the actual demo. You just have to be aware that they are different optimizers. And the more you dig into these models, you'll hit a point where you do need to play with these a little bit. But for the most part, leave it at the default when you're first starting out. And we're doing just the sequential. You'll see here layers dense. And then if we come down a little bit more, when they put this together and they're running the dense layers, you'll also see they have dropout, they have flatten, they have activation, they have the convolutional layer 2D, max pooling 2D, batch normalization. What are all these layers? And when we get to the model, we're going to talk about them. A lot of times when you're just starting, you can just import Keras.layers, and then you have your dropout, your flatten, your convolutional neural network 2D. And we'll cover what these do in the actual example when we get down there. What I want you to take from here, though, is you need to run your imports and load your different aspects of this. And, of course, your TensorFlow TF, because this is all built on TensorFlow. And then finally, import random as RN, just for random generation. And then we get down here, we have our CV2. That is your open image, or your open CV, they call it, for processing images. That's what the CV2 is. We have our TQDM. The TQDM is for is a progress bar. Just a fancy way of adding, when you're running a process, you can view the bar going across in the Jupyter setup. Not really necessary, but it's kind of fun to have. We want to be able to shuffle some files. Again, these are all different things. PIL is another image processor. It goes with the CV2. A lot of times you'll see both of those. And so we run those. We've got to bring them all in. And the next thing is to set up our directories. And so when we come into the directories, there's an important thing to note on here, other than we're looking at a lot of flowers, which is fun. Is we get down here, we have our directory, archive flowers. That just happens to be where the different files for different flowers are put in. We're denoting an X and a Z. And the X is the date of the image, and the Z is the tag for it. What kind of flower is this? And the image size is really important because we have to resize everything. If you have a neural network, and if you remember from our neural networks, let me flip back to that slide. When we look at this slide, we have two input nodes here. With an image, you have an input node depending on how you set it up for each pixel. And that pixel has 3 different color schemes usually in it, sometimes 4. So if you have a picture that's 150 by 150, you multiply 150 times 150 times 3. That's how many nodes, input layers coming in. I mean, so this is a massive input. A lot of times you think, oh yeah, it's just a small amount of data or something like that. No, it's a full image coming in. Then you have your hidden layers. A lot of times they match what the image size is coming in. So each one of those is also just as big. And then we get down to just a single output. So that's kind of a thing to note in here, what's going on behind the scenes. And of course, each one of these layers has a lot of processes and stuff going on. And then we have our different directories on here. Let me go ahead and run that. So I'm just setting the directories. That's all this is. Archive flowers, daisy, sunflower, tulip, dandelion, rose. Just our different directories that we're going to be looking at. And then we want to go ahead and we need to assign labels. Remember, we defined X and Z. So we're just going to create a definition here. And the first thing is return flower type. Okay, it just returns it what kind of flower it is, I guess, assign the label to it. But we're going to go ahead and make our train data. And when you look at this, there's a couple things to take away from here. The first one is we're just appending right onto our NumPy array the image. We're going to let NumPy handle all that different aspects as far as 150 by 150 by 3. We just dump it right into the NumPy, which makes it really easy. We don't have to do anything funky on the processing, and we want to leave it like that. And I'm going to talk about that in a minute. And then, of course, we have to have the string, append the label on there. And I want you to notice right here, we're going to read the image in, and then we're going to size it. And this is important because we're just changing this to 150 by 150. We're resizing the image so it's uniform. Every image comes in identical to the other ones. This is something that's so important is when you're resizing or reformatting your data, you really have to be aware of what's going on. With images, it's not a big deal because with an image, you just resize it so it looks squishy or spread out or stretched. The neural network picks up on that and it doesn't really change how it processes it. So let's go ahead and run that. And now we've got our definition set up on there. And then we want to go ahead and make our training data. So make the train data daisy flower, daisy directory, print length of X. So here we go. Let's go ahead and run that. And we're just loading up the flower daisy. So this is going all in there, and it's adding it in to our setup on there, to our X and Z setup. And we see we have 769. And then, of course, you can see this nice bar here. This is the bar going across is that little added code in there that just makes it really cool for doing demos. Not necessarily when you're building your own model or something like that, but if you're going to display this to other people, adding that little, what was it called? TQDM. I can never remember that, but the TQDM module in there is really nice. And we'll go ahead and do sunflowers. And of course, you could have just created an array of these, but this has an interesting problem that's going to come up, and I want to show you something. It doesn't matter how good the people in the back are or how good you are at programming. Errors are going to come up, and you got to figure out how to handle them. And so when we get all the way down to the where is it? Dandelion. Here's our dandelion directory we're going to build. Jupyter has some cool things it does, which makes this really easy to deal with. But at the same time, you would want to go back in there depending on how many times you rerun this, how many times you pull this. So when you're finding errors going in here, there's a couple things you can do, and we're just going to, oh, it wasn't, no, there it is. There's our error. I knew there was an error. This processed 1,062 out of 1,065. Now, I can do a couple things. One, I could go back into our definition, and I can just put in here try, and so if it has a bad conversion, because this is where the error is coming from, just skip it. That's one way to do it. When you're doing a lot of work in data science and you look at something like this where you're losing 3 points of data at the end, you just say, okay, I lost 3 points. Who cares? Or you can go in there and try to delete it. It really doesn't matter for this particular demo. And so we're just going to leave that error right alone and skip over because it's already added all the other files in there. And this is a wonderful thing about Jupyter Notebook is that I can just continue on there and the X and Z, which we're creating, is still running, and we'll just go right into the next flower rows. So all these flowers are in there. That's just a cool thing about Jupyter Notebook. And then we can go ahead and just take a quick look and see what we're dealing with. And this is, of course, really, when you're dealing with other people and showing them stuff, this is just kind of fun where we can display it on the plot library here. And we're just going to go through and let's see what we got here. Looks like we're going to do like 5 of each of them, I think. Is that how they set this up? Plot library 5 by 2. Okay, oh, I see how they did it. Okay, so 2 each. So we have 5 by 2 set up on our axes, and we're just going to go in and look at a couple of these flowers. It's always a good thing to look at some of your data. No matter what you're doing, we've reformatted this to 150 by 150. You can see how it really blurs this one up here on the tulip. That is that resize to 150 by 150. And these are what's actually going in. These are all 150 by 150 images. You can check the dimensions on the side. And you can see just a quick sampling of the flowers we're actually going to process on here. And again, like I said at the beginning, most of your work in data science is reprocessing this different information. So we need to go ahead and take our labels and run a label encoder on there. And then we're just going to, LE is a label encoder. One of the things we imported, and then we always use the fit to categorical, y comma 5, x, here's our array, x. So if you look at this, here's our fit. We're going to transform z. That's our z array we created. And then we have y, which equals that. And then we go ahead and do to categorical. We want 5 different categories. And then we create our x, NP array of x. X equals x over 255. So what's going on here, there's 2 different transformations. One, we've turned our categories into 0, 1, 2, 3, 4, 5 as the output. And we have taken our x array. And remember, the x array is 3 values of your different colors. This is so important to understand. When we do this across a NumPy array, this takes every one of those 3 colors. So we have 150 by 150 pixels. Out of those 150 by 150 pixels, they each have 3 color arrays. And those color arrays range from 0 to 250. So when we take the x equals x over 255, range from 0 to 255, this converts all those pixels to a number between 0 and 1. And you really want to do that when you're working with neural networks. Now, if you do a linear regression model, it doesn't affect it as much, and so you don't have to do that conversion if you're doing straight numbers. But when you're running neural networks, if you don't do this, you're going to create a huge bias. And that means it'll do really good on predicting 1 or 2 things, and they'll just totally die on a lot of other predictions. So now we have our x and y values. X being the data in, y being our known output. And with any good setup, we want to divide this data into our training. So we have x train. We have our x test. This is the data we're not going to program the model with. And of course your y train corresponds to your x train, and your y test corresponds to your x test, the outputs. And this is, when we do the train test split, this was from the scikit, sklearn. We imported train test split. And we're just going to go ahead and do the test size at about a quarter of the data, 0.25. And of course, random's always good. This is such a good tool. I mean, certainly you can do your own division. You could just take the first 0.25 of the data or whatever, do the length of the data. Not real hard to do, but this is randomized so that if you're running this test a few times, you can kind of get an idea whether it's going to work or not. Sometimes what I will do is I'll just split the data into 3 parts, and then I'll test it on 2, with one being or I'll train it on 2 of those parts, with one being the test, and I rotate it. So I come up with 3 different answers, which is a good way of finding out just how good your model is. But for setting up, let's stick with the xtrain, xtest, and the sklearn package. And then we're going to go ahead and do a random seed. Now, a lot of times the Keras actually does this automatically, but we're going to go ahead and set it up on here. And you can see we did an NP random seed from 42, and we get a nice RN number. And then we do TF random, we set the seed. So you can set your randomness at the beginning of your TensorFlow. And that's what the tf.random.set is. So that's a lot of prep. All this prep, and then we finally get to the exciting part. This is where you probably spend, once you have the data prepped and you have your pipeline going and you have everything set up on there, this is the part that's exciting, is building these models. And so we look at this model. One, we're going to designate it as sequential. They have the API, which is the Keras TensorFlow API versus sequential. Sequential means we're going one layer to the next. So we're not going to split the layer and bring it back together. It looks almost the same with the exception of bringing it back together. So it's not a huge step to go from this to an API. And the first thing we're going to look at is our convolutional neural network in 2D. So what's going on here? There's a lot of stuff that's going on here. The default for, well, let's start with the beginning. What is a convolutional 2D network? Well, a convolutional 2D network creates a number of small windows, and those small windows float over the picture, and each one of them is their own neural network, and it's basically becomes like a categorization. And then it looks at that and it says, oh, if we add these numbers up a certain way, we can find out whether this is the right flower based on this little window floating around, which looks at different things. And we have filters 32. So this is actually creating 32 windows, is what that's doing. And the kernel size is 5 by 5. So we're looking at a 5 by 5 square. Remember, it's 150 by 150. So this narrows it down to a 5 by 5. It's a 2D, so it has your x, y coordinates. And when we look at this 5 by 5, remember each one of these is actually looking at 5 by 5 by 3. So we're actually looking at 15 by 15 different pixels. And padding is just, usually I just ignore that. Activation by default is ReLU. We went ahead and put the ReLU in there. There's a lot of different activations. ReLU is for your smaller, remember I mentioned atom, when you have a lot of data use an atom kind of activation, or use an atom processing. We're using the ReLU here. It kind of gives you a yes or no, but it doesn't give you a full yes or no. It has a 0 and then it kind of shoots off at an angle. Very common. It's the most common one. And then of course here's our input shape, 150 by 150 by 3 pixels. And then we have to pool it. So whenever you have a convolutional 2D layer, we have to bring this back together and pool this into a neural network. And then we're going to go ahead and repeat this. So we're going to add another network here. One of the cool things, if you look at this, is that as it comes in, it just kind of automatically assumes you're going down to the next layer. And so we have another convolutional neural network, 2D. Here's our max pooling again. We're going to do that again, max pooling. And we're just going to filter on down. Now, one of the things they did on this one is they changed the kernel size. They changed the number of filters. And so each one of these steps kind of looks at the data a little bit differently. And that's kind of cool because then you get a little added filtering on there. This is where you start playing with the model. You might be looking at a convolutional neural network, which is great for image classifications. When we get down to here, one of the things we see is flatten. So we just flatten it. Remember, this is 150 by 150 by 3. Well, and actually the pool size changes, so it's actually smaller than that. Flatten just puts that into a 1D array. So instead of being, a tensor of this really complexity with the pixels and everything, it's just flat. And then the dense is just another activation on there. By default, it is probably ReLU as far as this activation. And then, oh yeah, here we go. In sequential, they actually added the activation as ReLU. So this just, because this is sequential, this activation is attached to the dense. And there's a lot of different activations, but ReLU is the most common one. And then we also see a softmax. Softmax is similar, but it has its own kind of variation. And one of the cool things, you know what, let me bring this up, because if you don't know about these activations, this doesn't make sense. And I just did a quick Google search on images of TensorFlow activations. I should probably look at which website this is. But this is the output of the values. So as your x, as it adds in all those weighted x values going into the node, it's going to activate it a certain way. And that's a sigmoid activation. And you can see it goes between 0 and 1 and has a nice curve there. This also shows the derivatives. And if we come down, the 7 popular activation functions, nonlinear activations, there's a lot of different options on this. Let me see if I can find the... Oops, let me see if I can find the specific to ReLU. So this is a leaky ReLU. And you can see instead of it just being 0 and then a value between going up, it has a little leaky there. Otherwise, your ReLU loses some nodes. They just become inactive. But you can see there's a lot of different options here. Here's a good one right here with the ReLU. You can see the ReLU function on the upper left here. And then the leaky ReLU over here on the right, which is very commonly used also. One of the things I use with processing language is the exponential one, or the tangent h, the hyperbolic tangent, because they have that nice funky curve that comes in that has a whole different meaning and captures word use better. Again, these are very specific to domain, and you can spend a lot of time playing with different models. For our basic model, we'll stick to the ReLU and the softmax on here, and we'll go ahead and run and build this model. So now that we've had fun playing with all these different models that we can add in there, we need to go ahead and have a batch size on here, 128, epochs 10. This means that we're going to send 128 rows of data or flowers at a time to be processed. And the epochs 10, that's how many times we're going to loop through all the data. Reduce the values, and verbose equals 1 means that we're going to show what's going on. Value, monitor what we're monitoring. We'll see that as we actually train the model. This is what's going to come out of there. If you set the verbose equal to 0, you don't have to watch it train the model, although it is kind of nice to actually know what's going on sometimes. And since we're still working on bringing the data in, here's our batch size, here's our epochs, we need to go ahead and create a data generator. This is our image data generator. And it has all the different settings in here. Almost all of these are defaults. So if you're looking at this going, oh my gosh, this is confusing, most of the time you can actually just ignore most of this. Vertical flip, so you can randomly flip pictures, you can randomly horizontally flip them. You can shift the picture around. This kind of helps, gives you multiple data off of them. Zooming, rotation, there's all kinds of different things you can do with images. Most of these we're just going to leave as false. We don't really need to do all that setup because we already have a huge amount of data. If you're short data, you can start flipping like a horizontal picture and it will generate, it's like doubling your data almost. So the upside is you double your data. The downside is that if you already have a bias in your data, you already have 5,000 sunflowers and only 2 roses, that's a huge bias. It's also going to double that bias. That is the downside of that. And so we have our model compile, and this you're going to see on all the Keras. We're going to take this model here, we're going to take all this information as far as how we want it to go, and we're going to compile it. This actually builds the model, and so we're going to run that. And I want you to notice learning rate, very important. This is the default 001. You really don't. This is how slowly it adjusts to find the right answer. And the more data you have, you might actually make this a smaller number. If you have a very small sample of data, you might go even larger than that. And then we're going to look at the loss, categorical cross entropy, most commonly used. And this is how much it improves. The model's improving is what this number means. Or, yeah, that's important on there. And then the accuracy. We want to know just how good our model is on the accuracy. And then one of the cool things to do is if you're in a group of people who are studying the model, if you're in shareholders, you don't want to do this, is you can run the model summary. I do this by default, and you can see the different layers that you built into this model. Just a quick summary on there. So we went ahead and we're going to go ahead and create a, we'll call it history, but we want to do a model fit generator. And so what this history is doing is this is tracking what's going on while it fits the model. Now there's a lot of new setups in here where they just use fit and then you put the generator in here. We're going to leave it like this, even though the new default is a little different on that. Doesn't really matter, it does the same thing. And we'll go ahead and just run that. And you can see while it's running right here, we're going through the epochs. We have 1 of 10. Now we're going through 6 to 25. Here's our loss. We're printing that out so you can see how it's improving, and our accuracy. The accuracy gets better and better. And this is 6 out of 25. This is going to take a couple minutes to process because we are training 150 by 150 by 3 pixels across 6 layers or 8 layers, whatever it was. That is a huge amount of processing, so this will take a few minutes to process. This is when we talk about the hardware and the problems that come up in data science and why it's only now just exploding, being able to do neural networks. This is why. This process takes a long time. Now you should have seen a jump on the screen here because I did pause the recorder to let this go ahead and run all the way through its epochs. Let's go ahead and take a look and see what these epochs are. And if you set the verbose to 0 instead of 1, it won't show what's going on in the behind the scenes as it's training it. So when we look at this epoch, 10 epochs, we went through all the data 10 times. If I remember correctly, there's roughly a gig of data there, so that's a lot of data. The first thing you're going to notice is the 270 seconds. That's how much each of those epochs took to run. And so if you divide 60 in there, you roughly get about 5 minutes worth of each epoch. So if I have 10 epochs, that's 50 minutes, almost an hour of runtime. That's a big deal when we talk about processing. On this particular computer, I actually have, 8 cores with 16 dedicated threads. So it runs like a 16-core computer. It alternates the threads going in. And it still takes it 5 minutes for each one of these epochs. So you start to see that if you have a lot of data, this is going to be a problem if you have a number of models. You want to find out how good the models are doing and what model to use. And so each of those models could take all night to run. In fact, I have a model I'm running now that takes about a day and a half to test each model. It takes 4 days to do the whole data. So what I do is I actually take a small piece of the data, test it out to find out, get an idea of how the different setups are going to do, and then I increase that size of the data and then increase it again, and I can just take that curve and kind of say, okay, if the data is doing this, then I need to add in more dense layers or whatever. So you can do a small chunks of data and then figure out what it costs to do a large set of data and what kind of model you want. The loss, as we see here, continues to go down. This is the error. This is how much error is in there. It really isn't a user-friendly number other than the more it trends down, the better. And so if you continue to see the loss going down, eventually you'll get to the point where it stops going down and it goes up and down and kind of wavers a little bit. At that point, you know you've run too many epochs. You're starting to get a bias in there, and it's not going to give you a good model fit. The accuracy just turns this into something that we can use. And so the accuracy is what percentage of guesses, in this case it's categorical, so this is the percentage of guesses are correct. Value loss is similar, it's a minus a value loss. And then you have the value accuracy, and you'll see the value accuracy is pretty similar to the accuracy, just rounds it off basically. And so a lot of times you come down here and you go, okay, we're doing 0.5, 0.6, 0.7, and that is 70% accuracy, or in this case 68.59% accuracy. And that's a very usable number, and it's very important to have. If you're identifying flowers, that's probably good enough if you can get within a close distance and knowing what flower you're identifying. If you're trying to figure out whether someone's going to die from a heart attack or not, you might want to rethink it a little bit or rekey how you're building your model. So if I'm working with a group of clients, shareholders in a company or something like that, you don't really want to show them this. You don't want to show them, hey, this is what's going on with the accuracy. These are just numbers. And so we want to go ahead and put the finishing touches, just like when you are building a house and you put in the frame and the trim on the house. It's nice to have a nice view of what's going on. And so we'll go ahead and do a pie plot, and we'll just plot the history of the loss, the history of the value loss over here, epochs, train, and test. And so we're just going to compute these. This is really important. And what I want you to notice right here is when we get to about 5 epochs, a little more than 5, 6 epochs, you see a crossover here. And it starts crossing as far as the value loss. And what's going on here is you have the loss in your actual model and your actual data, and you have the value loss where it's testing it against the test data. The data wasn't used to program your model, wasn't used to train your model on. And so when we see this crossing over, this is where the bias is coming in. This is becoming overfitted. And so when you put these two together, right around 5 and 6, you start to see how it does this switch over here. And that's really where you need to stop, right around 5, 6. It's always hard to guess because at this point the model's kind of a black box. But you know that right around here, if you're saving your model after each run, you want to use the one that's right around 5 epochs because that's the one that's going to have the least amount of bias. So this is really important as far as guessing what's going on with your model and its accuracy and when to stop. It also is, I don't show people this mess up here. I show somebody this kind of model and I say this is where the training and the testing comes in on this model. It just makes it easier to see and people can understand what's going on. So that completes our demo, and you can see we did what we were set out to do. We took our flowers and we were able to classify them within about 68-70% accuracy, whether it's going to be a dahlia, sunflower, cherry blossom, rose. A lot of other things you can do with your output as far as different tables to see where the errors are coming from and what problems are coming up. And we're going to take a look at image classification using Keras and the basic setup. And we'll actually look at 2 different demos on here. What's in it for you today? What is image classification? Intel image classification data, creating neural networks with Keras, and the VGG16 model. What is image classification? The process of image classification refers to assigning classes to an entire image. Images can be classified based on different categories like whether it is a nighttime or daytime shot, what the image represents, etc. And you can see here we have mountains looking for mountains. We'll actually be doing some pictures of scenery and stuff like that. In deep learning, we perform image classification by using neural networks to extract features from images and classifies them based on these features. And you can see here where it says like what computer sees, and it says, oh yeah, we see mostly forest, maybe a little bit of mountains because of the way the image is. And this is really where one of the areas that neural networks really shines. If you try to run this stuff through more like a linear regression model, you'll still get results, but the results kind of miss a lot of things as the neural networks get better and better at what they do with different tools we have out there. So Intel image classification data. The data being used is the Intel image classification data set, which consists of images of 6 types of land areas. And so we have forest, building, glaciers, and mountains, sea, and street. And you can see here is a couple of the images out of there as a setup in the Intel image classification data that they use. And then we're going to go into creating a neural networks with Keras. The convolutional neural network that we are creating from scratch looks as shown below. You'll see here we have our input layer. They have it listed max pooling. So you have, as you're coming in with the input layer, and the input layer is actually before this, but the first layer that it's going to go into is going to be a convolutional neural network. Then you have a max pooling that pools the convolutional neural network's returns. In this case, they have 2 of those. That is very standard with convolutional neural networks. One of the ones that I was looking at earlier that was standard being used by one of the larger companies, I can't remember which one, for doing a large amount of identification, had 2 convolutional neural networks, each with their max pooling, and then about 17 dense layers after it. We're not going to do that heavy duty of a code, but we'll get you headed in the right direction. And that gives you an idea of what you're actually going to be looking at when you look at the flattened part and then the dense. We're talking like 17 dense layers afterwards. I find that a lot of the stuff I've been working on, I end up maxing it out right around 9 dense layers. It really depends on what you have going in and what you're working with. And the VGG16 model. VGG16 is a pre-trained CNN model which is used for image classification. It is trained on a large, varied data set and fine-tuned to fit image classification data sets with ease. And you can see down here we have the input coming in, the convolutional neural network 1-to-1, 1-to-2, and then pooling. And then we do 2-to-1, 2-to-2 convolutional neural network, then pooling, 3-to-2, and you can see there's just this huge layering of convolutional neural networks. And in this case, they have 5 such layers going in, and then 3 dense going out, or more. Now, when they took this setup, this actually won an award back in 2019 for this particular setup. And it does really good, except that, again, we only show the 3 dense layers here. And as you find out, depending on your data going in and what you have set up, that really isn't enough on one of these setups. And I'm going to show you why we restricted it, because it does take up a lot of processing power in some of these things. So let's go ahead and roll up our sleeves, and we're going to look at both the setups. We're going to start with the first classification, and then we'll go into the VGG16 and show you how that's set up. Now I'm going to be using Anaconda, and let me flip over to my Anaconda so you can see what that looks like. Now I'm running in the Anaconda here. You'll see that I've set up a main Python 3.8. I always put that in there because this is where I'm doing like most of my kind of playing around. This is done in Python version 3.8. We're not going to dig too much into versions. At this point you should already have Keras installed on there. Usually Keras takes a number of extra steps. And then our usual setup is the NumPy, the pandas, your scikit, which is going to be the sklearn, your Seaborn, and I'll show you those in just a minute. And then I'm just going to be in the Jupyter lab where I've created a new notebook in here. And let's flip on over there to my blank notebook. Now, there's a couple cool things to note in here is that, one, I use the Anaconda Jupyter notebook setup because it keeps everything separate, except for Keras. Keras is actually running separately in the back. I believe it's a C program. What's nice about that is that it utilizes the multiprocessors on the computer, and I'll mention that just in a little bit when we actually get down to running the code. And when we look in here, the couple things to note is here's our oops, I thought I grabbed the other drawing thing. But here's our NumPy and our pandas right here and our operating system. This is our scikit. You always import it as sklearn for the classification report. We're going to be using, well, usually import like Seaborn brings in all of your PyPlot library also. Kind of nice to throw that in there. I can't remember if we're actually using Seaborn, if they just, the people in the back just threw that together. And then we have the sklearn shuffle for shuffling data. Here's our matplot library that the Seaborn is pretty much built on. CV2, if you're not familiar with that, that is our image module for importing the image. And then, of course, we have our TensorFlow down here, which is what we're really working with. And then the last thing is just for visual effect while we're running this. If you're doing a demo and you're working with the partners or the shareholders, this TQDM is really kind of cool. It's an extensible progress bar for Python. And I'll show you that too. Remember, data science is not, I mean, most of this code, when I'm looking through this code, I'm not going to show half of this stuff to the shareholders or anybody I'm working with. They don't really care about pandas and all that. We do, because we want to understand how it works. So we need to go ahead and import those different setup on there. And then the next thing is we're going to go ahead and set up our classes. Now we remember if we had mountain, street, glacier, building, sea, and forest, those were the different images that we have coming in. And we're going to go ahead and just do class name labels, and we're going to kind of match that class name of I for I, class name equals the class names. So our labels are going to match the names up here. And then we have the number of classes, and print the class names and the labels. And we'll go ahead and set the image size. This is important that we resize everything, because if you remember with neural networks, they take one size data coming in. And so when you're working with images, you really want to make sure they're all resized to the same setup. It might squish them, it might stretch them. That generally does not cause a problem in these. And some of the other tricks you can do with, if you need more data, and this is one that's used regularly, we're not going to do it in here, is you can also take these images and not only resize them, but you can tilt them one way or the other, crop parts of them, so that they process slightly differently. And it'll actually increase your accuracy of some of these predictions. And so you can see here we have mountain equals 0. That's what this class name label is. Street equals 1. Glacier equals 2. Buildings equals 3. C4. Forest equals 5. Now, we did this as an enumerator, so each one is 0 through 5. A lot of times we do this instead as 0, 1, 0, 1, 0, 1, so you have 5 outputs and each one's a 0 or a 1 coming out. So the next thing we really want to do is we want to go ahead and load the data up, and just put a label in there, loading data. just so you know what we're doing, I'm going to put in the loading data down here, make sure it's well labeled. And we'll create a definition for this. And this is all part of your pre-processing. At this point, you could replace this with all kinds of different things depending on what you're working on. And once you download, you can go download this data set, send a note to the Simplilearn team here in YouTube, and they'll be happy to direct you in the right direction. And make sure you get this path here, so you have the right, wherever you saved it. A lot of times I'll just abbreviate the path or put it as a sub thing and just get rid of the directory. But again, double check your paths. We're going to separate this into a segment for training and a segment for testing. And that's actually how it is in the folder. And let me just show you what that looks like. So when I have my lengthy path here where I keep all my programming Simplilearn, this particular setup we're working on, image classification and image classification. Clearly you probably wouldn't have that lengthy of a list. And when we go in here, you'll see sequence train, sequence test. They've already split this up. This is what we're going to train the data in. And again, you can see buildings, forest, glacier, mountain, sea, street. And if we double click, let's go under forest. You can see all these different forest images. And there's a lot of variety here. I mean, we have wintertime, we have summertime. So it's kind of interesting. You know, here's like a fallen tree versus a road going down the middle. That's really hard to train. And if you look at the buildings, a lot of these buildings, you're looking up a skyscraper, we're looking down the setup. Here's some trees with one. I want to highlight this one. It has trees in it. Let me just open that up so you can see it a little closer. The reason I want to highlight this is I want you to think about this. We have trees growing. Is this the city or a forest? So this kind of imagery makes it really hard for a classifier. And if you start looking at these, you'll see a lot of these images do have trees and other things in the foreground, weird angles. Really a hard thing for a computer to sort out and figure out whether it's going to be a forest or a city. And so in our loading of data, we have to have the path, the directory. We're going to come in here, we have our images and our labels. So we're going to load the images in one section, the labels in another. And if you look through here, it just goes through the different folders. In fact, let me do this. There we go. As we look at this, we're just going to loop through the 6 different folders that have the different landscapes. And then we're going to go through and pull each file out and each label. So we set the label, we set the folder for file and list. Here's our image path, join the paths. This is all kind of general stuff, so I'm kind of skipping through it really quick. And here's our image setup. If you remember, we're talking about the images. We have our CV2 reader, so it reads the image in. It's going to go ahead and take the image and convert it to from blue, green, red to red, green, blue. This is a CV2 thing. Almost all the time it imports it, and instead of importing it as a standard that's used just about everywhere, it imports it with the BGR versus RGB. RGB is pretty much a standard in here. You have to remember that was CV2. And then we're going to go ahead and resize it. This is the important part right here. We've decided what the size is, and we want to make sure all the images have the same size on them. And then we just take our images and we're just going to append the image, append the label, and then the images is going to turn into a numpy array. This just makes it easier to process and manipulate. And then the labels is also a numpy array. And then we just return the output, append images and labels, and we return the output down here. So we've loaded these all into memory. We haven't talked much. There'd be a different setup in there because there is ways to feed the files directly into your Keras model. But we want to go ahead and just load them all because it's really, for today's processing and what our computers can handle, that's not a big deal. And then we go ahead and set the train images, train labels, test images, test labels, and that's going to be returned in our output append. And you can see here we did images and labels set up in there, and it just loads them in there, so we'll have these 4 different categories. Let me just go ahead and run that. So now we've gone ahead and loaded everything on there. And then if you remember from before, we imported, let me just go back up there, shuffle. Here we go. Here's our sklearn utilities import shuffle. And so we want to take these labels and shuffle them around a little bit, just mix them up so it's not having the same, if you run the same process over and over, then you might run into some problems on there. And just real quick, let's go ahead and do a plot so we can just, we've looked at them as far as from outside of our code. We pulled up the files and I showed you what that was going on. We can go ahead and just display them here too. And I tell you, when you're working with different people, this should be highlighted right here. This thing is like when I'm working on code and I'm looking at this data and I'm trying to figure out what I'm doing, I skip this process. The second I get into a meeting and I'm showing what's going on to other people, I skip everything we just did. So, and go right to here where we want to go ahead and display some images and take a look at it. And in this display, I've taken them and I've resized the images to 20 by 20. That's pretty small. So we're going to lose just a massive amount of detail. And you can see here these nice pixelated images. I might even just stick with the folder showing them what images we're processing. Again, this is, you gotta be a little careful of this. Maybe resizing it was a bad idea. In fact, let me try it without resizing it and see what happens. Oops. So I took out the image size and then we put this straight in here. one of the things, again, this is, put the D, there we go. One of the things, again, that we want to note whenever we're working on these things is the CV2, there are so many different image classification setups. It's really a powerful package when you're doing images. But you do need to switch it around so that it works with the pyplot. And so make sure you take your NumPy array and change it to a uinteger8 format, because it comes in as a float. Otherwise you'll get some weird images down there. And so this is just basically we've created a plot. We went ahead and did the plot 20 by 20, or the plot figure size is 20 by 20. And then we're doing 25, so a 5 by 5 subplot. Nothing really going on here too exciting, but you can see here where we get the images. And really, when you're showing people what's going on, this is what they want to see. So you skip over all the code and you have your meeting, you say, okay, here's our images of the building. Don't get caught up in how much work you do, get caught up in what they want to see. So if you want to work in data science, that's really important to know. And this is where we're going to start having fun. Here's our model. This is where it gets exciting when you're digging into these models. And you have here, there we go. When you have here, if you look here, here's our convolutional neural network 2D. And 2D is an image. You have two different dimensions, X, Y, and even though there's three colors, it's still considered 2D. If you're running a video, you'd be convolutional neural network 3D. If you're doing a series going across, a time series, it might be 1D. And on these, you need to go ahead and have your convolutional neural network. If you look here, there's a lot of really cool settings going on to dig into. We have our input shape, so everything's been set to 150 by 150. And it has, of course, 3 different color schemes in it. That's important to notice. Activation default is ReLU. This is small amounts of data being processed on a bunch of little neural networks. And right here is the 32. That's how many of these convolutional neural networks are being strung up on here. And then the 3 by 3, when it's doing its steps, it's actually looking at a little 3 by 3 square on each image. And so that's what's going on here. And with convolutional neural networks, the window floats across and adds up all these numbers going across on this data. And then eventually it comes up with 30, in this case, 32 different feature options that it's looking for. And of course, you can change that 32. You can change the 3 by 3, so you might have a larger setup. And, you know, if you're going across 150 by 150, that's a lot of steps. So we might run this as 15 by 15. There's all kinds of different things you can do here. We're just putting this together. Again, that would be something you would play with to find out which ones are going to work better on this setup. And there's a lot of play involved. That's really where it becomes an art form, is guessing at what that's going to be. The second part I mentioned earlier, and I can only begin to highlight this. When you get to these dense layers, one is the activation is a ReLU. They use a ReLU and a softmax here. It's a whole setup just explaining why these are different. And how they're different, because there's also an exponential, there's a tangent. In fact, there's just a ton of these, and you can build your own custom activations depending on what you're doing. A lot of different things go into these activations. There are 2 or 3 major thoughts on these activations, and ReLU and softmax are, ReLU, you're really looking at just the number, you're adding all the numbers together, and you're looking at Euclidean geometry. AX plus BX2 plus CX3 plus bias. With softmax, this belongs to the party of it's activated or it's not, except they call it softmax because when you get to 0, instead of it just being 0, it's actually a little bit less than 0, so that when it trains, it doesn't get lost. There's a whole series of these activations. Another activation is the tangent, where it just drops off and you have like a very narrow area where you have from -1 to 1, or exponential, which is 0 to 1. So there's a lot of different ways to do the activation. Again, we can do, that'd be a whole separate lesson on here. We're looking at the convolutional neural network, and we're doing the two pools. This is so common. You'll see two convolutional neural networks stacked on top of each other, each with its own max pool underneath. And let's go ahead and run that. So we built our model there, and then we need to go ahead and compile the model. So let's go ahead and do that. We are going to use the Atom optimizer. The bigger the data, the Atom fits better on there. There's some other optimizer, but I think Atom's a default. I don't really play with the optimizer too much. That's like once you get a model that works really good, you might try some different optimizers, but Atom's usually the most. And then we're looking at loss. Pretty standard. We want to minimize our loss. We want to maximize the loss of error. And then we're going to look at accuracy. Everybody likes the accuracy. I'm going to tell you right now, I start talking to people and I'm like, okay, what's the loss on this and that? And as a data science, yeah, I want to know how what's going on with that, and we'll show you why in a minute. But everybody wants to see accuracy. They want to know how accurate this is. And then we're going to run the fit. And I wanted to do this just so I can show you, even though we're in Python setup in here where Jupyter Notebook is using only a single processor, I'm going to bring over my little CPU tool. This is 8 cores on 16 dedicated threads, so it shows up as 16 processors. And actually I got to run this and then move it over. So we're going to run this, and hopefully it doesn't destroy my mic. And as it comes in, you can see it's starting to go through the epochs. And I set it for 5 epochs. And then this is really nice because Keras uses all the different threads available. So it does a really good job of doing that. This is going to take a while. If you look at here, it's ETA 2 minutes and 25 seconds, 24 seconds. So this is roughly 2.5 minutes per epoch. And we're doing 5 epochs. So this is going to be done in roughly 15 minutes. I don't know about you, but I don't think you want to sit here for 15 minutes watching the green bars go across. So we'll go ahead and let that run. And there we go. There was our 15 minutes. It's actually less than that because I did, when I went in here, realize that, where was it? Here we go. Here's our model compile. Here's our model fit. And here's our epochs. So I did 4 epochs. So a little bit better, a little more like 10 to 11 minutes instead of doing the full 15. And when we look at this, here's our model. We talked about the compiler. Here's our history. We're going to history equals the model fit. We'll go into that in just a minute. And what we're looking at is we have our epochs. Here's our validation split. So as we train it, we're weighing the accuracy versus, you kind of pull some data off to the side while you're training it. And the reason we do that is that you don't want to overfit. And we'll look at that chart in just a minute. Here's batch size. This is just how many images you're sending through at a time. The larger the batch, it actually increases the processing speed. And there's reasons to go up or down on the batch size because of the smaller the batch. There's a certain point where you get too large of a batch and it's trying to fit everything at once. So 128 is kind of big. Depends on the computer you're on and what it can handle. And then of course we have our train images and our train labels going in, telling it what we're going to train on. And then we look at our 4 epochs here. Here's our accuracy. We want the accuracy to go up, and we get all the way up to 0.83 or 83%. This is actual percentage based pretty much. And we can see over here our loss. We want our loss to go down. It really fluctuates. 55, 1.2, 0.77, 0.48. So we have a lot of things going on there. Let's go ahead and graph those. Turn that up. And our team in the back did a wonderful job of putting together this basic plot setup. Here's our subplot coming in. We're going to be looking at, from the history, we're going to send it the accuracy and the value accuracy labels and set up on there. And we're going to also look at loss and value loss. So you can see what this looks like. What's really interesting about this setup, and let me just go ahead and show you, because without actually seeing the plots, it doesn't make a whole lot of sense. It's just basic plotting of the data using the PyPlot library. And I want you to look at this. This is really interesting. When I ran this the first time, I had very different results. And they vary greatly. And you can see here our accuracy continues to climb. And there's a crossover here. Put it in here. Right here's our crossover. And I point that out because as we get to the right of that crossover where our accuracy, and we're like, oh yeah, I got 0.8%, we're starting to get an overfit here. That's what this switchover means. As our value, as a training set versus the value accuracy stays the same. And so that this is the one we actually really want to be aware of. And where it crosses is kind of where you want to stop at. And we can see that also with the train loss versus the value loss right here. We did one epoch, and look how it just flatlines right there with our loss. So really, one epoch is probably enough. And you're going to say, wow, okay, 0.8%. Certainly, if I was working with the shareholders, telling them that it has an 80% accuracy isn't quite true. And we'll look at that a little deeper. It really comes out here that the accuracy of our actual values is closer to 0.41% right here, even after running it this number of times. And so you really want to stop right here at that crossover. One epoch would have been enough. So the data is a little overfitted on this when we do 4 epochs. And, oops, there we are. Okay. My drawing won't go away. Let me see if I can get, there we go. For some reason, I've killed my drawing ability and my recorder. All right, took a couple extra clicks. So let's go ahead and take a look at our actual test loss. So you see where it crosses over. That's where I'm looking at. That's where we start overfitting the model. And this is where, if we were going to go back and continually upgrade the model, we would start taking a look at the images and start rotating them. We might start playing with the convolutional neural network instead of doing the 3x3 window. We might expand that, or find different things that might make a big difference as far as the way it processes these things. So let's go ahead and take a look at our test loss. Now remember, we had our training data. Now we're going to look at our test images and our test labels for our test loss here. And this is just model evaluate, just like we did fit up here. Where was it? One more. Model fit with our training data going in. Now we're going to evaluate it on the, and this data has not been touched yet. So this model's never seen this data. This is on completely new information as far as the model is concerned. Of course, we already know what it is from the labels we have. And this is what I was talking about. Here's the actual accuracy right here, 0.48 or 4847. So this 49% of the time guesses what the image is. And I mean, really, that's the bottom dollar. Does this work for what you're needing? Does 49% work? Do we need to upgrade the model more? In some cases, this might be, what was I doing? I was working on stock evaluations, and we were looking at what stocks were the top performers. Well, if I get that 50% correct on top performers, I'm good with that. That's actually pretty good for stock evaluation. In fact, the number I had for stock was more like 30-something% as far as being a top performer stock. Much harder to predict. But at that point, you're like, well, you'll make money off of that. So again, this number right here depends a lot on the domain you're working on. And then we want to go ahead and bring this home a little bit more as far as looking at the different setup in here. And one of the, from sklearn, if you remember, actually let's go back to the top, we had the classification report. And this came in from our sklearn or scikit setup. And that's right here. You can see it right here on the, see, there we go, classification report right here. sklearn metrics import classification report. That's what we're going to look at next. A lot of this stuff depends on who you're working with. So when we start looking at precision, you know, this is like for each value, I can't remember what one was probably mountains. So if 44% is not good enough, if you're doing like you're in the medical department and you're doing cancer, is this cancerous or not? And I'm only 44% accurate. Not a good deal. You know, I would not go with that. So it depends on what you're working with on the different labels and what they're used for. Facebook, you know, 44%. I'm guessing the right person. I would hope it does a little bit better than that. But here's our main accuracy. This is what almost everybody looks at. They say, oh, 48%, that's what's important. Again, it depends on what domain you're in and what you're working with. And now we're going to do the same model. Oops, somehow I got my, there it goes. I thought I was going to get stuck on there again. This time we're going to be using the VGG16. And remember, this one has all those layers going into it. So it's basically a bunch of convolutional neural networks getting smaller and smaller on here. And so we need to go ahead and import all our different stuff from Keras. We're importing the main one is the VG16 setup on there. Just aim that, there we go. There's kind of a pre-processing images, applications, pre-process input. This is all part of the VGG16 setup on there. And once we have all of those, we need to go ahead and create our model. And we're just going to create a VGG16 model in here. Inputs, model inputs, outputs, model inputs. I'm not going to spend as much time as I did on the other one. We're going to go through it really quickly. One of the first things I would do is, if you remember in Keras, you can treat a model like you would a layer. And so at this point, I would probably add a lot of dense layers on after the VGG16 model and create a new model with all of those things in there. And we'll go ahead and run this because here's our model coming in and our setup. And it'll take it just a moment to compile that. Hey, what's funny about this is I'm waiting for it to download the package. Since I pre-ran this, it takes it about a couple minutes to download the VGG16 model into here. And so we want to go ahead and train features for the model. We're going to predict the train images, and we're going to test features on the predict test images on here. And then I told you I was going to create another model too, and the people in the back did not disappoint me. They went ahead and did just that. And this is really an important part. This is worth stopping for. I told you I was going to go through this really quick. So here's our, we have our model 2 coming in. And we've created a model up here with the VGG16, model equals model inputs, model inputs. And so we have our VGG16. This has already been pre-programmed. And then we come down here. I want you to notice on this right here, model 2 layers -4 to 1, x layer x. We're basically taking this model and we're adding stuff onto it. And so we've just basically duplicated this model. We could have done the same thing by using model up here as a layer. We could have had the input go to this model and then have that go down here. So we've added on this whole setup this whole block of code from 13 to 17, has been added on to our VGG16 model. And we have a new model with the layer input and X down here. Let's go ahead and run that and compile it. And that was a lot to go through right there. When you're building these models, this is the part that gets so complicated that you get stuck playing in, and yet it's so fun. It's like a puzzle. How can I loop these models together? And in this case, you can see right here that the layers, we're just copying layers over and adding each layer in. This is one way to build a new model. And we'll go ahead and run that. Like I said, the other way is you can actually use the model as a layer. I've had a little trouble playing with it. Sometimes when you're using the straight model over, you run into issues. And it seems like it's going to work, and then you mess up on the input and the output layers. There's all kinds of things that come up. Let's go ahead and do the new model. We're going to compile it. Again, here's our metrics: accuracy, sparse categorical loss. Pretty straightforward, just like we did before. You got to compile the model. And just like before, we're going to create a history. The history is going to be new model fit train 128. And just like before, if you remember when we started running this stuff, we're going to have to go ahead and it's going to light up our setup on here. And this is going to take a little bit to get us all set up. It's not going to just happen in a couple minutes. So let me go ahead and pause the video and run it, and then we'll talk about what happened. Okay, now when I ran that, these actually took about 6 minutes each. So it's a good thing I put it on hold. We did 4 epochs. I actually had to stop it because it was at 10 and switch it to 4 because I didn't want to wait an hour. And you can see here our accuracy and our loss numbers going down. And just at a glance, it actually performed, if you look at the accuracy, 0.2658. So our accuracy is going down, or 26%, 34%, 35%. And you can see here at some point it just kind of kicks the bucket. Again, this is overfitting. That's always an issue when you're running on programming these different neural networks. And then we're going to go ahead and plot the accuracy history. We built that nice little subroutine up above, so we might as well use it. And you can see it right here. There's that crossover again. And if you look at this, look how the red shifts up, how our loss functions and everything crosses over. We're overfitting. After one epoch, we're clearly not helping the problem or doing better. It's just gonna baseline. This one actually shows with the training versus the loss, value loss. Maybe second epoch. So on here, we're now talking more between the first and the second epoch, and that also shows kind of here. So somewhere in here, it starts overfitting. And right about now, you should be saying, uh-oh, something went wrong there. I thought that when we went up here and ran this, look at this. We have the accuracy up here is hitting that 48%, and we're down here. You look at the score down here, that looks closer to 20%, not nearly anywhere in the ballpark of what we're looking for. And we'll go ahead and run it through the actual test features here. And there it is. We actually run this on the unseen data and everything. 0.18 or 18%. I don't know about you, but I wouldn't want, at 18%, this did a lot worse than the other one. I thought this was supposed to be the super model, the model that beats all models, the VGG16 that won the awards and everything. Well, the reason is that one, we're not pre-processing the data, so it needs to be more. There needs to be more as far as like rotating the data at 45-degree angle, taking partials of it, so you can create a lot more data to go through here. And that would actually greatly change the outcome on here. And then we went up here, we only added a couple dense layers. We added a couple convolutional neural networks. This huge pre-trained setup is looking for a lot more information coming in as far as how it's going to train. And so this is one of those things where I thought it would have done better, and I had to go back and research it and look at it and say, well, why didn't this work? Why am I getting only 18% here instead of 44% or better? And that would be why, is it doesn't have enough training data coming in. And again, you can make your own training data. So it's not that we have a shortage of data, it's that some of that has to be switched around and moved around a little bit. And this is interesting right here too. If you look at the precision, we're getting it on number 2, and yet we had 0 on everything else. So for some reason, it's not seeing the different variables in here. So it'd be something else to look in and try to track down. And that probably has to do with the input. But you can see right here, we have a really good solid 0.48 up here. And that's where I'd really go with, is starting with this model. And then we look at this model and find out, why are these numbers not coming up better? Is it the data coming in? Where's the setup on there? And that is the art of data science right there, is finding out which models work better and why.
So if you want to seek expertise in deep learning skills and aspire to be a part of cutting-edge field of building chatbots and service bots using deep learning, our Caltech postgraduate program in AI and machine learning provides comprehensive coverage of the latest tools and technologies within the AI ecosystem. It offers masterclasses led by esteemed Caltech faculty and IBM experts, engaging hackathons, and interactive Ask Me Anything sessions. By enrolling in this program, delivered in partnership with IBM, you will gain the expertise needed to become a professional in AI and ML. This comprehensive artificial intelligence course will equip you with the knowledge about various AI-based technologies, empowering you to excel in this field. So do check out the course link in the description for more details. Let's get started now.
Now, let's talk about our first deep learning project. We have image classification using the CIFAR-10 dataset. Now this dataset was created by the Canadian Institute for Advanced Research. The CIFAR-10 dataset contains 60,000 32x32 color images in 10 different classes. The 10 different classes are airplanes, cars, birds, cats, deer, and others, which you can see on the screen. There are 6,000 images of each class. Now there are 50,000 training images and 10,000 test images. You can build a convolutional neural network model using the Keras library to classify each image into a category. So it is more of an image recognition kind of a project that is recommended for beginners who are new to deep learning. The next project in our list is brain tumor detection. Such projects are heavily used in the healthcare industries for detecting diseases before they occur. Brain tumors are the consequence of abnormal growths and uncontrolled cell division in the brain. They can lead to death if they are not detected early and accurately. Brain tumors can be classified into 2 types, benign and malignant. Deep learning can help radiologists in tumor diagnostics without invasive measures. A deep learning algorithm that has achieved significant results in image segmentation and classification is the convolutional neural network. It can be used to detect a tumor through brain using magnetic resonance imaging or MRI. Image pixels are first fed as input to the CNN. Softmax fully connected layers are used to classify the images. The accuracy of the convolutional neural network can be obtained with the radial basis function classifier. Next, we have Anna chatbot. Now this chatbot is the world's first open source conversation platform which comes with a graphical chart flow designer and chat simulator. Its supported channels are WebChat, Android, iOS and Facebook Messenger. The Anna chatbot is available to answer your questions 24 hours a day, 365 days a year. Anna is free for personal and commercial use. With the Anna Studio, server, simulator and SDK, which is software development kit, your development time is cut from days to hours. Using Anna, you can create chatbots to suit your needs. Chatbots play an important role in customer support for an e-commerce website. You can share real-time order and shipping updates, personalized product recommendations, and targeted offers within the conversation. Similarly, automobile brands, showrooms, and service centers can use a chatbot for lead generation, scheduling test drives, and roadside assistance. You can check the GitHub repository that's on the screen to know more about working on this project. The next project we have in deep learning is image captioning. Now, image captioning is the process of generating textual description of an image. It uses both methods from computer vision to understand the content of the image and a language model from the field of natural language processing to turn the understanding of the image into words in the right order. Microsoft has built its own caption bot where you can upload an image or the URL of an image and it will display the textual description of the image. On the screen, you can see we have the picture of Elon Musk, and the caption bot has generated a description that says, "I think it's Elon Musk wearing a suit and a tie, and he seems..." It ends with an emoticon. Another such application that suggests a perfect caption and best hashtags for a picture is Caption AI. Automatic image caption generation software can be built using recurrent neural networks and long short-term memory networks or LSTMs. Now, we have image colorization as our next project. Image colorization has seen significant advancements using deep learning. Image colorization is the process of taking an input of a grayscale image and then producing an output of a colored image or a colorized image. Colorization is a highly undetermined problem that requires mapping a real valued luminance image to a three-dimensional colored value 1 that has not a unique solution. ChromaGAN is an example of a picture colorization model. A generative network is framed in an adversarial model that learns to colorize by incorporating perceptual and semantic understanding of color and class distributions. The model is trained using a fully supervised strategy. If you want to implement ChromaGAN, check the GitHub link that's on the screen below. Next in our list of projects we have OpenNMT machine translation. OpenNMT is an open source ecosystem for neural machine translation and neural sequence learning. It started in December 2016 by the Harvard NLP Group and Sistran. The project has since been used in several research and industry applications. Neural machine translation, or NMT, is a new methodology for machine translation that has led to significant improvements, particularly in terms of human evaluation, compared to rule-based and statistical machine translation systems. OpenNMT provides implementations in two popular deep learning frameworks, Pytorch and TensorFlow. Please feel free to refer to the below GitHub link to learn more about neural machine translation. Now, we have music generation. Using deep learning, it is possible for a machine to learn the notes, structures, and patterns of music and start producing music automatically. Music 21 is a Python toolkit used for computer-aided musicology. It allows us to teach the fundamentals of music theory, generate music examples, and study music. The toolkit provides a simple interface to acquire the music notation of MIDI files, which stands for Musical Instrument Digital Interface. Using WaveNet architecture and long short-term memory networks, you can generate music without human intervention. Amper Music, MuBut, and JukeDeck produce smart music powered by deep learning algorithms. Then we have AlphaGo. Now AlphaGo was created by Google DeepMind and is the first computer program to defeat a professional human Go player. AlphaGo's algorithm uses a combination of machine learning and tree search techniques combined with extensive training both from human and computer play. It uses Monte Carlo tree search guided by a value network and a policy network, both implemented using deep neural network technology. AlphaGo was initially trained to mimic human play by attempting to match the moves of expert players from recorded historical games. It was done using a database of around 30 million moves. Once it had reached a certain degree of proficiency, by being set to play large number of games against other instances of itself, using reinforcement learning to improve its play. Next in our list of projects we have DeepDream. DeepDream is a computer vision program which uses a convolutional neural network to find and enhance patterns in images via algorithmic pareidolia. It then creates a dream-like hallucinogenic appearance in the overprocessed images. DeepDream is an experiment that visualizes the patterns learned by a neural network. Similar to when a child watches clouds and tries to interpret random shapes, DeepDream overinterprets and enhances the patterns it sees in an image. Do check the given GitHub link to install dependencies listed in the notebook and play with the code locally. Then we have Deep Voice. Deep Voice was developed by Baidu, which is an AI system that can clone an individual's voice. The trained model takes just 3 seconds to replicate the output of a person's voice. Deep Voice 3 is a fully convolutional attention-based neural text-to-speech system that converts text to spectrograms or other acoustic parameters to be used with an audio waveform synthesis method. Below you can find the GitHub link for Pytorch implementation of convolutional networks based text-to-speech synthesis models. Now we have IBM Watson. IBM Watson helps run machine learning models anywhere across any cloud. Using IBM Watson machine learning, you can build analytical models and neural networks trained with your own data that you can deploy for use in applications. With its open, extensible model operation, Watson machine learning helps businesses simplify and harness AI at scale across any cloud. It is used in healthcare, teaching assistant, chatbot, as well as for weather forecasting. And finally, in our list of deep learning projects, we have the YOLO real-time object detection. You only look once, or YOLO, is a state-of-the-art real-time object detection system. It frames object detection in images as a regression problem to spatially separated bounding boxes and associated class probabilities. Using this approach, a single neural network divides the image into regions and predicts bounding boxes and probabilities for each region. The neural network predicts bounding boxes and class probabilities directly from full images in one evaluation. The base YOLO model processes images in real time at 45 frames per second. You can use the COCO dataset and TensorFlow library to train and test the model. To learn more about YOLO object detection, check the GitHub link that's shown on the screen below.
So if you want to seek expertise in deep learning skills and aspire to be a part of cutting-edge field of building chatbots and service bots using deep learning, our Caltech postgraduate program in AI and machine learning provides comprehensive coverage of the latest tools and technologies within the AI ecosystem. It offers masterclasses led by esteemed Caltech faculty and IBM experts, engaging hackathons, and interactive Ask Me Anything sessions. By enrolling in this program, delivered in partnership with IBM, you will gain the expertise needed to become a professional in AI and ML. This comprehensive artificial intelligence course will equip you with the knowledge about various AI-based technologies, empowering you to excel in this field. So do check out the course link in the description for more details. Let's get started now.
Deep learning interview questions. And we're going to go from the very basics of neural networks and deep learning into some of the more commonly used models, so that you can have an understanding of what kind of questions are going to come up and what you need to know in interview questions. We'll start with a very general concept of what is deep learning. This is where we take large volumes of data, in this case on cats and dogs or whatever. A lot of times you use a training setup to train your model. Remember, it's kind of like a magic black box going on there. And then we use that to extract features or extract information, and in this case classify the image of a cat and a dog. So the primary takeaway when we're talking about deep learning is it learns from large volumes of structured and even unstructured data and uses complex algorithms to train neural network. It also performs complex operations to extract hidden patterns and features. And if we're going to discuss deep learning in this very simplified overview, then we also have to go over what is a neural network. This is a common image you'll see of a drawing of a forward propagation neural network. And it's a human brain inspired system which replicate the way humans learn. So this is inspired how our own neurons in our brain fire, but at a much simplified level. Obviously it's not ready to take over the human population and be our leader yet, not for many years. It's very much in its infant stage. But it's inspired by how our brains work. And they use a lot of other inspirations. You can study brains of moths and other animals that they've used to figure out how to improve these neural networks. The most common one consists of 3 layers of network, and this is generally how you view these networks, is you have an input, you have a hidden layer, and an output. And the neural network is broken up into many pieces, but when we focus just on the neural network, it's always on the hidden layers that we're making all the adjustments and figuring out how to best set up those hidden layers for their functions to both train faster and to function better. When we look at this, of course, we have our input, hidden, and output. Each layer contains neurons called as nodes that perform various operations. And you can see here we have the list of the nodes. We have both our input nodes and our output nodes, and then our hidden layer nodes. And it's used in deep learning algorithm like CNN, RNN, GAN, etc. We'll address some of these models a little closer, at least the most common models, as we go down the list and we study the deep learning and the neural network framework. Let's start with what is a multi-layer perceptron, or MLP, a lot of time is referred to. And you'll see these abbreviations. I'll be honest, I have to write them down on a piece of paper and go through them because I never remember what they all mean, even though I play with them all the time. What is a multi-layer perceptron? Well, if you look at the image on the right, it's very similar to what we just looked at. You have your input layer, your hidden layer, and your output layer. And that's exactly what this is. It has the same structure of a single layer perceptron with one or more hidden layers, except the input layer. Each node in the other layers uses a nonlinear activation function. What that means is your input layer is your data coming in, and then your activation function is based upon all those nodes and weights being added together, and then it has the output. MLP uses supervised learning method called backpropagation for training the model. Very key word there is backpropagation. Single layer perceptron can classify only linear separable classes with binary output, 0, 1, but the MLP can classify nonlinear classes. So let's break this down just a little bit. The multi-layer perceptron with an input layer and a hidden layer and an output layer. As you see that it comes in there, it adds up all the numbers and weights depending on how your setup is, that then goes to the next layer, that then goes to the next hidden layer if you have multiple hidden layers, and finally to the output layer. The backpropagation takes the error that it sees. So whatever the output is, it says, hey, this has an error to it, it's wrong. And then sends that error backwards from where it came from. And there's a lot of different functions used to train this based on that error and how that error goes backwards in the nodes. So forward is you get your answers, backward is for training. You see this every day. Even my Google Pixel phone has this. They train the neural network, which takes a lot more data to train than it does to use. And then they load up that neural network into, in this case I have a Pixel 2, which actually has a built-in neural network for processing pictures. And so it's just the forward propagation I use when it processes my photos. But when they were training it, it used the back propagation to train it with the errors they had. We'll be coming back to different models that are used. For right now, though, multi-layer perceptron, MLP. Put that down as your vocabulary word. And, of course, back propagation. What is data normalization and why do we need it? This is so important. We spend so much time in normalizing our data and getting our data clean and setting it up. So when we talk about data, there's a pre-processing step to standardize the data. So whatever we have coming in, we don't want it to be a 1 gigabyte file here, a 2 gigabyte picture here, and a 3 kilobyte text there. Even as a human, I can't process those all in the same group. I have to reformat them in some way that loops them together so that it's standardized format. We use this data normalization in pre-processing to reduce it and eliminate data redundancy. A lot of times the data comes in and you end up with two of the same images or the same information in different formats. Then we want to rescale values to fit into a particular range for achieving better convergence. What this means is with most neural networks, they form a bias. We've seen this recently in attacks on neural networks where they light up one pixel or one piece of the view and it skews the whole answer. So suddenly, because one pixel is really bright, it doesn't know what to do. Well, when we start rescaling it, we put all the values between, say, -1 and 1, and we change them and refit them to those values. It helps get rid of that bias, helps fix for some of those problems. And then finally, we restructure the data and improve the integrity. We want to make sure that we're not missing values or we don't have partial data coming in. One way to look at this is bad data in, bad data out. So you want clean data in and you want good answers coming out. One of the most basic models used is a Boltzmann machine. So let's address what is a Boltzmann machine. And if you know, we just did the MLP, multi-layer perceptron. So now we're going to come into almost a simplified version of that. And in this we have our visible input layer and we have our hidden layer. The Boltzmann machines are almost always shallow. They're usually just two-layer neural nets that make stochastic decisions whether a neuron should be on or off. True, false, yes, no. First layer is the visible layer and second layer is the hidden layer. Nodes are connected to each other across layers, but no two nodes of the same layer are connected. Hence it is also known as restricted Boltzmann machine. Now that we've covered a basic MLP or multi-layer perceptron, and we've gone over the Boltzmann machine, also known as the restricted Boltzmann machine, let's talk a little bit about activation formulas. And this is a huge topic that can get really complicated, but it also is automated, so it's very simple. So you have both a complicated and a simple at the same time. So what is the role of activation functions in a neural network? Activation function decides whether a neuron should be fired or not. That's the most basic one. And that actually changes a little bit because it's either whether it's fired or not, in this case activation function, or what value should come out when it's fired. But in these models we're looking at just the Boltzmann restricted layers. So this is what causes them to fire. Either they don't or they do. It's a yes or no, true, false, all or nothing. It accepts the weighted sum of the inputs, the bias, as input to any activation function. So whatever our activation function is, it needs to have the sum of the weights times the input. So each input, if you remember on that model, and let's just go back to that model real quick. And then you always have to add a bias. And you can look at the bias if you remember from your Euclidean geometry. You draw a straight line. Formula for that line has a y coordinate at the end. It's always cx plus m or something like that, where m is where it crosses the y coordinates if you're doing a straight line. With these weights, it's very similar, but a lot of times we just add it in as its own weight. We take it as a node of a one value coming in, and then we compute its new weight, and that's how we compute that bias, just like we compute all the other weights coming in. The node which gets fired depends on the y value, and then we have a step function. And the step function, this is where, remember I said it's going to get complicated and simple all at the same time? We have a lot of different step functions. We have the sigmoid function, we have just a standard step function, we have the ReLU, it's pronounced like ray, the ray from the sun, and lu, like a name, so ReLU function. And we have the tangent h function. And if you look at these, they all have something similar. They all either force it to be one value or the other. They force it to be, in the case of the first three, a 0 or a 1, and in the last one, it's either a -1 or a 1. And you can easily convert that to a 0, 1, yes, no, true, false. And on this, one of the most common ones is the step function itself, because there is no middle value. There is no discrepancy that says, well, I'm not quite sure. But as you get into different models, probably the most commonly used, it used to be the sigmoid was most commonly used, but I see the ReLU used more often. Really, depending on what you're doing, you just have to play with these and find out which one works best, depending on the data and your output. The reason to have a non-0-1 answer or something kind of in the middle is when you're looking at this and it's coming out, you can actually process that middle ground as part of the answer into another neural network. So it might be that the ReLU function says, hey, this is only a 0.6, not a 1. And even though the 1 is what's going into the next neural network or the next hidden layer as an input, the 0.6 value might also be going in there to let you know, hey, this is not a straight up 1 or a straight up 0, it's someplace in the middle. This is a little uncertain what's coming out here. So it's a very powerful tool, but in the basic neural network, you usually just use the step function. It's yes or no. Let's take a big step back and take a kind of an overview. The next function is, what is a cost function that we're going to cover? This is so important because this is your end result that you're going to do over and over again and use to decide whether the model is working or not, whether you need to try a different step function, whether you need to try a different activation, whether you need to try a fully different model used. So what is the cost function? Cost function is a measure to evaluate how good your model's performance is. It is also referred as loss or error, used to compute the error of the output layer during backpropagation. There's our backpropagation where we're training our model. That's one of our key words. Mean squared error is an example of a popular cost function. And so here we have the cost function C equals half of y minus y predicted, and then you square that. So the first thing is, real quick, if you haven't done statistics, this is not a percentage. It's not a percentage of how accurate it is. It's just a measurement of the error. And we take that error for training it, and we push that error backwards through the neural network, and we use that through the different training functions, depending on what model you're using, to train the neural network. So when you deploy the network, you're usually done training it because it takes a lot of computational force to train it. This is a very simple model. And so you deploy the trained one, but we want to know how your error is. And so how do we do that? Well, you split your data. Part of your data is for training and part of your data is for testing, and then we can also test the error on there. So it's very important. And then we're going to go one more step on this. We got to look at both the local and the global setup. It might work great to test your data on what you have on your computer, but that's different than in the field. So when we're talking about all these different tests in the error test, as far as your loss, you want to make sure that you're in a closed environment when you do initial testing, but you also want to open that up and make sure you follow up with the testing on the larger scale of data, because it will change. It might not fit the larger scale. There might be something in there in the way you brought the data in specifically, or the data group you used, or any of those could cause an error. So it's very important to remember that we're looking at both the local and the global context of our error. And just one other side note on a lot of the newer models of neural networks, by comparing the error we get on the data, our training data, with a portion of the test data, we can actually figure out how good the model is, whether it's overfitted or not. We'll go into that a little bit more as we go into some of the different models. So we have our output. We're able to figure out the error on it based on the square means usually, although there's other functions used. So we want to talk about what is gradient descent, another vocabulary word. Gradient descent is an optimization algorithm to minimize the cost function or to minimize the error. Aim is to find the local or global minima of a function. Determine the direction the model should take to reduce the error. So, as we're looking at this, we have our squared error that we just figured out based on the cost function. It says, how bad is my model fitting the data I just put through it? And then we want to reduce that error. So how do you figure out what direction to do that in? Well, it could be that you're looking at just that line of data coming in, so that would be a local minima. We want to know the error of that particular setup coming in. And then you have your global minima. We want to minimize it based on the overall data we're putting through it. And with this, we can figure out the global minimum cost. We want to take all those local minimum costs of each piece of data coming in and figure out the global one. How are we going to adjust this model to fit all the data? We don't want it to be biased just on 3 or 4 lines of data coming in. We want it to kind of extrapolate a general answer for all the data coming in. And this, of course, we mentioned it briefly about back propagation. This is where it really comes in handy, is training our model. Neural network technique to minimize the cost function helps to improve the performance of the network, back propagates the error, and updates the weights to reduce the error. So as you can see here is a very nice depiction of a back propagation. We have our predicted y coming out, and then we have, since it's a training set, we already know the answer, and the answer comes back, and based on, in case of the square means was one of the functions we looked at, one of the activation functions based on cost function. That cost function then, depending on what you choose for your back propagation method, and there's a number of them, will change the weights. It will change the weight going to each of one of those nodes in the hidden layer, and then based upon the error that's still being carried back, it'll change the weights going to the next hidden layer. And then it computes an error level on that and sends that back up. And you're going to say, well, if it computes the error into the first hidden layer and fixes it, why would it stop there? Well, remember, we don't want to create a biased neural network. So we only make small adjustments on these weights. We don't make a big adjustment that changes everything right off the bat. So no matter how far back you go, you're always going to have a small amount of error, and that's still going to continue to go all the way back up the hidden layers. For right now, focus on the back propagation is taking that error and moving it backwards on the neural network to change the weights and help program it so that it'll have the correct answers. So far, we've been talking about forward propagation neural networks. Everything goes forwards, goes left to right. But let's take a little detour and let's see what is the difference between a feed-forward neural network and a recurrent neural network. Now this is in the function, not when we're training it using the back propagation. So you've got new information coming in and you want to get the answer. And there's a couple different networks out there, and we want to know, we have a feed-forward neural network and we have a new vocabulary term, recurrent neural network. A feed-forward neural network. Signals travel in one direction from input to output. No feedback loops. Considers only the current input. Cannot memorize previous inputs. One example of one of these feed-forward neural networks, and we've covered a number of them, but one of the ones that has a big highlight nowadays is the CNN, a convolutional neural network. TensorFlow, the one put out by Google, is probably most known for their CNN, where the information goes forward. It first takes a picture, splits it apart, goes through the individual pixels on the picture so it picks up a different reading, then calculates based on that, goes into a regular feed-forward neural network, and then gives your categorization on there. Now, we're not covering the CNN today, but we do have a video out that you can look up on YouTube, put out by Simplilearn, the convolutional neural network. Wonderful tutorial. Check that out and learn a lot more about the convolutional neural network. But you do need to know that the CNN is a forward propagation neural network only. So it's only moving in one direction. So we want to look at a recurrent neural network. Signals travel in both directions, making it a looped network. Considers the current input along with the previous received inputs for generating the output of a layer. Has the ability to memorize past data due to its internal memory. And you can see they have a nice image here. We have our input, and for some reason they always do the recurrent neural network in reverse from bottom up in the images. Kind of a standard, although I'm not sure why. Your X goes into your hidden layer, and your hidden layer, the answer for part of the answer from that it generates feeds back into the hidden layer. So now you have an input of both X and part of the hidden layer, and then that feeds into your output. Now, if we go back to the forward, let me just go back a slide, and we're looking at our forward propagation network. One of the tricks you can do to use just a forward propagation network is if you're in what they call a time sequence. That's a good term to remember, or a time series, meaning that it's sequential data. Each term comes after the other. You can trick this by creating your input nodes with the history. So if you know that you have values 1, 5, and 7 going in, and you know what the output is from what those outputs are, you can expand the input to include the history input. That's one of the ways to trick a forward propagation network into looking at that. But when you do it with a recurrent neural network, you let the hidden layer do that for you. It sends that data and reprocesses it back into itself. What are some of the applications of recurrent neural network? The RNN can be used for sentiment analysis and text mining. Getting up early in the morning is good for health. And it's a positive sentiment. One of the catches you really want to look at this when you're looking at the language is that I could switch this around and totally negate the meaning of what I'm doing, so it would no longer be positive. So when you're looking at a sentence, knowing the order of the words is as important as the meaning of the words. You can't just count how many good words there are versus bad words to get a positive sentiment. You now have to know what they're addressing. And there's lots of other different uses. Kids are playing football, or soccer as we call it in the US. RN can help you caption an image. So based on previous information coming in, it refeeds that back in, and you have a image setter. And then time series problems like predicting the prices of stocks in a month or quarter or sale of products can be solved using an RNN. And this is a really good example. You have whatever your stocks were doing earlier this month will have a huge effect on what they're doing today if you're investing. So having an RNN model, a recurrent neural network, feeding into itself what was happening previously allows it to take that model and program in that whole series without having to put in a month at a time of data. You can only put in one day at a time, but if you keep them in order, it will look back and say, oh, this is because of what happened yesterday. I need some information from that, and I'm going to use that to help predict today's, and so on and so on. We're going to go back to our activation functions. Remember I told you ReLU is one of the most common functions used? So let's talk a little bit more about ReLU and also softmax. Softmax is an activation function that generates the output between 0 and 1. It divides each output such that the total sum of the outputs is equal to 1. It is often used in the output layers. Softmax L of the n equals e to L of the n over the absolute value of e to the L. So what does this function mean? I mean, what is actually going on here? So we have our output nodes, and our output nodes are giving us, let's say they give us 1.2, 0.9, and 0.4. As a human being, I look at that and I say, well, the greatest value is 1.2, so whatever category that is, if you have 3 different categories, maybe you're not just doing if it's a cat or it's a dog or, let's say it's a cow. Maybe we had cats and dogs earlier. Why the cats and dogs are hanging out with a cow, I don't know. But we have a value, and it might say 1.2 is a cat, 0.9 is the dog, and 0.4 is a cow. For some reason it thinks that there's a chance of it being any one of these 3 items, and that's how it comes out of the output layer. Well, as a human, I can look at 1.2 and say this is definitely what it is. It's definitely a cat or whatever it is. Maybe it's looking at different kinds of cars might be a better, whether it's a car, truck, or a motorcycle. Maybe that'd be a better example. Well, from a computer standpoint, that might be a little confusing because they're just numbers waving at us. And so with the softmax, we want all those numbers to always add up to 1. So when I add 3 numbers together, I want the final output to be 1 on there. And so it goes through this formula, changes each of these numbers. In this case, it changes them to 0.46, 0.34, and 0.20. They all add up to 1. And that's a lot easier to register because it's very set. It's a set output. It's never going to be more than 1. It's never going to be less than 0. And so you can see here that there's probably a pretty high chance that it's the first one. So as a human being, we have no problem knowing that. But this output can then also go into, say, another input. So it might be an automated car that's picking up images, and it says that image in front of us is probably a big truck. We should deal with it like it's a big truck. It's probably not a motorcycle, or whatever those categories are. That's the softmax part of it. But now we have the ReLU. Well, where's the ReLU coming from? Well, the ReLU is what's generating the 1.2 and the 0.9 and the 0.4. And so if you remember, our ReLU stands for or rectified linear unit, and is the most widely used activation function. We looked at a number of different activation functions, including tangent H, the step function. I remember I said the step function is really used if that's what your actual output is, because then you know it's a 0 or 1. But the ReLU, if you have that as your output, you now have a discrepancy in there, and if that's going into another neural network or another process, having that discrepancy is really important. And it gives an output of x if x is positive and 0 otherwise. So it says my x value is going to be somewhere between 0 or 1. And then the usually, unless it's really uncertain, the output's usually a 1 or 0. And then you have that little piece of uncertainty there that you can send forward to another network, or you can look at to know that there's uncertainty involved. And is often used in the hidden layers. This is what's coming out of the hidden layers into the output layer usually. Or as we referenced the convolution neural network, the CNN, which you'd have to go to another video to review, the ReLU is the most common used for convolutional part of that network. It has a bunch of little pieces that are very simplified, looking at all the different images or different sections of the map, and the ReLU works really good for that. And like I said, there's other formulas used, but this is the most common one, and you'll see that in the hidden layers going maybe between one layer and the next layer. So just a quick recap, we have our softmax, which means that if you have numerous categories, only one of them is going to be picked, but you also want to have some value attached to it, how well it picked it. And you put that between 0 and 1, so it's very standardized. So we have our softmax. We looked at that. Let's go back one. We looked at that here, where it transforms the numbers. And then we have our ReLU function, which takes the information and the summation and puts it between a 0 and a 1, where it's either clearly a 0 or, depending on how confident our model is, it'll go between the 0 and 1 value. What are hyperparameters? Oh, this is a great interview question. Hyperparameters. When you are doing neural networks, this is what you're playing with most of the time once you've gotten the data formatted correctly. A hyperparameter is a parameter whose value is set before the learning process begins, determines how a network is trained and the structure of the network. This includes things like the number of hidden units, how many hidden layers are you going to have, and how many nodes in each layer. Learning rate. Learning rate is usually multiplied once you've figured out the error and how much you want to change the weights. We talked about, or I mentioned it early just briefly, you don't want to just make a huge change, otherwise you're going to have a biased model. So you only take some little incremental changes, and that's what the learning rate is those small incremental changes. Epochs. How many times are you going to go through all the data in your training set? So one epoch is one trip through all the data. And there's a lot of other things depending on which model you're working with and which programming script you're working with. Like the Python sklearn package will have it slightly different than, say, Google's TensorFlow package, which will be a little bit different than the Spark machine learning package. So these are just some examples of the hyperparameters. And so you see in here we have a nice image of our data coming in, and we train our model, then we do a comparison to see how good our model is, and then we go back and we say, hey, this model's pretty good, but it's biased. So then we send it back and we change our hyperparameters to see if we can get an unbiased model, or we can have a better prediction on it that matches our data closer. What will happen if learning rate is set too low or too high? We have a nice couple graphs here. We have one over here that says the learning rate set too low, and you can see that it slowly works its way down the curve. And on the right, you can see a learning rate set too high. It's just bouncing back and forth. When your learning rate is too low, that's what we studied at 2 slides ago, that's what the learning rate was, training of the model will progress very slowly as we are making very tiny updates to the weights. We'll take many updates before reaching the minimum point. So I just mentioned epoch, going through all the data. You might have to go through all the data 1,000 times instead of 500 times for it to train. Learning rate too high causes undesirable divergent behavior to the loss function due to drastic updates in weights. At times it may fail to converge or even diverge. So if you have your learning rate set too high and it's training too quickly, maybe you'll get lucky and it trains after one epoch run, but a lot of times it might never be able to train because the weights are changing too fast. They flip back and forth too easy. And you see down here we've introduced 2 new terms, converge and diverge. Converge means that our model has reached a point where it's able to give a fairly good answer for all the data we put in. All those weights have adjusted and it's minimized the error. Diverge means that the data is so chaotic that it can never manage to train to that data. The data is just too chaotic for it to train. So we have two new words there, converge and diverge, are important to know also. What is dropout and batch normalization? Dropout is a technique of dropping out hidden and visible units of a network randomly to prevent overfitting of data. It doubles the number of iterations needed to converge the network. So here we have our standard neural network, and then after applying dropout. Now it doesn't mean we actually delete the node. The node is still there, and we're still going to use that node. What it means is that we're only going to work with a few of the nodes. A lot of times, I think the most common one right now used is 20%. So you'll drop out 20% of the nodes when you do your training. You reverse propagate your data. And then you'll randomly pick another 20 nodes the next time you go through an epic data training. So each time you go through one epic, you will randomly pick 20 of those nodes not to mess with. And this allows for less overfitting of the data. So by randomly doing this, you create some, I guess it just kind of pulls some nodes off to the sides and says we're going to handle the data later on so we don't overfit. Batch normalization is a technique to improve the performance and stability of a neural network. The idea is to normalize the inputs in every layer so that they have mean output and activation of 0 and standard deviation of 1. This question covers a lot of different things, which is great. It's a great interview question because it pulls in that you have to understand what the mean value is. So a mean output activation of 0, that means our average activation is 0. So when you normalize it, remember usually we're going between -1 and 1 on a lot of these. It's a very standard setup. So you have to be very aware that this is your mean output activation of 0. And then we have our standard deviation of 1. So we want to keep our error down to just a 1 value. The benefits of this doing a batch normalization is it provides regularization, it trains faster, higher learning rates, and weights are easier to initialize. What is the difference between batch gradient descent and stochastic gradient descent? Batch gradient descent. Batch gradient computes the gradient using the entire data set. It takes time to converge because the volume of data is huge and weights update slowly. So you can look at the batch as, a lot of times if you're using big data, batch the data in, but you still go through a full epic. You still go through all the data on there. So batch gradient descent means you're going to use it to fit all the data and look for a convergence there. Stochastic gradient descent. Stochastic gradient computes the gradient using a single sample. It converges much faster than batch gradient because it updates weight more frequently. Explain overfitting and underfitting and how to combat them. Overfitting happens when a model learns the details and noise in the training data to the degree that it adversely impacts the execution of the model on the new information. It is more likely to occur with nonlinear models that have more flexibility when learning a target function. An example of this would be if you're looking at, say, cars and trucks and motorcycles, it might only recognize trucks that have a certain box-like shape. It might not be able to notice a flatbed truck unless it's only a specific kind of flatbed truck or only Ford trucks because that's what it saw on the training set. This means that your model performs great on your trained data and great on maybe a small test amount of data, but when you go to use it in the real world, it leaves out a lot and is not very functional outside of your small area, your small laboratory data coming in. Underfitting, doing the opposite when you underfit your data. Underfitting alludes to a model that is neither well trained on training data nor can generalize to new information. Usually happens when there is less and improper data to train a model, has a poor performance and accuracy. So if you're using underfitted data and you generate a model and you distribute that in a commercial zone, you'll have a lot of people unhappy with you because it's not going to give them very good answers. So we've explained overfitting and underfitting, so now we want to ask how to combat them. Combating overfitting and underfitting. Resampling the data to estimate the model accuracy, k-fold cross-validation. Having a validation data set to validate the model. So when we do the resampling, we're randomly going to be picking out data, and we'll run it a few times to see how that works, depending on our random data and how we sample the data to generate our model. And then we want to go ahead and validate the data set by having our training data, and then keeping some data on the side, testing data to validate it. How are weights initialized in a network? Initializing all weights to 0. All the weights are set to 0. This makes your model similar to a linear model. So if you have linear data coming in, doing a basic setup like that might work. All the neurons in every layer perform the same operation given the same output and making the deep net useless. Right there is a key word. It's going to be useless if you initialize everything to 0. At that point, be looking into some other machine learning tools. Initializing all weights randomly. Here the weights are assigned randomly by initializing them very close to 0. It gives better accuracy to the model since every neuron performs different computations. And here we have the weights are set randomly. We have our input layer, the hidden layers, and the output layer. And W equals NP random, random N. Layer size L L minus 1. This is the most commonly used, is to randomly generate your weights. What are the different layers in CNN? Convolutional neural network. First is the convolutional layer that performs a convolutional operation. We have our other video out if you want to explore that more, so we can go into detail exactly how the convolutional layer works in the CNN as far as creating a number of smaller picture windows that go over the data. The second step is as a ReLU layer. ReLU brings nonlinearity to the network and converts all the negative pixels to 0. Output is rectified feature map. So it goes into a mapping feature there. Pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. So we have all our ReLU layer, which is pulling all these little maps out of our convolutional layer. It's taking that picture and creating little tiny neural networks to look at different parts of the picture. Then we need to pool it together. And then finally, the fully connected layer. So we flatten our pooling layer out, and we have a fully connected layer recognizes and classifies the objects in the image. And that's actually your forward propagation, reverse propagation training model, usually. I mean, there's a number of different models out there, of course. What is pooling in CNN, and how does it work? Pooling, used to reduce the spatial dimensions of a CNN, performs downsampling operation to reduce the dimensionality, creates a pooled feature map by sliding a filter matrix over the input matrix. I mentioned that briefly on the previous slide. It's important to know that you have, if you see here, they have a rectified feature map. And so each one of those colors, like the yellow color, that might be one of a smaller little neural network using the ReLU. It'll just kind of go over the main picture and look at all the different areas on the main picture. So you might step 1, 2, 3, 4 spaces. And then you have another one that's also looking at features. And it has a 2, 7, 8, 5. Each one of those is a map. So it might be, the first one might be a map looking for cat ears, and the second one looking for human eyes. When it does this, you then have this rectified feature map looking at these different features. And the max pooling with a 2x2 filters and a stride of 2. Stride means instead of skipping every pixel, you're going to go every 2 pixels. You take the maximum values. And you can see over here, when we look at a pooled feature map, one of the features says, hey, I had a max value of 8, so somewhere in here we saw a human eye labeled as 8, pretty high label. And maybe 7 was a human hand, and maybe 4 was cat whiskers, or something that we thought might be cat whiskers. 4 is kind of a low number in this particular case compared to the other ones. So you have your full pooled feature map. You can see the process here as we have our stepping. We look for the max value, and then we create a pooled feature map of the maxed values. How does a LSTM network work? And that's long short-term memory. So the first thing to know is that an LSTMS are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. We did look at the RNN briefly, talked about how the hidden layer feeds back into itself. With the LSTM, it has a much more complicated feedback, and you can see here we have the hidden layer of T-1 and the hidden layer, that's what the H stands for, hidden layer of T, and the formula is going in. As we can see here, we have the hidden layers. We have T-1 and then H of T, where T stands for time. So this is a series. Remember, working with series, and we want to remember the past. And you can see you have your input of T, and that might be a frame in a video. As a frame comes in, they usually use in this one the tangent H activation formula, but you also see that it goes through a couple other formulas, the omega formula. And so when it combines these, that then goes into the next layer, your next hidden layer. That then goes into the data that's submitted to the next input. So you have your X of T+1. So when you have that coming in, then you have your H value that's coming forward from the last process. And depending on how many of these omega structures you put in there, depends on how long-term the memory gets. So it's important to remember this is more for your long-term recurrent neural networks. The 3 steps in an LSTM. Step 1 decides what to forget and what to remember. Step 2 selectively updates cell state values. So based on what we want to remember and forget, we want to update those cell values. And then decides what part of the current state make it to the output. So now we have to also have an output on there. What are vanishing and exploding gradients? This is a great question that affects all our neural networks. While training an RNN, your slope can become either too small or too large, and this makes the training difficult. When the slope is too small, the problem is known as vanishing gradient. So our slope, we have our change in x and our change in y. When the slope decreases gradually to a very small value, sometimes negative, and makes training difficult. When the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. The slope grows exponentially. You can see a nice graph of that here. Issues in gradient problem: long training time, poor performance, and low accuracy. What is the difference between epoch, batch, and iteration in deep learning? Epoch. An epoch represents one iteration over the entire data set. So that's everything you're going to go ahead and put into that training model. Batch. We cannot pass the entire data set into the neural network at once, so we divide the data set into a number of batches. And then iteration. If we have 10,000 images as data and a batch size of 200, then the epoch should run 10,000 times over 200. So that means we have our total number over the 200 equals 50 iterations. So in each epoch, we're running over all the data set, we're going to have 50 iterations. And each of those iterations includes a batch of 200 images in this case. Why TensorFlow is the most preferred library in deep learning? Well, first, TensorFlow provides both C++ and Python APIs that makes it easier to work on. Has a faster compilation time than other deep learning libraries like Keras and Torch. TensorFlow supports both CPUs and GPUs computing devices. So right now TensorFlow is at the top of the market because it's so easy to use for both programmer side and for hardware side and for the speed of getting something up and running. What do you mean by tensor in TensorFlow? Tensor is a mathematical object represented as arrays of higher dimension. These arrays of data with different dimensions and ranks that are fed as input to the neural network are called tensors. And you can see here we have a tensor of dimensions 5, 4. So it's a two-dimensional tensor coming in. You can look at an image like this, that each one of those pixels is a different value if it's a black and white. So it might be 0 and 1s, and then each one represents a black and white image. In a color photo, you might either find a different value system, or you might have a tensor value that has the XY coordinates as we see here, plus the colors. So you might have 3 more different dimensions for the 3 different images, the red, the blue, and the yellow coming in. And even as you go from one layer or one tensor to the next, these layers might change. We might flatten them, might bring in numerous. In the case of the convergence neural network, we have all those smaller different mappings of features that come in. So each one of those layers coming through is a tensor if it has multiple dimensions coming in and weights attached to it. What are the programming elements in TensorFlow? Well, we have our constants. Constants are parameters whose value does not change. To define a constant, we use tf.constant command. Example, a equals tf.constant 2.0 tf float 32. So it's a tensor float value of 32. B equals tf constant 3.0. Print AB. If we did a print of AB, we'd have tf.constant, and then of course B is that instance of it. Variables. Variables allow us to add new trainable parameters to graph. To define a variable, we use tf.variable command and initialize them before running the graph in session. Example, w equals tf variable 0.3 d-type tf float 32, or b equals the tf variable minus 3 comma d-type float 32. Placeholders. Placeholders allow us to feed data to a TensorFlow model from outside a model. It permits a value to be assigned later. To define a placeholder, we use tf placeholder command. Example, a equals tf placeholder, b equals a times 2. With the tf session as SESS, result equals session run, b comma feed dictionary equals a 3.0, print result. So we have a nice example there of a placeholder. Session. A session is run to evaluate the nodes. This is called as the TensorFlow runtime. So for example, you have a equals tf constant 2.0, b equals tf constant 4.0, c equals a plus b. And at this point, you'd go ahead and create a session equals tf session, and then you could evaluate the tensor c print session run c. That would input C as an input into your session. What do you understand by a computational graph? Everything in TensorFlow is based on creating a computational graph. It has a network of nodes where each node performs an operation. Nodes represent mathematical operation and edges represent tensors. Since data flows in a form of a graph, it is also called a data flow graph. And we have a nice visual of this graph, or graphic image of a computational graph. And you can see here we have our input nodes, our add, multiply nodes, and our multiply node at the end. And then we have the edges where the data flows. So we have from A going to C, A going to D. You can see we have a 2 flowing, 4 flowing. Explain generative adversarial network along with an example. Suppose there is a wine shop that purchases wine from dealers, which they will resell later. So we have our dealer going to the wine, our shop owner that then sells it for a profit. But there are some malefactor dealers who sell fake wine. In this case, the shop owner should be able to distinguish between fake and authentic wine. The forger will try different techniques to sell fake wine and make sure certain techniques go past the shop owner's check. So here's our forger, fake wine, shop owner. The shop owner would probably get some feedback from the wine experts that some of the wine is not original. The owner would have to improve how he determines whether a wine is fake or authentic. Goal of forger, to create wines that are indistinguishable from the authentic ones. Goal of shop owner, to accurately tell if the wine is real or not. There are two main components of generative adversarial network. And we'll refer to it as a noise vector coming in, where we have our forger who's going to generate fake wine, and then we have our real authentic wine, and of course our shop owner who has to figure out whether it's real or fake. The generator is a CNN that keeps producing images that are closer in appearance to the real images, while the discriminator tries to determine the difference between real and fake images. The ultimate aim is to make the discriminator learn to identify real and fake images. What is an autoencoder? The network is trained to reconstruct its inputs. It is a neural network that has 3 layers. Here the input neurons are equal to the output neuron. The network's target outside is same as the input. It uses dimensionality reduction to restructure the input. Input image comes in, we have our Latin space representation, and then it goes back out reconstructing the image. It works by compressing the input to a Latin space representation and then reconstructing the output from this representation. What is bagging and boosting? Bagging and boosting are ensemble techniques where the idea is to train multiple models using the same learning algorithm and then take a call. So we have in here where we're bagging, we take a data set and we split it. We're going to have our training data and our test data, very standard thing to do. Then we're going to randomly select data into the bags and train your model separately. So we might have bag 1, model 1, bag 2, model 2, bag 3, model 3, and so on. In boosting, the emphasis is to select the data points which give wrong output in order to improve the accuracy. So in boosting, we have our data set. Again, we split it to test data and train data. And we'll take bag 1 and we'll train the model. Data points with wrong predictions then go into bag 2, and we then train that model and repeat.
And with this, we have come to the end of this advanced deep learning full course. If you like this video, subscribe to our YouTube channel and hit the bell icon to never miss any updates from Simplilearn. Please let us know in the comment section below if you need help opting for this Caltech postgraduate program in AI and machine learning course. We will get back to you as soon as possible. Until next time, thank you and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.